Good morning and welcome. My name is Brian Collard. I am the HVAC program coordinator for PG&E. I welcome you. Thank you very much for your attendance. We still have people rolling in here, so I am going to take some time just to do a bit of housekeeping. You have a control panel in front of you that has some gray bars going across it. The first gray bar is the audio tab, and if you drop that down, if you're having any audio issues, you could use that to phone call in. As long as you're on a good landline or a cellular connection, you could push the phone call method, and then you could utilize the telephone number and the access code to call into the webinar that may clear up any audio issues that you have. The way that we run our webinars is typically through the questions tab, but Steve has agreed to open up the microphones and he will call on attendees. If you could please follow the raise hand protocol if you have any questions, and then you'll be able to interface directly with our instructor. And then next is, if you have questions, you're more than welcome to utilize the questions tab for note purposes and things of that nature, maybe to push it out to the entire audience. I'll be monitoring the questions tab, but you have the opportunity to interface directly with our instructor today. I'll open up the mics here shortly. Next is the handouts tab. There is a copy of today's presentation in the handouts tab. Please download that, utilize it to follow along, and then make notes, and then also for future reference. I'll also be placing a link in the chat here shortly. Oh, actually, Steve already did that. Thank you very much, Steve. Appreciate that. Steve put a link. You could utilize that link to download the content also. So follow that link, and then it will take you to a website where you could download the content, and then you'll have it and be able to hold it forever. And so next, I'm going to go into safety. This is optimizing the design and control of chilled water plants. Your instructor today is Steve Taylor. So thank you very much for joining us. And let's go into safety. PG&E, we take our safety very serious. Please speak up for safety. Several of you may work out in the field and be on different job sites. You may see something that is a safety issue, and you never know when you may be able to save someone's life, not only your own, but a colleague. And so if you see a safety issue, please point it out. Take notice of it. Make sure you identify it to someone on that job site as a safety issue. And then, of course, hopefully correct the safety issue and then get back to work. Please take care of yourself during the course of this presentation. We are here for 8 hours today, so this is a long one, folks. So please prepare yourself for that. Steve does have breaks built in as well as a lunch break. Make sure you're taking care of yourself. You're stretching throughout the day, making sure that you hydrate. You take some breaks here and there when necessary. So just take care of yourself. Please follow good ergonomics. I suffer from back pain myself. So I throw a pillow behind my back, or I have an arch support in my chair. It helps out immeasurably. It's helped me, straighten my posture, and then also, important also is your screen height and your keyboard position. Next, in the event of an emergency, we're going to call 911. Oh, Steve, if you get back out of there, please, sir. And then if you're calling in from California, this is earthquake country. Please remember, drop, cover, and hold. Active shooter, we're going to get out, hide out, or take out that individual. Please remember your path of egress out of your home, making sure that, or place of business, that you have a place to meet in the event of an emergency that is safe. And then the most important thing on this slide is the call 811 before you dig. This is a free service offered by all the utilities. When you call 811, before you dig in the ground, you'll provide pertinent information, name, phone number, address, and then what will happen is I've utilized this free service personally myself. I've called first thing in the morning. They typically open up and start taking, calls at 7. I've had utilities and, Comcast telephone services showing up as soon as midday. So please utilize this vital service. Please call 811 before you dig. We're still in this pandemic. I want to disclose I have colleagues, friends, neighbors, loved ones still coming down with this. I had a colleague that got COVID, announced it on our team meeting on Monday. I got COVID in July. And so the reason I think I got COVID was because I went back to shaking hands. So since then, I've changed that behavior. I went back to the fist bump, and so it may be something that you want to utilize. But here's the thing: is wash your hands for at least 20 seconds. Utilize hand sanitizer after you handle items from others, or cough or sneeze. Help protect yourself and your family. And go bags, very important, especially with the wildfires in California. Here's the thing, folks. There's a reason why the military has bug out bags. And so some items you would want to have in a go bag are, medications if you're on any. Imagine if you was asked to evacuate and you didn't have your medication for, say, for example, your heart. That would be an awful experience. And so you would want your medications in there, cash, credit cards, changes of clothes, food, water, just essentials to get you through a period of time if you're ever asked to evacuate. So create one, keep one, throw it in a closet. You always got it, and you never know when it will save your backside. This is being recorded. This class will go up as on demand. We do have the authorization from Taylor Engineers to post this as an on demand. But folks, I want to be very clear with you. On demand is great if you're just trying to get some information, but you have a instructor that has a wealth of knowledge. And so please utilize that. Ask questions, be involved in this class. It makes it that much more enjoyable for all the attendees, including the instructor. So pick this person's brain. He is, has a lot of notoriety within the Bay Area. He's done several engineering projects. He knows chiller design inside and out. So please ask questions. You can utilize the microphone and the raise hand feature to get Steve's questions. To get questions answered by Steve. So please utilize that functionality. I'll unmute all the attendees here shortly so you can interface directly with Steve. So disclaimer slide, during the course of this presentation, Taylor Engineers may share different products and manufacturers. PG&E does not endorse any one product or manufacturer, so please remember that during the course of this presentation. This is my QR code. You can scan this with your smartphone, camera phone, as long as it's a newer generation or at least updated cell phone. This is much like you go to a restaurant now and you can scan the menu with the use of a QR code. Once you scan this, you could bookmark it on your phone, and then you could utilize this to access, register, take classes via mobile device, all from your cell phone. And so please scan this, bookmark it. I have 60 plus classes on anything and everything that you would like to know about HVAC. Some classes that I have going on right now is refrigerants. I have a class on new generation refrigerants that's in process right now. It's a 3-day series. I also have a class that is on residential 3D design, where they're using gaming interfacing to do load calculations. I also have a lot of classes on electrification. This is a hot topic in California right now, so please scan this. Bookmark it like I stated, and then you always have access to our classes. I will be placing in the chat a survey link, and then Steve will also be highlighting that later on in the class. Please provide valuable feedback on this class or any new classes you would like to see at PG&E. I do look at these personally. I review them carefully, and there has been classes that has spurned out of those comments from different attendees. So please make sure you follow the survey link and provide valuable feedback. And with further ado, I'm going to turn this over to our instructor. Steve, you have the floor, please, sir.
Okay, thank you. Appreciate it. So just a brief resume of mine, and you can see that I've been very involved with ASHRAE over the years and many of their committees. And I highlighted a couple that are very pertinent to this particular seminar. The first one there is Guideline 36. If you haven't heard of Guideline 36, it's pretty revolutionary, quite frankly. It's a standardized sequence of operation for HVAC systems that are built off of research projects to optimize controls. And the idea behind that is to have sequences that are pre-programmed, pre-debugged, pre-proven to work, and standardized so that they can be repeated over and over without having to reprogram them every single project, so we don't reinvent the wheel all the time. And in this class, we'll talk about guideline 36 sequences for chill water plants and hot water plants. So the latest version of it has both of those in great detail. So if you're interested in control sequences, and after this class you probably will be, I suggest that you buy guideline 36. It's available off of, it's only like, you know, 30 bucks or something. And with it, you get a PDF of the sequences, but you also get a Word document of the sequences that you can cut and paste and edit yourself for your own projects. And then the next one is the fundamentals of design and control of central chill water plants. That's an ASHRAE, they call it a self-directed learning course. And it's a long book essentially on design of chill water plants. And this course here follows that manual in great detail. So it's really a version of that, a very much shortened version, of course, but it's a version of that. So again, I think that would be a good purchase. You don't have to actually take the course if you don't want to. There's questions and answers that you can submit and get credit for it, but you get the book, and that's the most important thing. And then the last one there is RP 1711. That was the research project that created the sequences of operation for chill water plants that's now in guideline 36. So those are the foundations of what we'll be talking about in terms of control sequences here today. All right, so normally I would say, who are you? And if this was live, you'd all raise your hands. Since we aren't live, that will be sort of difficult to do. The course is really designed towards practicing engineers, you know, whether you're design build or consulting engineers, someone who's actually going to be designing chill water plants. It also can be useful to building engineers that are operating chill water plants and energy consultants that are modeling chill water plants. But it's the primary focus is design engineers. So here's the schedule. We'll talk about chill water distribution systems first, and the various different kinds. We'll introduce all the chill water systems that are sort of out there, and later on, after lunch, you can see we have a section here called selecting chill water distribution systems. So we'll introduce them here, and then give you a chart that helps you select the right one for your plant. We'll talk about balancing variable flow systems. Almost all of our systems these days are variable flow, and so it's important to understand balancing issues or lack thereof. Then we'll break, and then we'll talk about degrading delta T, one of the problems that occurs in plants where the temperature difference between supply and return water starts degrading lower than what you designed it for, and the ways you can mitigate that. Then we'll talk about condenser water systems, distribution systems, break for lunch, select chill water distribution systems, as I mentioned, and then selecting chill water and condenser water delta T. So this is basically, how do I design, what temperatures do I design hot and chill water systems to? And it's related to how we size the pipes for those systems, because that's a big first cost impact. And we'll talk about cooling towers, take a break, and talk about selecting chillers. We'll talk about two different ways of selecting chillers, sort of a long way and a short way, and talk about the advantages and disadvantages of each. And then we'll get into controls. And so we'll spend quite a bit of time talking about optimized control sequences. And as I mentioned, it'll be largely based on the guideline 36 sequences, which came from ASHRAE Research Project 1711. And then last, I'll have a brief introduction of a new plant design called TIER, Time Independent Energy Recovery. And it's a all-electric plant that one of my partners invented, and we've been using on a few of our projects. It's super energy efficient as well as very cost effective. So I'll talk about that in very basically an overview, because it's a pretty complicated plant, so we won't have a lot of time for it. One of the resources that you can make available to yourselves is all the articles on our website. So if you go to the Taylor Engineers website, you can go to the article section. There are various chillwater plant related articles. So the first one here, the solving the large all electric problem, is the tier plant concept. So that gives you lots of detail on how the tier plant came to be and how to design it. The second one is value-based HVAC system equipment selection. And I'll talk about this when we get into chiller selection on a way of picking equipment that is value-based rather than low bid based that I think you'll like. It's a good practice that doesn't take a lot of time and has much better results than sort of traditional practices for picking equipment. I'll talk about balancing variable flow systems in great detail in this class. So this is an article on that. Changeover controls is using coils for both heating and cooling, and then a whole bunch of other details here. These 5 classes in the middle here are related to this course. So those were journal articles that were written based on the fundamentals of controls for chillwater plants that ASHRAE, that's self-directed learning class that I mentioned earlier. Waterside economizing, I'll talk a little bit about that here. And then sizing pipes using life cycle cost. I will discuss that here because sizing piping is very much tied to how we design the plant. We actually pick the sort of piping first and then the chillwater delta T's and hot to water delta T's second. And the techniques I'll be teaching you later on. And then this optimizing chillwater plant control was a method that helped us develop the control sequences that are now in guideline 36, and et cetera, et cetera, et cetera. So we have lots of documents here that you can download for free from our website. By the way, as mentioned, if you have questions, just go ahead and ask them. You should be unmuted, and you can just interrupt me and ask questions. More on our website are design guides and tools. So there's another section of our website called Design Guides and Tools, and it has various tools for you to use that, again, are for free. The first one is expansion tank selection. It's amazing to me how few people actually know how to select properly an expansion tank. So we have some articles written on that, but also a free spreadsheet you can use to calculate the sizing of an expansion tank. And then we have a couple of spreadsheets used for the selection of, well, first one is a piping optimizer that allows you to use life cycle cost to select pipe sizes. I'll talk about that in some detail today, but this is an actual spreadsheet you can use. And one of the nice things about it is that it also calculates your pump head, and quite accurately. So all the information in the spreadsheet about the fitting losses and pressure drops from various valves and check valves and everything else are all fairly accurate. So you can use this to not only size pipe, but to also calculate pump head very accurately and very quickly as well. And then one of this document here is a spreadsheet for collecting data on chillers if you want to use our long version of how to select a chiller. I'll talk about use of this later on today. And then there's 2 design guides. The first is this Cool Tools design guide. This was actually funded by PG&E and around 1997, 1999. It's free, but it's from 1997, 1999, so it's a little dated. This other one here is essentially the second version of the Cool Tools plant design. It's a more expanded version and made up to date, much more information on controls, for instance, and other details. And it's relatively new, 2017, but it's not free. So you can get that from the ASHRAE. You can click on the link on our site, but just Google it and you can get it off of ASHRAE. $140 for ASHRAE members, and that basically is what this plant is going to, what this class is going to be talking about. So the scope of that design guide and the scope of this class is to talk about new construction, and we cover hydronics system design, both the distribution system selection itself and how to size a pipe and delta T's, et cetera, chiller selection, cooling towers, control optimization, and we mentioned commissioning, but we don't really get into a lot of detail in this class. There is detail in the design guide. And then you can also apply this design guide to retrofits, replacing chillers, adding variable speed drives to make your plant variable speed, variable flow. And then all the control optimization stuff also applies to existing plants as well as does commissioning. Optimizing the energy use of and life cycle cost of a chill water plant is really complicated because there's so many variables. So with chillers, we have different types of chillers, including whether they are screw or centrifugal, whether they have variable speed drives or not, their inherent efficiency, which is essentially how much copper there is in the heat exchanger, and then how that the size of the chiller or chillers relates to the size of the load in the building. Cooling towers also have a lot of variables, the fan type, inherent efficiency, how you selected it in terms of approach to wet bulb, the range, flow options like variable speed drives, and then how much the flow can be turned down when you have a multiple cell plant. Chill water pumps have the arrangement design, whether it's direct pipe to a chiller or whether it's headered, flow and delta T, overall pressure drop, whether you have variable speed drives or not. Same with condenser water pumps with flow and delta T. You'll notice I don't have variable speed drives listed here under condenser water pumps. We'll talk about that and why we really don't think it's a good idea to put variable speed drives on condenser water pumps. And then the air handling system is also part of this because the chill water coil is going to affect the air side pressure drop and the energy efficiency of the air handler. As we'll learn later, though, it turns out that the air side pressure drop is not as significant of an issue as one might think in how you select chill water temperatures and delta T. So you have all these variables, and these will affect, these will affect the first cost and the inherent energy efficiency of the plant. But then adding that to that even more is how do you control all these variables? What's the control logic to affect these things? As an example, if we make the cooling tower temperature, leaving water temperature colder, we make the chiller more efficient, but we make the cooling tower use more energy. So where's the optimum temperature and fan speed control? What's the optimum there? It's very complex. So ideally, we would design a plant to have the lowest life cycle cost. So we would account for the first cost of all these different pieces of equipment and based on all the variables. And then we look at also the interaction among them in terms of not only design, but also how they're controlled. Unfortunately, there's just too many variables. It's basically impossible to do a life cycle cost analysis in great detail for every single component. Even if it were possible, it just wouldn't be worth the effort. You'd spend all of your engineering fee doing analysis, and you still at some point have to put pen to paper and create a design that eventually gets built. So it just isn't practical to do that much analysis. What is practical is to design subsystems that are near life cycle cost using techniques that are based on life cycle cost. So as part of the chill water manual that we developed originally for PG&E and then later for ASHRAE, we did incredible amounts of optimization analysis, but we broke the building into, or the system into subsystems. So we have the chill water system, the condensed water system, et cetera. We looked at the life cycle optimization of each of those subsystems and came up with rules of thumb for how to design each of those subsystems to make them near life cycle cost optimum. And that's what this course is about. That's what I'm going to teach you is the rules of thumb and the design guidance that we developed. And it wasn't just made up. We developed it after tons of analysis in the optimization of the plant. And you'll notice the optimization is life cycle cost optimization. That doesn't mean it's the most energy efficient plant. It means it's the one that has the lowest life cycle cost. Life cycle cost is composed not just of energy, but also first cost and to a lesser extent maintenance costs on the plant. So all of our analysis was done with all three of those variables in mind in terms of the optimization. All right, let's start with chill water distribution systems. As I mentioned earlier, we'll start out teaching you about basically all the distribution types that are out there. And then this afternoon, we'll have a simplified method for picking which of those plants is the optimums for your application. So plants can be divided into two types, constant flow and variable flow. For constant flow, there's two ways of achieving constant flow. One is to have no control valves in it at all, nothing to make the flow vary. And then the second, it was three-way control valves. Three-way control valves are not exactly constant flow, as the valves vary from modulating flow through the coil or around the coil. It actually results in flow that's not really constant, but for practical purposes, we call it constant flow. For variable flow, we have various types: primary only, primary secondary. And then you can add pumps to that, make it primary, secondary, tertiary. And then we have some primary, secondary alternates or options. One is distributed secondary. This is where you apply generally for a central plant serving a campus, where you can put pumps at each building, and you have primary pumps at the plant, distributed pumps in each building. And then we can also have coil secondary pumps, where we put pumps on each coil that are variable speed, and they vary the flow through the coil. I'll talk about each of these as we go along. So the simplest system is simply a single chiller and a single coil with no control valve. And instead of controlling the load on this coil with flow variation, the sort of typical way, is we do it with temperature variation. So whatever control loop would normally modulate a chill water valve, we actually make it reset the water temperature off of the chiller. And so this is pretty simple. The pump is constant speed, constant flow, and we vary the water temperature. Now you might think, well, this isn't very good because it's a constant flow pump. We want to get into variable flow and variable speed. One thing that's I'll emphasize over and over again is that the chiller is the big user of energy in a chill water plant. It uses way more energy, an order of magnitude more energy than a pump does. And so in general, we want to treat the chiller better than the pumps. We want to make them more efficient. Well, chiller efficiency is a function of what we call lift. And lift is the difference between the leaving chill water temperature and the leaving condenser water temperature. So I'm not showing the condenser side of this thing, but it's on the other side that goes to the cooling tower. And lift, if the smaller it is, the more efficient the chiller is. And this is basic thermodynamics. So we want to make that lift as low as we can. So resetting water temperature to control air temperature is actually way more efficient than changing the pump speed. So if we had the chiller deliver 44-degree water all the time, and we modulated the flow through the coil and saved some pump energy, we would use way more energy than just running the pump constant and resetting the water temperature, because the chiller again uses way more energy than the pump. So it's more, always favor making the water warmer. We'll talk about this with variable flow plants as well, but it's always better to make the water warmer when you can. So this is a very energy efficient design, even though it's super simple. Now, a couple of things here. Why, you might think, where would we have one coil? Well, we actually design buildings like that all the time. We, meaning Taylor engineers. We like airside economizers, and we want them on all of our buildings. But when we build a high-rise building, you want that, it almost requires that you have a central air handling system on the roof so that you can get air in and out for the economizer, as opposed to floor by floor. So we want the system on the roof, and what you can end up with is one giant air handler that serves the entire building. And so it is possible to have one coil and a chiller plant serving it for the building. So this isn't just a trivial thing. We've got, you know, a dozen buildings where we have one giant air handler serving the building. Now you may think that's not very energy efficient to have one giant air handler. In fact, it is energy efficient, and it can be more energy efficient than floor-by-floor air handlers. So if you want to read about that, we actually have an article on our website as well called Designing Mega Air Handlers, which is big air handlers. So we have some that are 240,000 CFM. We've got one that's almost 500,000 CFM, one air handler being built right now. So and it uses basically this design. The storage tank is here because when you have a close coupled system like this, there's not a lot of piping involved. The chiller, hopefully, is right next to the air handler. There's not a lot of piping, so there's not a lot of mass in the system. And the chiller is going to behave better if it has a little bit of thermal inertia to keep it from short cycling. So that's what the storage tank is for. Almost always needed with a system like this that's close coupled with not a lot of piping in there. Now, a variation on this is to put the chillers in series. So if I have more than one chiller on it, it's actually better to put them in series than to make them in parallel. And this is what we do on some of those mega air handlers that I talked about. And it's actually discussed in that article as well, is put the chillers in series with each other. Now, why is this important? Well, remember, efficiency is a function of lift. The warmer the water temperature, the more efficient the chiller is going to be. So if I have two chillers making 45-degree water, that's a lot of lift. If I split it in two, one of them can make 55-degree water, and it's going to be way more energy efficient because it's making warmer water. So even though the overall delta T is still 65 to 45, I split it in two, I actually save energy. Now, of course, pump energy goes up because now I have these units in series with each other. So I'm going to have a little bit that given back to pump energy. But all in all, a plant with series chillers roughly is about 8 to 10% more efficient than a plant with parallel chillers on the chill water side. Now we can also put them on the condenser water side. So not shown here is the condenser water temperature. Let's pretend that this is a condenser water going in. I can also have the condenser water in series. And we call this, so we have it primary, this is called series counterflow, where the chill water is going in one direction and the condenser water is going the other direction, so that the lift, this one sort of reduces some of the benefit of the counterflow or the series on the chill water side, because we now are doing the series on the other side, but it makes the cooling tower smaller, and it makes the chillers very similar in capacity and size to each other, so it sort of makes the selection a little bit easier. Now, in the chill water plant manual and in this class, we don't talk about series chillers all that much. And that's really because we hadn't really been doing much in the way of series chillers when we wrote that manual. We're now doing series and series counterflow on several of our plants, and we sort of like it. It generally doesn't cost more. It can cost more because the pipes are bigger, but if you pipe it cleverly, it doesn't cost more. What's also not shown here is that you're going to want bypasses around the chillers when they turn off. So each of these is going to have a bypass around them. And this is a motorized bypass. So this is an actuated valve. So when the chiller is off, we just open the valve to reduce the pressure drop, and so we don't pump water through an inactive chiller. When we engage the chiller, we close the valve and it pushes water through the chiller in there. So a few things missing from this, but this is a common design, again, for that one coil mega air handler plant. Another option is to have constant flow using three-way valves. And if I have three of these three-way valves, both Title 24 and 90.1 say that's okay. And where might that be? A small system, that just has a few coils and you don't want to get into the complexity of variable flow, you got to keep in mind that variable flow adds a lot of complexity to the system, because as we'll talk about later, the chiller has a limited range of flow it can have. The coils have range from 0 to 100%. They can go any range of flow, but the chiller can't. And so adding variable flow to the system with two-way valves, for instance, adds complexity. And if it's just a tiny little 10-ton chiller serving 3 coils, it just doesn't make any sense to get into that kind of complexity. And don't forget, the chill water pump energy really isn't that big a part of the plant's energy. Most of it's the chiller. So we don't want to get anal about going variable flow just because it's sort of the cool thing. So 90.1 and Title 24 say that if you have 3 of these 3-way valves, that's fine, you can do that. Another example where you might see that is 2 or 3 big air handlers on a roof serving an office building. So sort of like those mega air handlers that I talked about, it's now instead of 1 big air handler, it's 2 big air handlers, one on the east, one on the west kind of thing. And again, it's if it's all close coupled on the roof up there, there's only 2 air handlers, it may not make sense to get into variable flow. And then this one is a partially variable flow system. This is where we have variable flow at some of the coils with 2-way valves, but we do have some 3-way valves, and the 3-way valves are sized for the minimum flow. So the chiller might be able to go down to say 50% of its design flow. And so about half of the coils in that case would have 3-way valves, so that you just add up the GPMs of the flow for the coils that have 3-way valves, and you want it to add up to the minimum flow of the chiller. And that way we can be variable flow on the other ones. And we can still use a variable speed drive. It probably won't save a lot of energy, because if we're only going down to 50% flow, but it still saves some. Variable speed drives are not very expensive these days, and so the cost of using variable flow is not super high, and so it can still be cost effective. Okay, so if I have this system, where do I locate the 3-way valves? If I put them at the end of the system, that's good in terms of gauging the mass. So remember in that first slide I showed we added a storage tank, a buffer tank, to provide mass to the system. Here we don't have a buffer tank. Instead, we can put the 3-way valves at the end of the system, and that way we engage all the water in all the mains going out there. So we've added mass to the system effectively by putting the 3-way valves at the end. And our differential pressure sensor is also going to go out at the end, like it's shown here. And if we're maintaining this at a constant pressure, then all the flow through all the chill water valves is also going to be relatively constant. And we want it to be relatively constant because, remember, it's providing the minimum flow for the chiller. But it's still self-balancing on the 2-way valves. We'll get into balancing variable flow systems later on this morning. And 2-way valves are essentially self-balancing. They'll take just as much water as they want. And so we still can be self-balancing for all of the 2-way valves, even though we have 3-way valves in the system. So that's the advantages of putting them at the end. If we put them close to the pump, in other words, put these 3-way valves up here, we save a little bit of pump energy, because now I don't have to push all that water that's providing my minimum flow all the way to the end of the system. It would be shorter, and therefore the pressure that the pump has to create would be less. But this is a minor impact, and these are major. So this is where you want to put the 3-way valves, right at the end of the system, to get all these advantages. So what happens if we have multiple chillers and multiple coils? And this can end up with, if this is, let's say these 2 air handlers right here were serving an office building, and both air handlers were roughly running at the same schedule. They're serving similar loads, office building loads. This plant design right here is perfectly fine. We'll find that when one air handler is at roughly half load, the other one's at roughly half load. So I can turn off one of the pumps and one of the chillers and stage the pumps pretty well. But what happens if these coils are not serving loads that are fairly similar? For instance, it's probably an unrealistic example, but it makes the point. Let's say it's serving 2 ballrooms. Each of them are 240 GPM each, but they're on different schedules. So I can have one of them operating and the other one not operating. What happens if ballroom A is running and everybody's in there and it's filled with people and lights are on and it needs all of its 240 GPM to handle the load? But let's say ballroom B is unoccupied at the time. It doesn't need any flow through its coil. So 0 GPM through the coil. So how many chillers do we have to run? Well, the problem with variable three-way valve systems is they use the water whether they need it or not. So you can see that ballroom B has 0 GPM through the coil, but all that flow is getting bypassed around. So I'm still using 240 GPM here as well as here, even though the load on the coil is half. So the load on the plant is half, but I'll starve the ballroom A if I turn off one of the chillers. So I have to run both the chillers and both the pumps. So this is an example where when you have a variable flow system, if I use three-way valves, then the load and the flow don't match each other. And so that can cause staging problems at the plant. I may have to inefficiently stage the chillers to make sure that I have enough flow in the plant. And it's problems like this that gave birth to variable flow systems that I'll talk about next. So variable flow systems. We have a problem. We had big buildings. We had a problem with matching flow to load. And so the solution was variable flow. Variable flow can occur in two ways. The most common way is two-way valves, but I can also use variable speed pumps at the coils to provide variable flow through them. I'll talk about both. Then we talk about configurations. We have primary, secondary, and then variations of primary, secondary, such as primary, secondary, tertiary, and distributed secondary, et cetera, that I mentioned earlier, and then primary only. So let's talk about first primary, secondary. And primary, secondary was given birth because of this old paradigm. So a long time ago, meaning essentially up until the late 90s, controls were not very smart. They're proportional kind of controls. They were by that time, the late 90s, they were already digital, but they weren't very clever in how they worked. And so they responded mostly to changes in temperature, and they weren't able to handle changes in flow, particularly any kind of radical change in flow. So if you tried to change the flow in the chiller, it would often overcool and make the water get too cold, and it would trip on a low temperature safety. That would lock out the chiller. Usually it's a manual reset, so very much a pain. The building engineer would have to go up there to the chiller plant and reset it. If you did it radically and quickly enough, then you could actually freeze the evaporator and cause some major damage. So the old paradigm was we need to maintain constant flow through the chiller. But again, we want it to be variable flow through the coils so that we don't have this mismatch of load and flow. So how do we do that? Well, that's where the concept of primary, secondary came along. And the fundamentals are of when I have a joint, we have conservation of matter. So the goes into is equals to the goes out is. So we have what goes into this this junction is what equals goes out. And then another fundamental is that when I have two circuits connected to each other with a common element, if there's no pressure drop through this common element, then no flow is induced through the other leg. If I start squishing down on say a valve in this common leg between these two circuits, then I'll induce flow through this one. But if I keep the pressure drop very, very low, then this circuit and the other circuit are independent of each other. So a little bit cleaner example is let's take a primary secondary system where I have a primary pump and I have a secondary pump, and they share this common pipe that's shown in red here. If both pumps are on and both of them were designed for 100 GPM, then the two pumps are running, they're each doing 100 GPM, and this element between the two actually has no flow going into it. So the water coming in here is 100 GPM, it goes out 100 GPM, therefore it has 0 GPM going forward, and then it comes back. So the two systems are operating together, each doing 100 GPM. Now let's say we turn off the secondary pump. So there's no flow in this system. The primary pump continues to do 100 GPM, and now the flow does go through the common leg, but because it's very low pressure drop here, it's not inducing any flow through here. So I have 0 GPM through here and 100 GPM through here. So you can see that the primary circuit isn't affected by what happens with the secondary pump. It's 100 GPM when it's on, it's 100 GPM when it's off. So no matter what happens to the secondary circuit, the primary circuit is essentially constant flow. Now, of course, you can't be 0 pressure drop through here, but you can be low enough that it really doesn't matter. And essentially, there's no induced flow through here, and therefore no induced flow through here. So this gives us then what we want. We want to have variable flow through the secondary and constant flow through the primary so that the chillers can see primary constant flow. And here's how it's drawn up with the chillers in it. I have my chiller circuit, and I have constant speed primary pumps. By the way, you'll see that these pumps are dedicated. This pump pumps that chiller, this one pumps that chiller. I'll talk about that in a minute using a headered arrangement. But the concept is basically the same, is that I can start and stop chillers here, and it doesn't even matter if the condenser water, the chill water pump serving the coils are even on or not, right? We're independent circuits. This circuit and this circuit are independent of each other, so I can be constant flow or staged flow in the primary circuit while I'm variable flow in the other circuit. So when you put these systems together, by the way, you always want to draw, why I did that, draw the actual circuits, because when you draw them, when you go through the common leg, they actually have to be counter flow to each other. The primary goes in one direction and the secondary goes in the other. That's the only way it's going to work. So make sure you draw those in there when you're laying it out to make sure that you don't end up piping it incorrectly. So the two flows have to go against each other. So you see the arrows here flow in both directions. Conceptually, that's what's happening. This arrow is for the primary, this area is for the secondary. In reality, the flow will pretty much always go in this direction. I'm not sure what's making these little spikes here. Sorry, it's some weird thing with PowerPoint. Because we want to keep the primary bigger than the secondary. I'll explain that later when we get into staging chillers. But conceptually, they go in both directions for the two systems. So that's primary, secondary. So the original design, again, was to make it so that the chillers saw constant flow while the coils see variable flow. You can also do this with series chillers. This is primary, secondary. It may not look like primary, secondary because it's a little odd. These pumps are sort of shown on this side. They could also be over on this side. That doesn't make any difference. These could be over here if you wanted to. And then it looks a little bit more like the previous diagram. But here the primary pumps are sucking off the circuit, putting the water back. Most of the time, the primary flow is going to exceed the secondary flow. So we actually have flow going backwards right here. And so that it's delivering 55 degrees off of here. Some of it's going to actually go backwards and blend with 65. That's returning to unload this chiller. So at design flow, there's no flow, there's no backwards flow, but on partial flow, there is. So this has, again, the benefits of the series chillers. You also could do this without the pumps, right? I could just put a valve in here, and I could push the water through. This would be a primary only variable flow. If I got rid of the pumps and I put a valve in there, now it would be primary only variable flow, where this pushes the water through there when they're in series with each other. So it'd be a little different system, but you can see that it's piped very much the same. Now we have various options on the secondary pumps. This is called distributed secondary. So the primary pumps are just sort of normal. You'll notice that they're headered right now in this case over here instead of dedicated. Again, I'll talk about that later. There are two variations. They both essentially work for primary, secondary. But instead of having secondary pumps back at the plant, I move the pumps out into the system. So this could be a pump serving one coil, as is shown here, or it could be a pump serving multiple coils where this is out at some remote building, building B. And this could be the normal primary or secondary system with two-way valves. I'll talk about both of these variations and when you might want to use them this afternoon. And then we have primary, secondary, tertiary. This is where we have primary pumps, secondary pumps back at the plant, and then in each building, I would have either primary, secondary, tertiary, where the pumps are again, common leg between primary and secondary, a common leg between tertiary and secondary. This is commonly called a bridge connection, or I can put them in series with each other. Well, in the early days where we didn't have variable speed drives, you pretty much had to have them like this with a common leg, so that one pump, because it couldn't unload, wouldn't push water through the system when you didn't want it to. Now with variable speed drives, you should never ever need a tertiary connection. The pumps should all be in series with each other's, and so that the secondary pumps and the tertiary pumps would be in series with each other. Why does that work? Because we now have variable speed drives, and we can slow down these pumps so that it doesn't push water through the system. The problem with tertiary connections like this with common legs is that inevitably it ends up with blending, where you blend this return with the supply. And you never want to blend in a system from an energy efficiency standpoint. Blending water never saves energy on a chill water plant. It always makes the pump energy go up, and it doesn't save any chiller energy. The fundamentals of the chiller's energy is what's the temperature of the water leaving the chiller. That determines its lift, and its lift determines its efficiency. And so once I made the water cold, you should just use it at that temperature. Blending it with return water to warm it up will not save any energy. It makes the pump energy go up, and it has no impact on the chiller energy. So this relates to some systems that may deliberately blend. If this were serving, say, chill beams or radiant floors, in that case, you do want to blend. So you could remove my X here. And because there you're blending not for energy saving reasons, you're blending because the water needs to be warm so that it doesn't cause condensation. You don't want condensation on your radiant floor. You don't want your chill beams dripping on somebody's head. But just note that when you do that, you're not saving any chiller energy. One of the benefits of radiant and chill beams is that they can work with warmer water, but the water has to come out of the chiller that warm in order for it to actually save any chiller energy. So you need to have a dedicated chiller to serve that warmer water load. Blending doesn't work. So again, if you guys have any questions, just interrupt me. All right, let's move on to variable flow chilled water systems, variable flow through the chiller. So remember, the old paradigm was the chillers can't handle it, variable flow. Well, the new paradigm is modern controls are very robust. They can handle both variable flow and variable temperature at the same time. So it's okay to have variable flow through the chillers. And we do have to keep in mind that there's a range. There's going to be a minimum flow that the chiller wants. And also there's a speed of change, a rate of change that the chiller manufacturer may specify. How quickly does that flow change? And we don't want it to be too abrupt, or the controls won't be able to handle it. Now, having done this for a while, when we first did the first variable flow system I was involved with was in the early 1990s. And then the chiller controls were very finicky, and we had to be very careful about rate of change issues. Now they've gotten to be quite robust, and you would have a hard time making one of the modern chillers trip, even with radical changes in flow and very quick changes in flow. Nevertheless, we include a lot of control sequences that make sure that the changes in flow are gentle, just to make sure that they don't trip. So here's the classic case. It sort of looks like primary, secondary, but with the secondary pumps gone. Like if you go back and you look at the primary, secondary slide, there was pumps right here. We just take those out. And so suddenly we have a primary only system, sort of. In fact, the common leg isn't a common leg anymore. It's a minimum flow bypass. And whereas in the primary secondary system, this bypass or this common leg was deliberately oversized, meaning it was sized basically the same as the chiller mains to keep the pressure drop down, to keep the systems decoupled. Now with primary only, we don't want this to be a big pipe. We want it to be a little pipe and a little valve sized just for what the minimum flow needs to be. And I'll talk about that in a minute. So big difference there. Early on, when people started changing from primary secondary to primary only, they kept the basic design the same, got rid of the secondary pumps, and they kept this bypass the same pipe size as these chiller mains. What that does is it means controlling the minimum flow super difficult because the minimum flow is quite low. And you've all heard about oversized control valves and things like that. We can't control flow if we have a big giant valve in there, so it doesn't work. So we have to be very careful about sizing this bypass. It will definitely be smaller than the pump mains. So even though it looks sort of like this is the common leg in the primary secondary, it ain't. So keep that in mind. You'll notice another variation on pumping here where we have the pumps again headered together. I'll talk about that a bit later. And when you header them together, you need to have isolation valves to turn off the flow because the dropping a pump won't do that. All right, so we have a minimum flow bypass, and in order to make it work, we need a flow meter or some way of measuring flow. I'll talk about that in a minute too. And then we have two-way valves out in the system, and we control the primary pumps now with differential pressure at the end of the system, just like we used to control the secondary pumps. So what about that primary flow bypass valve? Where do we put it? In the diagram I showed you before, we showed it right back at the plant, and that's certainly one of the options. If you do put it at the plant near the chillers, it's best for energy. This is sort of the same reason why three-way valves, if they were put closer to the plant, were better than putting it at the end of the system in that previous design. If I put it at the plant, I don't have to pump all that minimum flow. The minimum flow, by the way, is going to be like 40 or 50% of your design flow. And so I don't send all that 50% of the water all the way to the end of the system and back again. That makes the pump energy go up. So it's better to have it close by. Controls are less expensive if it's near the chiller. There's a rule with controls that the controlled device, which is the two-way valve in this case, and the controlled variable, which is the flow in this case, and the controller, the device that's doing the control, all have to be connected to each other. So the control loop, the control device, the control variable all connect together. So if I have a controller at the plant, these devices tie right into it, and I have a control loop that says, okay, maintain the minimum flow, it's all together. If I move that bypass out to the end of the system, I have to hardwire that valve all the way back to the plant so that it's being controlled by the plant that's measuring the flow. So it just adds to that cost. Also, by putting that valve way out at the end of the system, I have a time delay that's going to occur. So that's this third bullet here, is it's hard to tune the loop because I'm sensing flow, I make the valve open, but the flow meter doesn't see it for a little bit. There'll be a time delay by the time that valve opens and it affects the flow. That water sort of find its way back to the plant. So it makes it a little more difficult to control that way. On the other hand, when it's close together like this, I bypass water, it immediately affects what's happening with the plant. So if I'm bypassing cold water, say 42-degree water, putting it right back into the chiller, if I don't have very stable control of this valve, then I'm going to have erratic control through the chiller, and I'm going to cause cycling inner water temperature, which is causing short cycling of the chiller. So it makes the sizing and the tuning of this valve super critical. If I put it out the remote, I have less chance of that unstable control or that cycling control, but I still have the instability I mentioned earlier with the physical distance between the two. One possible benefit of putting it at the end is the water is cold everywhere all the time, so I can have instantaneous response. When a fan coil turns on, for instance, it gets chill water immediately. If the bypass is at the plant, maybe the water going out in that leg to that one fan coil has no flow through it, and it may take a while for the water to get there. That's seldom an important issue because loads do not cause a space to overheat instantaneously. It takes a while, right? So if it takes 30 seconds or a minute for water to get from the plant to a coil, it's not going to make any difference. So don't put bypass at the end because it keeps the system cold. That it's not helpful. Most of the time, we do this. We put it at the chiller because of all these benefits. Better for energy, controls are less, but we have to be very careful in how you size the thing in order to not have this problem here. So how do you size it? It's, as I said, it's very critical when the valve is at the chillers and the pumps, and it also, sizing it depends on whether I have a variable speed drive or not. So you'll notice up here it says variable speed drive is optional. Pretty much all of our variable flow plants will have variable speed drives on them. You don't have to, you can ride the pump curve. If I do ride the pump curve, then the pressure as flow goes down goes up. My pressure gets higher as flow goes down because I'm going to ride the pump curve up. If I have a variable speed drive, as the flow goes down, my pressure gets less than it is. So what we typically do is size the valve. Usually you have a variable speed drive, so let's assume you did. And imagine that this system's going way out here, and I'm going to measure my flow with a DP sensor across here. When I'm at really low flow and I need my bypass to come into play, so when I don't have enough flow here for the minimum flow, I'm going to have fairly low pressure in the system because there's not a lot of flow going out here. I don't need the pressure. So this might be as low as like 5 psi. And if there's not a lot of flow in the mains, then it's also 5 psi up here or close to it. And so what I'll do then is I'll size the valve for the minimum flow of one chiller only, minimum flow of one chiller at 5 psi. Now, why one chiller? Well, I'm only going to be running one chiller when I'm at low flow. And so if I have 2 chillers on, that's because I have enough flow for 2 chillers. I don't need to worry about the minimum flow. So you size it for one chiller at about 5 psi pressure drop. That's how you get the C sub V of this valve. Now, just be aggressive on this. It's actually better to undersize this than to oversize it. If you undersize it, it just means you run the pump energy a little bit higher to squish the water through. If you oversize it, it will be very hard to tune, and you'll end up with problems. So be very careful when you put that bypass there. Okay, now how about flow measurement? I also show a flow meter. That's nice because it's the most accurate. It's also, you want flow in order to do BTU calcs. As we'll see when we get into the controls this afternoon, is that I need to know what the load is in order to optimally stage my chillers. And load is the flow times the delta T. So I need that flow measurement. Other people, to save a little money, will put DP across the chiller. So they'll put a DP sensor across here. And they'll correlate that to flow by looking at the manufacturer's data on flow versus pressure drop. So they control that. Over time, you know, as the tubes might foul or whatever, that correlation is not going to be that good. So all in all, you might save a few bucks by using DP instead of a flow meter, but it's not worth it. So you definitely want to use the flow meter option. And if you take the X4 73 class, which is a UC Berkeley class, UC Extension, you'll learn that the best kind of flow meter is a full bore magnetic flow meter. They're not as expensive as they once were, and that's what we always use in our plants here. Full bore means it's the size of the pipe. It's not an insertion meter, it's a full bore meter, and it's extremely accurate, extremely reliable, and it's not that expensive. You're only buying one of them, so the budget can handle it. Use a good meter. I mentioned all along here that we have various options for how to pipe the pumps. First option is to dedicate them. Second option is to header them. And the third option is a sort of combination of the two, where you header them, but with a whole bunch of manual valves to allow you to change which pump serves the chiller. So option A is dedicated. What's the advantage of that? A little bit less controls complexity, because I can actually control the pump from the chiller's own controller. So the chiller controller will have a contact on it, and you can actually physically or through the DDC system tie that contact to the chiller. So the chiller will say, I want my pump to run, and I want my pump not to run. If you, when we get into these options over here, we have to be careful about when we start and stop chillers, because chillers need the pump to run before they actually turn themselves on. They need flow. And when they turn off, they want the pump to run a little bit longer than after you told it to go off, so that it has, it can sort of unload itself as well. So we have to build that logic into the pump logic here. Over here, we don't have to, because the chiller is telling it itself. So it has its own time delays built right into it. So that's nice. Custom pump heads with unmatched chillers. So if these were three different kinds of chillers, let's say one was a pony screw chiller, and then one was an absorption chiller, and one was a centrifugal chiller, they may all have different heads. So let's say that this has a 20-foot head here, this one has a 10-foot head, and this one has a 15-foot head. Each of these pumps could be sized for that head. So they're all sized for the same system head, but this pump can have a 10-foot higher pressure drop head than this one, and a 5-foot higher than this one. So that you can customize the pump heads. Now, why is that nice? It just saves a little pump energy. So I don't have to, whereas over here, they all have to be sized for the one that has the most pressure drop. So if this is 20 and this is 10 and this is 15, they're all headered together. So they all have to be able to produce 20 PSI or 20 feet. So what I have to do is have a manual balancing valve that would chew up 10 feet, and a manual balancing valve here that would chew up 5 feet. And so I'm deliberately wasting energy with this device. So if I have unmatched chillers, this can be an advantage. Next item is, usually this is less expensive if the pumps are adjacent to the chiller serve. So if it's laid out just like this diagram shows, where I have a chiller and right in front of it is the pump, this can be less expensive because there's less piping. Now, a lot of people think that pumps like to be all next to each other. So they'll take these 3 pumps and they'll throw them into the corner of the chiller room, and then they have a dedicated pipe going all the way across the room to each chiller from there. Then it won't be less expensive. So pumps don't need to be collected together. It does save you perhaps on the inertia base, if there's an inertia base, but that's about it. You'll spend more in piping. So when you lay out a plant, and I'll talk about this a little bit later as well, when we talk about condenser water pumps, laying them out literally like this, where physically the pump and the chiller are in line with each other, is the way to do it to save money. And then lastly, a pump failure doesn't cause multiple pump trips. So let's say I have all 3 of these chillers running and all 3 of these pumps running. If one of the pumps fails, only its chiller will trip on lack of flow. The other ones just keep cruising along. Whereas over here, let's say I have 2 pumps running and 2 chillers running, and one of the pumps fail, immediately the flow drops 50% through both chillers, because the flow will just split. So what will happen is, unless those chillers have very robust controls, you will lose both chillers. They'll both trip off because I lost one pump. So this is a little more robust. So what does this mean? In option A then can be used where I have, it's best used where I have a plant where that safety is just unacceptable. So this might be a data center. So we do data centers. We often will pipe them this way, not only because of this last item down here, the pump failure issue, but also because we modularize the controls with a data center so that if I lose a controller, I only lose one element of the plant. So you'll end up putting the chill water pump, the chiller, the condensed water pump, even a cooling tower on the same controller together. So if you lose anything, including the controller, I only lose one element of the plant and the rest of it keeps going. And so that's so this is the data center option A. Option B has better redundancy. This means that so over here, if I lose chiller 1, I've essentially lost chiller. If I lose pump 1, I've essentially lost chiller 1 as well, because no other pump can serve it. Whereas here, if I lose pump 1, and I haven't lost chiller 1. So if I lose pump 1 and chiller 3, I still have 2 pumps and 2 chillers that can run. Over here, if I lost pump 1 and chiller 3, I only have chiller 2, and I have no extra redundancy. So it's a little more flexible with redundancy here. And then over here, when I have them headered, I need control valves for each to stop the flow. You'll notice there's no valves over here. The pumps control the flow. But here we need these isolation valves. Well, the isolation valves not only isolate the pump, the chiller, but they can also modulate flow slowly. So when I get into staging chillers later on with primary only systems, I'll talk about how modulating these valves can make that happen. So that's a real plus. So for primary only systems, they really like this design because I can have slow, soft loading and unloading of the chillers with these valves. And then lastly, it's easier to include a standby pump. It simply is put in parallel with all the rest. You can imagine if I put a fourth pump over here, it would have to be separately piped into each of the chillers so that it would be very awkward and expensive to do. So if you want a redundant pump, this is the way to go. The last option was simply recommended by somebody who was peer reviewing my paper on this subject. And he said, if you need to put this in there because this is the option I always use. And to humor him, I said, fine. But frankly, this has no use in my mind. So forget it. So here we have data centers is option A, and virtually everything else is option B. And in particular, if you have primary only systems, you definitely have to use option, or you don't have to, but you want to use option B. So because of this soft loading issue. So almost all of our plants, except for data centers, use option. Let's go on to balancing variable flow systems now. And this is an important issue that I go into probably a little too much detail on, but I think it's worth the explanation. Again, if anybody has any questions, now's the time to ask. Okay, so balancing. First question is, why do we balance? Talk about that in a minute. And then we have various balancing options for variable flow and constant flow systems. I'm not going to talk about constant flow systems in this particular talk. I will talk about, it is talked about in the manuals that have been referenced here, but not talked about here. We'll be talking about variable flow system balancing. And then I'll talk about how we analyze these systems using a pipe simulation program to help us understand what was going on, and the results of that analysis on controllability, flow during transients, that's like warm up and cool down, pump energy costs, and first cost. Then I'll rank the different systems and where you might use them, make some recommendations. So all this comes from a paper that we wrote, one of my partners, Jeff Stein, and I wrote back in 2002. I talked about it again in 2017 on not balancing variable flow systems. So preview here, our recommendation is going to be not to balance variable flow systems. And I doubled down on why I didn't think it was a good idea. Both of these papers are available at our website. So why do we want to balance systems? We want to make sure that adequate flow is available in all the coils to meet their load. And what is adequate? Well, adequate is just mean that whatever it takes to work. You can have less than design flow and still be adequate most of the time. Coils are very non-linear. So if I have a coil that say is 10% low on flow, it's probably only 1% low on capacity. So it's very non-linear. So flow is not nearly as important as the salesmen who sell balancing valves will tell you. It can be it isn't that quite as important as one thinks. A second is to make sure that we don't end up with super high pressure drops across control valves. So if I end up with a large variable flow system, and the valves all opening and closing, and the way the pump is controlled, if I end up with a lot of pressure drop across control valves, they can do what we call two position. And that means if they open up a tiny bit and the flow is so big that it overcools and it shuts off again. So it ends up, instead of modulating, it's basically on, off, on, off, on, off, and it becomes unstable at the load. So that's an important issue. We want to make sure that the pressure drop isn't too high across the valves to cause two positioning. In the old days, by the way, when we used pneumatic actuators, the pressure drop across the control valve could not only cause two positioning, but it could also push the valve open. Pneumatic controls, the actuators don't have a lot of oomph, and they could have a shutoff capability as low as like 20 or 30 psi. So if the pump was delivering a lot of pressure, we would actually push the valves open. So balancing variable flow systems was more important back in the days of pneumatic controls than it is now. And then there's cost considerations. First, costs of how you balance the system or how you make it self-balancing, energy costs, and then rebalancing costs. So most systems, at some point in their life, people are going to add or subtract coils to the system. And so how is it, are there going to be any costs to rebalancing if that happens? So as an example, if I have a high-rise office building with reheat coils, through the life of that building, you're going to be doing tenant work over and over and over again in that building. So you're going to be adding coils and subtracting them. How sensitive is the system to adding and subtracting those loads? So in the paper that I referenced earlier, we looked at 7 different systems, and then we've added an 8th since then. First is no balancing, meaning we're simply going to rely on the two-way valves to automatically provide flow. What's the philosophy behind that? Well, the two-way valves are being controlled by a controller. The controller is generally using the air temperature off the coil as its control point. It's saying, I want to deliver a certain air temperature off that coil. And to get that, I need so much flow. And I'm not going to take more flow than that or less flow than that. I'm going to modulate to deliver the flow I need. So in that sense, the two-way valve is really an automatic flow regulating device. It's not just handling the low, it's handling the flow, because that's what's controlling the capacity of the coil. And so if that valve is able to modulate flow and deliver only what it needs, it's automatically self-balancing. Then we have manual balancing. This comes in 2 flavors. One is simply to use the ball or butterfly valve that's already at the coil for isolation purposes, and then use the coil pressure drop correlated to flow from the manufacturer's data, and you can use that for balancing flow. More commonly, though, people use calibrated balancing valves. These are balancing valves that have either a flow measuring device or a differential pressure device, some way of measuring flow, and on the valve itself. Usually it comes with a little kit that has a DP sensor on it that you can use to correlate pressure drop and valve position to the flow. So it's called a calibrated balancing valve. A common brand name is Circuit Setter, which is Bell & Gossett's name. So often people say, I have a Circuit Setter, even though it might be made by some other manufacturer. That's the Kleenex name for calibrated balancing valve. Then we have automatic flow limiting valves. These are valves that will limit the flow to a certain level. It doesn't do anything when the flow is less than that set point, but it will make sure that you don't go above that set point. And it does this through springs and other devices inside. Um, these are also called flow control valves, although that word is not a good word because it's not really controlling the flow, it's actually just limiting the flow. And a Kleenex name for this one is Griswold valve, because Griswold, the manufacturer who invented the first one of these, so you often hear people call them Griswold valves, even though it might be made by somebody else. And then we have various designs for making the system self-balancing without a balancing valve. First one is reverse return, and I'll explain this one later. It's easier with a diagram. Second was oversizing the piping mains to try to reduce the pressure drops in the mains, which helps it make self-balancing. And then we're going to undersize the branch piping or undersize the control valves. So manual balancing valves essentially create a pressure drop where you didn't have one before to limit the flow through the branch. And you say, well, why bother with a balancing valve? I'll just make the pipe smaller, and that will create that same pressure drop. And if you do this cleverly and correctly, I can actually reduce my first cost by making the pipes or the control valves smaller to make that happen and get the throttling that I want, but at lower cost instead of higher cost. The bad part about these two is that it takes a very accurate simulation of the piping system in order to do it, because you might end up undersizing the branch piping unless you're very, very careful, in which case you've now created the critical circuit as being this circuit that used to be oversized, now it's undersized. So both of these options I'm not going to talk about. It's talked about in the paper, but it's an option that we don't think many people are going to use, and that's why I'm not going to talk about it, because it requires an extra engineering effort and some and being very, very careful about how you do the undersizing of things. I can tell you this from experience, because when we first thought of this idea, I tried it on a job and I ended up screwing up and making a close circuit into the critical circuit, the one that needed the most pressure, because I undersized it too much. It's something big. So we've eliminated it from this discussion just because of that. But you can read about it in the paper if you want to hear about it. Now, when we did the paper, it was an ASHRAE journal paper, and ASHRAE doesn't allow you to talk about things that are proprietary. At the time we did it, there's only one pressure independent control manufacturer on the market, and that was a company that I won't say its name anyway, but it was only one company that had a product. Actually, they called it the Delta P valve. So that manufacturer had a pressure independent valve. They came up with the idea, but there's only one of them, and ASHRAE doesn't allow us to talk about something that's proprietary. So we had to eliminate it from our analysis when we did in the paper. However, we've added it to this discussion based simply on our subjective knowledge of what the valve does. We didn't redo all the pipe flow analysis. So speaking of the pipe flow analysis, here's the system that we did all this analysis on to evaluate all these balancing options. This is for a real building. You might recognize this building as the Ask.com building, downtown Oakland. We were doing tenant work, the first tenant work in the building. It finished right before a recession, and we were doing the tenant work for the first tenants in the building. And the building engineer insisted that we use manual balancing valves to balance the system. The hot water system in this building did not have variable speed drives on it. It was a two-way valve system, but the pumps just rode their pump curve. So they would create very high pressures when we only had a couple of the floors occupied here because they were sized for the whole building. And I told the building engineer, if we manually balance these coils, we are going to create a big pressure drop to chew up that extra pressure that the pump was creating. And when you add more coils to the building, when more tenants move in, you would have to rebalance the entire building, including the floors that we just did. And I said, you don't need to do this. Look across the bay over to San Francisco. Look at the high rises in San Francisco. Not one of them is manually balanced. They're all just relying on the two-way valves. And he didn't believe me. So we decided to do this analysis to prove to the building engineer that you really didn't, not only did you not have to balance the system manually, but you don't want to balance the system manually so that you end up having to rebalance every time a tenant comes into the building. So the hot water side of the system is the exact building over here. This is an actual system. But we took our floor and we basically duplicated it on all the floors to simulate the system. And again, it had constant speed pumps, and this is the building over here. Now, the cooling system in this building is actually a central system. There's 2 big air handlers on the roof. Not very interesting from a balancing standpoint. So we created a fake system and said, well, what happens if this had 20 floors of air handlers on it? And so we created a fake system for the same building, 20 floors, floor by floor air handlers, because they do have balancing sort of issues. But we put variable speed drives on them. All the valves are 2-way, and we used a commercial program called PipeFlow to do the analysis. So this is a program for usually for simulating civil engineering kind of things, like city scale kind of analysis is where it's most popularly used. But we wanted to use it for this building so we could accurately see what was happening with all the pressures and flows in the building. So here's the footprint of the building. The original design had 1 hot water riser, so when we did our floor with VAV boxes, we used a reverse return kind of thing. Now, reverse return, it means the supply goes in one direction, the return goes in the other direction, and the flow is actually parallel to each other. And I'll explain reverse return a little bit later because it's a little bit hard to do. But I wanted to make an aside on this one, that we didn't design the core and shell for this building. We just did the tenant work. And 2 things that we would do differently than what was done here. First of all, we would put in more risers. So if you're designing a building like this, all this horizontal piping that goes on every floor is expensive. The more risers you put in, the less piping you have on the floor. And if you add up all the vertical piping, it'll be much less pipe than all the horizontal piping you had on the floor. So more risers is actually less expensive. It's also cheaper to put in a riser than it is to put in a horizontal duct. It's just easier to support it. So if we were doing this building, we would have had more risers, at least 4, maybe even 6 risers on the building. Second comment is that we, we generally do not put the VAV boxes way out at the perimeter. We collect them all around the duct main that's in the floor. So the duct mains in this building are, what the hell are the duct mains in this building? Can't remember. Anyway, the supply risers of this building, those are the stair pressurization, I've forgotten. Anyway, there's 2 supply risers on this building coming down, and we would keep all the duct mains, the medium pressure mains near the core, all the VAV boxes near the core, and then duct out from there to diffusers at the zones. Why do that? It shortens the medium pressure duct work to the VAV boxes, which reduces pressure drop, and it shortens the piping runs. So all in all, even though you have your low pressure ductwork longer, it'll end up reducing costs and making it less energy used as well. So that's just an aside. So I'll talk about reverse return later on. And here's the coil piping, the simplest way you could pipe these coils for the various options. So you have to look back to see which of the options here. So the first one is the no balancing option. So we just have, this is the chill water coil here. We have butterfly valves. These would be ball valves for the reheat coils. So no balancing device is required here. But one thing that we've done, sometimes it's nice to diagnose what the flow is. So in our own projects, we always use option 1, or pretty much always. We put an extra test plug in on the other side of the control valve. And what that allows you to do is measure the pressure drop across the control valve. And when the control valve is wide open, we know what its C sub V is. And so using the fundamental equations, we can calculate what the flow is based on pressure drop and C sub V. So we're essentially using the control valve as a flow meter. Why do we do this? Not for balancing purposes, but for testing purposes. We want to see what the flow is when we first turn the system on and make sure we don't have any weird things going on. And if we're trying to diagnose a problem in the future, to see what the flow is. So this is basically the coiled piping diagram that we have in our system. Second option is the calibrated balancing valve. You'll notice that it's being used as a combination calibrated balancing valve and shutoff valve. Some engineers don't allow that. We don't allow it either if we don't use these valves, but if we were using them, if this is a ball valve, then we trust it as a shutoff valve, and so we allow it to be used for both shutoff and balancing. If it's a globe valve, we require another ball valve next to it or another butterfly valve next to it, because globe valves do not provide reliable, good long-term shutoff. In this case, we made a combination just to be aggressive on the pricing of things. Now we have the flow limiting valve, option 3. As I mentioned, it has springs and these engineered, computer designed, precisely engineered little plug here. As the pressure increases, this squishes into the valve. It starts hiding some of these openings, and that's how it very cleverly provides a constant flow, regardless of what the pressure drop across it is, up to a maximum, which is about 32 psi. Now you notice on these we also have a strainer. The strainer is because if you don't put a strainer in front of this valve, it will become the strainer, and will get all clogged up during startup with all the debris that's in the piping system when you first turn it on. Then the option 8 is the pressure independent valve, and it also has a strainer because it also has a lot of nooks and crannies that could get clogged up. I'll talk about exactly how pressure independent valves work in a minute, but this is a regulator style pressure independent control valve. So let's go start at the beginning, and we'll go through the balancing options. Option 1 for no balancing. So the advantages are no balancing labor. Now you are going to test it. So you are going to go out to each coil and you want to make sure you're getting some flow there, measure some temperatures, make sure that there's no plugs anywhere, no clogs, but you don't actually have to balance anything. You don't throttle any valves. And because of that, you can add and subtract coils with all day long. This is why your big high-rise building uses this approach, because it doesn't want to have to rebalance every time tenant work is done in the building. Disadvantages, it could have an imbalance during transients, such as warm up. So when I'm first warming up the building or cooling down if it's cooling, I first turn the system on, you're going to have more flow through the closer coils than the further away coils, and maybe that's a problem. And in fact, a lot of salesmen of flow limiting valves will argue that this is an important reason why you need some kind of balancing. Well, our flow analysis, which I'll talk about later, showed that this in fact is not an issue at all. So it's a possible issue, but it's not an actual issue. So not an issue. But what can be an issue is that if I have a big system with some big pumps, I can overpressurize some valves that are close to the pump and cause them to have controllability problems and tube positioning, things like that. So this one is definitely an issue that we need to think about on large systems. Manual balancing valves, advantages is that I have the valve there for measuring flow for future diagnostics as well as for balancing. And that's nice, but remember, all I need is that extra test plug, and I have that capability on the previous option as well, much less expensively. Some reduced overpressurization because I am going to throttle the valve here, so I do get some benefit of that. But I have a whole raft of disadvantages here. We have the cost of the balancing valve, the higher balancing cost, because when you do manual balancing, it's iterative. I throttle some valves, but that pushes the water elsewhere. So I have to go and throttle those valves, and then I got to go back to the previous one and check its balancing. A very talented balancer can do it in maybe basically 2 swings. A less talented one may have to take multiple circuits, tweaking each valve one after the other to make sure that the balancing works. I have to rebalance if I add and subtract coils. This is why you don't want to do it on a high rise. I have slightly higher pump energy because the balancing valve has a higher pressure drop than a ball valve or a butterfly valve. And then I can starve coils depending on how I control the variable speed drives. I'll talk about this on the next slide with an example. And then I have slightly higher pumping energy costs. So, yeah, here's the reason why I can get in trouble with calibrated balancing valves and manual balancing. Let's take a system down here where I have a pump. It's serving this large system. I'm only showing 2 of the coils, one that's close to the pump, one that's furthest away, and there's a whole bunch in between that I'm not showing. And so if you did a pressure profile of this system, I create the most pressure right at the pump discharge. And as I go through the piping, I start losing energy due to friction of the piping losses. And at my first coil, I have here 38 pounds of pressure drop across it available. And I keep going down the system. I end up with 12 PSI at the end. So with manual balancing, I would have the pressure drop of the last manually balancing valve just wide open. So it has 2 PSI pressure drop just perfectly wide open. So no balancing at the end of the system. But in order to get my 100 GPM across this first coil, I have to squish down on this manual balancing valve, and I have to actually create a pressure drop equal to 28 PSI instead of 2 PSI to make the thing balance, because this has 26 PSI extra pressure drop compared to the end of the system. So I've throttled the valve and to make the flow right. Okay, so that's that. Now, what happens if it's the building's only partially occupied, and in fact, the only thing that's occupied is this close coil, and all the other coils are off. So this is like my air handler on the top floor of my building, and my example building is on, serving the tenant on the top floor, but all the other tenants aren't there. So this is the attorney's office, and they're working late at night or on the weekend. And we have a hot day, they need design flow, but all the other coils are off. Well, the differential pressure is being maintained to maintain that 12 PSI. And so that's going to cause the pump to slow down. But since there's no flow in these pipes here, 12 PSI here will also occur here because there's no pressure drop from here to here. So this system only is going to see 12 PSI. But I already throttled down on my valve. It's a manual valve. So even when my control valve is wide open, it's not going to be able to get the flow we want. And in fact, we end up with only 56 GPM instead of the 100 GPM that I wanted because of this situation. Now, smart controls will simply speed up the pump. It will detect that this control valve is wide open and being starved, and so it'll speed up the pump. But you can see that, of course, will waste energy as well. Now I'm speeding up the pump against a coil that didn't have to have this manual balancing. So the disadvantage of the manual balancing valve is that it creates a pressure drop that ultimately is going to waste energy and possibly cause starving coils in this situation. All right, flow limiting valves. Again, no balancing labor in terms of having to do the manual balance. Again, you're still going to go out there to measure the differential pressure across the thing to make sure that the pressure is not too high, make sure that you have pressure at all so that you know it's working. So there's some balancing labor, but not to modulate balancing valves. The sales pitch for this system is I can add and subtract coils without rebalancing because they're self-balancing. They use their controls inside to limit the flow. Disadvantages, I now have the cost of not only the flow limiting valve, but also a strainer added to it. I have to clean that strainer after startup, so I have a labor cost added to that. I have higher pressure drop due to the strainer and the flow limiting valve creating pressure. The valves have a custom flow rate, so they must be installed in the correct location. So these valves look the same, and but they may not be the same. The springs inside them are not going to be the same, and they have custom flow rates for each fan coil. And you got to make sure that I have a whole pile of 3/4 inch valves that you look at the valve tag and you make sure you put them in the right place. And that could be a horrible problem to diagnose if they get put in the wrong place. The valves can clog over time, and the springs can fail over time. It's a long time, but they can fail over time. And then you still have this problem of overpressurizing the valves, the control valves. And you think, well, why is that? Well, remember, this valve only comes into play to maintain a maximum flow. When I'm throttling my control valve, it's because I want less than design flow. Okay, so this thing is only going to help in the case of a transient where the coil size for say 5 GPM, and when the system first turns on and a control valve maybe goes wide open, and it possibly could take 7 GPM if you didn't limit it. But this thing will say, no, you only get 5 GPM. So this valve comes into play, the spring starts springing. But once the flow goes below 5 GPM, this a flow limiting valve does nothing because I'm less than the limit, so it doesn't care. And so the control valve is going to see the entire pressure drop across the thing, just like option 1. So the controllability issue is no better than option 1. Other bad things about flow limiting valves is that they can be very unforgiving to engineers who do a bad job of selecting flow rates. So a classic example is that engineers will assume a delta T. So here's a reheat coil system where the engineer put a condensing boiler in and said, I really want this thing to condense. We're going to make the water temperature 140, comes back at 110, 30-degree delta T. I'm going to size all my reheat coils for that flow rate in there. Well, it turns out over here, what the real flow rate is for these coils is quite a bit less delta T. Leaving water temperature is not 110, it's 128, 118, et cetera. So the flow is much bigger than what this calculation faked it, right? He didn't make the selections. He didn't go to selection software and make the selections. He faked it. And so the flow required is way higher than what it was calculated. If I didn't have a flow measuring device, if I didn't balance the system, this would work okay because all the pipes are there. They're all the same size anyway, and the control valves would open up and deliver whatever flow rate was needed to make the coils happy. So not having any balancing would work pretty well. Even manual balancing would be okay because I would just go out there and open up the manual balancing valve and I'd be okay. But a flow limiting valve is what it is. It comes with the factory that way. Many are not adjustable in the field. And so I get the flow that the flow limiting valve has, and this starves the coil. Here's another example. This is a spreadsheet error. This is an underfloor system where the first coil happened to need 0.3 GPM. The engineer just dragged that 0.3 GPM all the way down. But you can see just from the size of these coils and the heating flow rates that they all needed much more flow than that. But they called for Griswold valves or the flow limiting valves in there. And if you got said 0.3, that's what you got. So both these systems were underheating spaces. How did we solve the problem? Well, in this particular case, the condensing boilers, fortunately, could go up to 190. So we just cranked up the water temperature and that made it work. Ultimately, we went back out and we took the springs out of the flow limiting valve so that they basically did nothing, so that we could get back to the condensing temperatures that they wanted in the first place. But a quick thing was just to make the water hotter. These here, we were sort of screwed. There was no easy way of fixing it other than removing the flow limiting device. So we simply removed the cartridges out of the flow limiting device, unbalanced the system, and presto, the system worked. Believe me, the building engineer did not believe me that this was going to be the solution. But I said, well, it's not working now, so you might as well just give it a try. So we removed the cartridges and it worked. We have fixed the problems on so many buildings that had flow limiting valves by simply deleting them, eliminating the cartridge inside them so that they essentially were not there. Okay, reverse return. This is where you supply the first coil and you return the last coil, so that the idea is that the circuits are all the same length. So this one's going like this, the last one goes out here and comes back. And if you look at how much pipe each one goes through, it's the same length. So this makes the pressure drop across each of the coils roughly the same. In a high-rise building built with pneumatic-controlled actuators, we used to always have to do this. In my early high-rise buildings, we always used reverse return because the pressure drop, we could push these coils open, these valves open when I had pneumatic controls. Now, electric actuators can handle very high pressure drops, so you don't have to worry about that. But that's one of the advantages of the reverse return, sort of self-balancing. So when you have a riser situation, how do you make this work? You add another riser. So in those high-rise buildings, we used to have a dedicated riser that went down to the bottom of the building, and then we fed all the individual risers back up again with 2 pipes. You end up with an extra pipe. So obviously this costs more because I have, instead of 2 pipes, I have 3 pipes, 1 dedicated return. On a floor plan, like the floor plan for the Ask.com building that we talked about earlier, you simply pipe in different directions here. So the supply goes this way, the return goes in the other direction, which is actually the same flow direction, but they come out of the shaft in 2 different directions. And again, the first supplied is the last that's returned. And so the flow length is the same through each of them. Now you'll notice in this case, the first cost is going to be roughly the same, right, as a direct return. Same pipe lengths, same pipe sizes. The only disadvantage perhaps is that I have individual hangers for each. I might have been able to use a trapeze or something, but they generally don't. So the first cost of reverse return on a floor plan is basically 0. It costs you almost nothing to get that benefit. Advantages of first return is, again, no balancing labor, self-balancing. You can add and subtract coils without rebalancing. You also gain the balance that you didn't have with option 1, is that now I have no significant overpressurization of control valves. That's very nice, and which is why we did it with pneumatic controls. We had to do it with pneumatic controls. And then we end up with lower pump head and lower pump energy. Now you think, well, how can that be? And in fact, we said the same thing when the pipe flow program came back and said it used less energy. We said, how is that possible? We got longer piping lengths. We got that whole dedicated riser. How is that possible? Well, remember that that's not where the water is going. It's going into first supplied is the last returned, but the pipe length is the same for all of them. And so we're not really adding any pipe length in terms of where the flow is going. We add another pipe, but not flow length. And it turns out that the dedicated pipe tends to have a lower friction rate than when we do direct return because of the limitations on pipe sizes as you get bigger. And so almost all the time, you end up with a lower pump head with reverse return. Disadvantage is added cost of that reverse return pipe, that other riser, but again, nothing if it's on the floor plan. And then sometimes you just can't do it. If I have a very complicated layout where I'm sending water to several buildings, it's not very practical. So in a multi-building application, it just doesn't really work. Oversized mains, this is pretty obvious. In this particular case, I'm assuming everything's in the basement going up instead of the other way around. It doesn't really matter. But in the standard design, as the flow drops off from the basement, I drop the pipe sizes all the way up. With the oversized main, I just keep them all the same. And so I end up where all the pipe sizes are the same all the way up. And this is sort of like a duct plenum. You know, it makes it so that the pressure differential is very similar across each coil because there's very little pressure drop in the main. Advantages: no balancing labor, add and subtract coils, reduced overpressurization. The lowest pump energy, those oversized headers, reduce the energy a lot. And then the last one is increased flexibility due to adding loads. So I can put the loads anywhere. So as an example, let's say that the top floor tenant had a little data center, and they said, okay, I'm going to put a data center on this floor. Can you serve it with the chilled water? And you say, no, the pipe sizes are too small. They're just sized for your HVAC loads. Can't do it. Well, if you had sized all the pipe with a big pipe like this, you could add a coil anywhere in the system you want, and you wouldn't even have to think about it anymore. Another example is if this were a campus and I was oversizing the distribution system throughout the campus, then I would have the flexibility of adding a building anywhere I wanted on the campus. I pay more for that distribution, but I add that flexibility in there. And so the only disadvantage of this is the added cost of the pipe. Everything else is a big advantage. Okay, what about undersizing the branch piping? I mentioned that this is engineering costs, so we're not going to look at it. Again, you can read about it in the paper if you want. Too much engineering cost, forget it. Let's talk about pressure independent control valves. There's two styles of this. One is called the regulator plus control valve idea, like this one is. What it is that the regulator section is like a it's like a self-powered valve that creates a constant pressure drop, typically about 5 psi. I have no idea why these little spikes are occurring. I apologize. Across the control valve, and it basically controls that all the time. And it does it through a very clever thing of measuring some pressure and these springs, and the springs go in and out, and it essentially throttles the flow to create a pressure drop that's constant all the time across the control valve. So even though I'll have 50 psi across the whole assembly, because I'm right next to the pump and creating a whole bunch of pressure, the control valve only sees 5. As the pump slows down, and this maybe drops to 30, I still only see 5. The regulator will just open up a little bit and chew up less pressure. So it's constantly making the control valve see the same pressure drop regardless of how throttled it is. Okay, so what this does is we call it perfect valve authority. As this valve starts to close and reduce flow rate, it doesn't change the pressure drop across it itself. And that makes it have incredible controllability. That's what this is all about. So here, shown schematically, this is what we have. We have this regulator. It's going to measure pressure drop across the valve. It's going to, with this spring action, it's going to modulate this valve to maintain a constant pressure drop across the control valve. The control valve can be any type of control valve you want. Typically, it's a standard ball valve or glow valve. And it can be equal percentage or whatever you want. And then this regulator section does have a limit. It will not be able to control if you get too much pressure, but the limit's very high, like 50 psi, which is over 100 feet. So it has lots of capability of maintaining a constant pressure across the valve. So this valve is good in terms of its concept. It's maintaining perfect controllability across that control valve. Another style is a flow meter style. This is almost like a VAV box. It's like, conceptually, it's exactly the same as a VAV box. We're going to measure flow, where the control device is going to tell the flow controller how much flow I want. And then the flow controller will modulate the valve to deliver that flow, exactly like a VAV box works, right? So it'll say I want 5 GPM, it'll squish down until it gets to 5 GPM. And so just like a VAV box, it has some of the advantages of that. One is it knows what the flow is. That's nice. You can use that for resetting pressures in the system. Second, it can limit flow if you wanted to, because I'm measuring flow. You could put in there that I don't want this coil to ever get above a certain flow, and it just does it through the controls. But the disadvantage of this system is that it's not regulating the pressure across this valve. So if I have 50 psi across the assembly, the flow meter has almost no pressure drop, so the valve sees 50 psi, just like it would if this were a regular option 1 control valve, just a regular one. So there's no benefit of regulation. So this is going to have the controllability limits just the same as option 1 of having no balancing at all. And so I have to size the valve with the same considerations. I have to make sure that I have enough valve authority, C sub V kind of stuff, whereas I don't when I have the other style. So the other style is much better. And a lot of manufacturers are pushing that as being equal to the regulator plus valve style, but it ain't, trust me. All right, advantage of the different styles. Regulator plus style, regulator plus valve style has the true perfect authority. Very simple to select. You just select it on the pipe size and the flow range, and you don't have to get into the C sub V stuff and pressure drop and yada yada. The flow meter plus valve style must be selected just like a regular valve. It has to have a valve authority just like a regular valve, so it'll have a higher pressure drop for that reason, and you have to have that consideration. The controllability is better than a regular pressure independent valve, option 1, because it does have that feedback with flow, and that will make it a little more stable, but it's not going to be as good as the regulator style. So this style is going to have the better flow. You need straight pipe because of the flow meter. Just like any flow meter, it has to have some straight pipe upstream of it to make it work accurately. But one nice advantage is I now have 2 independent control loops, one controlling the valve position and but I also know what the flow is. And so I can now reset water temperature and pump DP set point independently of each other. It's a little esoteric here, but when I have a pressure dependent valve, I don't know whether the valve is open saying I want more pressure, or I'm open because I want colder water. You can't tell the difference between the two. And so you end up having to use that valve position to reset one or the other, but not both. In this case here, just like VAV boxes, I have a control loop that tells me how cold the water needs to be off the coil, and I have a control loop that tells me what the valve position is and how much pressure I need, so you can reset them both independently. So that's nice, nice thing, and it's nice to know what the flow rate is. Those are all nice pieces of information, but it doesn't work as well from a controllability standpoint. So what's the advantages of option 8? Using the regulators type of valve, no balancing labor and track coils, no overpressurization, easy valve selection, perfect valve authority. Supposedly the actuators won't wear out as much because they're not always searching to find the right spot. Possibly you gain a delta T benefit of this, and I'll talk about that in a second. Disadvantages: cost of the strainer and the valves are still very expensive. But the costs are coming down, but they're still very expensive. I have a strainer, I gotta have that pressure drop, and I gotta clean it. I'm gonna have higher pressure drop because of the strainer and the valve itself. I have custom flow rates. Now remember the problem with custom flow rates on the Griswold valve problem, and possibly getting them mixed up with each other. That's the same here. I gotta put it in the right place. However, pipe fitters are all used to control valves being custom to the coil. So they're going to look for that tag on the valve and make sure that they put the right valve in the right space. So it's much less of a problem because the pipe fitters are already used to control valves being custom to the coils. They're not necessarily used to the balancing valve being custom to the coil. And then maybe what's going to clog, and maybe there's going to be springs failing over time. They haven't been around long enough to know whether this is a real issue or not. Are the springs going to fail over time? Perhaps, but maybe that's long enough in the future that we're going to remodel before then anyway. So what about the improved delta T argument? One of the valve manufacturers, Belimo, did a study at the Energy Center at Iowa State. They started publishing this particular curve here, where the delta T is over here on the left, time on the bottom. They looked at a globe valve in one air handler and a pressure independent control valve in the other, and you'll see that the delta T was routinely higher for the PICV than it was for the globe valve. And then over here, we're having fluctuation problems with the globe valve, and you can see the average delta T, if you sort of imagine the average of this blue line in here, was also better. Well, it turns out that this report was actually quite biased. And fortunately, I know the researcher who did the research, and he gave me the skinny on it. It turns out that there's a difference between the two air handlers, air handler B and air handler A. They weren't identical, And so the fact that the delta T was higher on B was because of the air handler, not the coil. And when they did the test, they reversed these two, put the PICV down here and the globe valve up here, and ended up with exactly the same delta T issues. In other words, it had nothing to do with the valve. It was the air handler that did it. On the throttling issue, it's true that when you oscillate, your delta T is going to average lower than if you precisely control the flow. However, this was because we had really low loads and they used a globe valve, not a ball valve. The PICZ is a ball valve. So had they used a ball valve in here, which has lower rangeability than a globe valve, it's quite possible we wouldn't have seen any of this. And because it only happened at low load, it really didn't affect energy use at all. So conclusion in the report, this is the actual report from the Iowa State Energy Center. PICV produced slightly higher temperature rises across cooling coils at low load conditions. Any pump energy savings resulting from the improved control performance was not distinguishable. So yeah, it can theoretically improve delta T, but if the control is decent, then it won't. So here's another example. We took a coil program and said, okay, what would the flow be if I have stable control? I'm maintaining 65 GPM, I'm getting 52 degrees off the coil. What happens if the coil was not being controlled well and was fluctuating? So I reselected the coil, assuming I'm fluctuating between 48 and 56 half the time each. So the average between 48 and 56 is 52. So I'm maintaining the same 52 on average, but it's going down to 48 where the flow went all the way up to 150, and it goes up to 56 where the flow drops to 28. The average of those fluctuating coils is 90 GPM if they each happen half the time, whereas I only really needed 65. So this corroborates the argument that because coils are nonlinear, I will need more flow if I have erratic control versus stable control. So if I have pressure inhibiting control valves in locations where I had a really high pressure drop that would cause erratic control, it in fact can save some pump energy and reduce delta T or increase delta T. All right, so I'm running a little late here. Sorry about that for my first break. Let me finish though the balancing. Oh, no, let's not. Let's take a break. I'm a little late, but I'll come back to this section in the middle. Let me go forward to the break thing so it's clear we're on break. There we go. All right, so I'll go back and to those summary pages in a minute. So let's take a break for just 5 minutes, since we're all at home, presumably, or at the office, to water ourselves and everything. So we'll come back at 11:08. So I'll mark on here 11:08. Okay, we are back. Let me go back a few slides and just talk about some of these issues with transients and things. So we did our analysis with the pipe flow model. We looked at what's the maximum pressure drop across the control valve as it squished the flow down to be self-balancing. So here the control valve is doing the throttling, and what is the pressure drop across the one that was the highest, the one closest to the pump? How far did it have to squish down just to get to design flow? And this is an indicator then of controllability. So you can see with the no balancing option and the flow limiting valve option, because it doesn't do anything when you're below design flow, all had fairly high pressure drops across it. Theoretically, manual balancing didn't have any problem because we would chew up that 44 feet with the manual balancing valve. Now, how high of a pressure drop is too high? We don't really know that. It hasn't been determined experimentally. So we sort of figured that 40 or 50 feet is a lot, but it's not too much. We've got that building is actually working, the Ask.com building, and it has direct return and no balancing now, and so all the balancing valves were open, and so this is probably okay. But if you start getting above, maybe 50 feet of pressure drop across this, then you start having some serious problems, we think. Now, what about, so look for low numbers in here. You can see that reverse return was good, oversized domain was good. We're not going to consider the balance, the undersized this and undersized that options. But the ones that, that were the worst of the available ones here were option 1 and option 3. So option 3, the automatic flow limiting valves, didn't do anything. But what it does do is make sure that you don't have any transient problems by making all the valves only get 100% of design flow at design conditions. But what about transients when I'm option 1? Well, this is where I'm talking about where flow and load don't match each other. So here's the maximum flow closest to the coil. The maximum flow was double the design flow on hot water, 43% higher on chilled water, but the coil capacity was only at 106%, 119%. This was made with coil selection programs. So the coil load, they're very nonlinear. So double the flow, but only 20% increase in capacity. Same with the ones that were being starved at the end of the system. It had 73% of the flow, but 90% of the load. Hot water is even more less sensitive to flow, 75% of the load and 96% of the capacity. So what this means is on a warm-up situation is that transient load is not a problem. I'm not going to have any issue where this one's going to warm up 2 hours later than this one or whatever. It'll be minutes later, if at all later. Nowadays, by the way, we're using guideline 36 logic. We're controlling the flow and hot water coils to a supply air temperature, not to the thermostat. So there actually isn't any transient anymore because everything's being controlled to their own leaving temperatures. So even this is not an issue, and it wasn't an issue to begin with, controlling off the thermostat, but it's not an issue at all. So the whole idea that I want flow limiting valves to limit flow because of transients is BS. You don't need it at all. So what about first cost and energy costs? We calculated the pump heads. You can see them here, and we calculated the energy costs. You can see once again that the energy cost difference. This is a big building, and the difference between one and another is nothing. It's hundreds of dollars. Just really not even worth considering between the two. So the energy cost difference between all of these things is all small and slight. Even though the pump heads are different. Now, maybe you had to have a bigger pump motor or something like that for the automatic flow limiting valves compared to nothing. But the overall energy just doesn't make that much difference. We also looked at first costs between them, with the baseline being no balancing. So option 1 was the base case. Everything is, this is the dollars above that. And you can see that flow limiting valves was quite a bit more than the baseline. It was the most expensive option for hot water compared to all of them. So you're sort of seeing a trend here. The automatic flow limiting valves had almost no benefit, only the transient benefit, which didn't matter. They cost more. They have higher pressure drop. They there's just no benefit to them. They don't do anything for you. So there's no controllability benefits. There's no nothing in them. So we subjectively sort of ranked everything here with adding the pressure independent valves just subjectively. And it has the highest first cost because the valve is very high, but it has tied for, or I mean, excuse me, has the best controllability issues, but unfortunately it has the highest first cost, which is too bad. And then our conclusions and recommendations are, one is that flow limiting valves shouldn't be used on any variable flow system. They don't do anything. But having said that, if I have a semi-constant flow system like a auxiliary condenser water system that you might find in a high-rise serving heat pumps or water-cooled AC units on each floor, those are semi-variable flow. They have valves, by code, they have valves in them that stop the flow when the compressor goes off. But when the the compressor's on, the valves just open and there's no feedback loop on them. So they're not self-balancing like a chilled water coil is. And so there, having a flow limiting valve makes a lot of sense because it will limit the flow to keep the system so you don't take any more flow than you want on the condenser water side. So condenser water and chill water are not the same thing. And so flow limiting valves on a condenser water system is a good idea. That's what we always do. But it makes no sense on hot water or chill water when we have closed loops and modulating valves. So calibrated balancing valves are also not recommended for balancing. They're useful for diagnostics, but make sure you just leave them open or just add the extra pressure drop. And hard to write. Add the extra test plug. Add the Pete's plug at the valve and use it for measuring flow. So you don't even need this option. So don't even do this. Just add the extra flow. So don't bother with calibrating balancing valves anywhere. Oversizing the mains, it has a good payback on 24/7 systems. So if you have a data center, a central plant serving a campus, then it actually can be cost effective to oversize the mains. And it also has that big benefit of being very flexible, that I can add loads anywhere. Now, when we do data centers, we always oversize the mains, right? We put a big loop around the data center so you can add coils anywhere or do other things. Same with campuses. Nice to have big oversized pipes so you can add buildings anywhere. Campuses never follow their master plans, so it's always nice to have that flexibility. Reverse return, you'll use that when it's free, like floor loops, but not worth it. Otherwise, it costs too much. Undersizing the piping and the valves does reduce cost, it does improve balance, but it adds a lot of engineering time, and most people are not going to do it. The pressure independent control valves. We consider them on systems that have very high pump heads, like 90 feet or so, for the coils near the pumps. You don't have to use the same solution everywhere. So you can have all the coils that are next to the pumps have pressure independent control valves and regular control valves for those downstream. The cost is still high for these valves, particularly large ones. The small ones are actually getting to the point where they're not that big of a deal. Small ones meaning 1/2 inch and 3/4 inch. And so if I have a small chill water system that serving like fan coils serving a hotel or something, it's really not that big of a premium. Maybe hot water too. It's not that big of a premium. And when costs are competitive, our feeling is that one of these days we're just all going to use pressure independent valves because it's just so easy to use, and they definitely will work better. But right now we're shy against it because of the premium and cost. But maybe that'll go away in the not too distant future. So keep your eye on pricing on these things, and that will have an impact. So for everything else, except for the considerations above, our feeling is that no balancing is the best option. And this is what we do on almost all of our buildings. So our bigger buildings will use option 1, except we'll put some pressure independent valves around the pumps that are closest to the coils when the pump head is high. Here's basically a summary that says exactly the same thing, so I won't repeat it. It's just a little bit easier to read than all those bullets. So any questions on balancing variable flow systems before I move on? Okay. All right, so now we're going to talk about degrading delta T. And this is a phenomenon that happens in almost all plants. A lot of it can be helped, but in some ways it can't be, and that's what we'll talk about. So first of all, here's our fundamental equation. Q on the left is BTUs per hour is 500. That's basically the density times the heat capacity and times and the getting units right with hours in there for times the GPM times delta T. So if you want to know that, like with hot water, it's 490 instead of 500 for 180 degree water because the heat capacity is different or density is different. So here's our final equation. So what happens if the delta T goes down? Well, if delta T goes down, then the GPM goes up. So having delta T go down from what we design it to be is going to make pump energy go up. There's no question about that. And so in addition to that, it might cause us to run more chillers than we have to. So this same kind of issue is when we put three-way valves in. They screw up the delta T. They make it so that flow and load don't match, and I may end up having to put in to run more chillers than I want to. So that's the big downside. Possibly I could starve the entire plant if the delta T is down, even on design conditions. Then that may be a problem where I actually starve coils. That usually doesn't happen. What we'll see as we talk about this is that the delta T tends to go down when the weather is mild. When the weather is more extreme, when you need that capacity, it tends to go back up again. So it usually is not a problem unless you have some serious design issues where you actually starve the plant itself. So a resource for this is a paper we wrote way back when in 2002 about degrading delta T, and it covers all this stuff in more detail than I'm going to cover now. So what about this staging issue? You know, what's the problem? Well, here's a primary secondary system. Let's say that I'm at 80% load on one chiller, and I'm cruising along, I'm delivering 42-degree water, and the primary flow exceeds the secondary flow. This chiller's off, and so the water's coming back at 60. It's going to blend right in here, and then it's going to mix and go into the chiller, and that's what the load is on the chiller. Now, what happens if the water starts going backwards? If my primary flow is less than my secondary flow, the water goes the wrong way in the common leg. Now I'm blending water with the 42, and it goes out at a warmer temperature. When it goes out at a warmer temperature, the coil needs more water to meet the load. Makes sense, right? You can do so much at 42. If I'm blending it down, I'm going to need more water. And when it needs more water, the coil works worse, and it has a worse delta T. So the water comes back warmer, and when it comes back warmer, it makes this whole thing get worse. And we call it the death spiral, because if you don't do anything about it, pretty soon the load on this chiller actually starts going down, as you can see here, because the water coming back is less, and the whole plant is cruising, but all the coils are being starved. They're all saying, I need cold water, I need cold water, and the plant's going, no, we're fine. If you're staging by load, it'll say, I don't need another chiller, I'm fine. I'm not even, this chiller is only doing 70%. What are you talking about? And it gets even less and less load, but we're starving all the coils. So what has to happen here is you have to make the primary flow exceed the secondary flow, and that means you have to turn on another chiller. So you got to turn on the second chiller to make it go the right direction. Here's an example of a real building where we had tremendous delta T degradation. This is a chill water plant in San Jose. It was stupidly designed for 10-degree delta T at the beginning. We'll talk about what you should really design these things to. But they never even got to 10 degrees except for some of the hottest weather conditions. Most of the year, they're around half of that, right? 4 or 5 degrees delta T, you can see here. So they had some serious delta T problems on this plant. So what was going on? So we had to investigate why was the plant just not maintaining, and we were running tons of chillers to keep the flow up because they couldn't handle the flow at that low delta T. All right, so what we discovered was then that you had degrading delta T could be broken down into 3 categories. One is the ones that could be avoided by proper design and operation. So these are the things that we can do by just being smart and doing it right. And then there's a solution that can mitigate the problem. However, it ends up costing more energy. And if the whole point of degrading delta T is the energy impact of higher pump energy and staging chillers non-optimally, then we certainly don't want to find a solution that makes the energy go up. The whole point was to make the energy go down. So in other words, degrading delta T doesn't have an inherent bad evil to it. Its evil is that it makes energy go up. So solving it with a problem, with a solution that makes energy go up more doesn't make any sense. And then there's causes that are inevitable and you simply can't avoid them. So let's discuss each one of them. So here's causes that it can be eliminated by design or operation. One is improper set points or calibration. So for instance, dropping a coil set point by 2 degrees, say some like 55 to say 53, that can double the flow rate or have the delta T. And so so that can be an issue. A lot of times building engineers, if there's a cooling complaint, they'll just crank down the supply temperature. That causes problems. Use of three-way valves is obviously a problem. It's deliberately bypassing cold water so to the other side. So you don't want to use any three-way valves in a system in general. So in variable flow systems, in general, don't use any three-way valves. If you need mass in the system, if you want to engage mass, put a tank, a buffer tank at the system, and don't use three-way valves. Now, we in hot water systems, a lot of these discussions have the same validity on hot water as they do chill water. We often have, and still do occasionally, put three-way valves at the end of each riser to get a little flow through each of the risers to gauge the mass so the boilers don't cycle. But we've learned a lot about piping losses since then, and piping hot water losses are really significant. And so a better way to do it is to not use any three-way valves and instead use a buffer tank to provide that thermal mass at the boiler plant itself. So don't use any three-way valves anywhere ever. No control valve interlock. This was a case where this plant was serving a lot of process loads, and the process loads weren't always on, but the flow always went through the load anyway. They also had some pneumatically operated control valves, and again, when with GDC, it's really easy when you say if fan is off, close valve. But with pneumatic controls, if the fan went off, you would have to electrically interlock them so that when the fan went off, you push the valve to be closed. And it takes a little money to do that, so it wasn't always done. Coils pipe backwards. Amazingly, this is at the PG&E Energy Center where we usually give this presentation live. One of the air handlers there was found to have been piped backwards because a sticker put on the in and out on the coil was from the factory was wrong. So the pipe fitter did it according to the sticker, but the sticker was on the wrong thing. And coil parallel flow can't achieve the capacity of counterflow, but just as bad, it ends up with horrible delta T. Poorly circuited coils, I'll talk about that in the next slide, is too many feeds, and then more later. So this next slides here are circuiting. Circuiting is very confusing because there's lots of words used that different people call them serpentining and circuiting and feeds and circuits and passes and all these words, and they don't always, they're not clear as to what they mean. With chill water coils, it's quite easy. Always fully circuit them, which means that the passes equals the rows. The coil on the right over here is a full circuit coil where there's a header. I put the water, in here, and it comes out here. I'm putting it in all the coils. It goes through counterflow, and it comes out all of the tubes at the same time. So this is called full circuiting over here. This is half circuiting here, where we're putting in only half the coils. It goes through some other coils, comes back over, goes through all the other ones, and comes back out. This one is spaghetti. Who knows what the hell that is? This one is one circuit, right? The water comes in once and comes out once here. And for a hot water coil, this is the way you want to go. One circuit, get the biggest delta T you possibly can out of this thing. It has a higher pressure drop, but who cares what the pressure drop is on hot water, because pump energy is just electric heat, so it doesn't matter. On chill water, this would not be good because you'd need more rows, like 6 or 8 rows, and the pressure drop would be way too high. So again, as a rule of thumb, is pick the fully circuited coils, rows equals passes, or passes equals rows for chill water coils like this one on the right. And then you could possibly do it half circuited as well, but you have to check the pressure drop to make sure that it's going to work for you energy wise, all in all. So ironically, hot water coils are the manufacturers deliberately screw these up by doing things like this, by not by putting in more passes, more and more feeds in them to make the delta T worse. They do this because engineers, dumb engineers like us, sometimes say, oh, I want a 20-degree delta T on that coil when it naturally would be 40 degrees. You say, oh, well, I have to screw up the coil then. I'll just put in more feeds. Then this would be with hot water, this coil here could have a 60-degree delta T on a reheat coil. But if you want it to be 20, you got to screw it up like this. So sometimes it's the engineer demanding stupid stuff. Here again is what the Rose circuit, some of the terms, Rose passes circuits. I'll let you just read this at your leisure. But this one over here is again, one of these fully circuited coils. By the way, we're finding as we're doing some experiments, piping the coil from the bottom and coming out the top is what everybody says you have to do because of air getting trapped inside. So far, we can find no evidence that there's actually any validity to that. So piping it from bottom in the top and out the bottom it doesn't appear to be a problem. But what is an issue is you want to be counterflow. So you can see here that the air comes in from the left, the water comes in from the right. So you always want it to be counterflow. Automatic slide thing here. Ignore that picture on the bottom for a minute here. So continued. Other things that control delta T by design. Uncontrolled process loads, I mentioned those before. You need isolation valves that shut them off when the process is turned off. Incorrectly control valves, if they result in hunting because of high loads. Remember, nonlinear coils, if you're hunting, the average delta T will be higher. Undersized actuators, if that could get pushed open. That's like those pneumatic actuators I spoke of. Incorrectly selected coils. This is a problem on campuses because some engineers don't find out what the campus central plant was sized for. So almost all the CSU and UC campuses have a central plant, and they often have thermal energy storage. The bigger the delta T, the more storage that tank can hold. And so you want big delta T. So they'll have a campus standard that say design all coils for either something prescriptive like 8 rows, 10 fins, or something related to delta T, like all coils have at least a 20-degree delta T, something like that. And dumb engineers will come in there and say, oh, I always size my coils for a 12-degree delta T. They put in a 4-row coil and it screws up the whole campus. It's unbelievable how many times we have seen that happen. Improper bridge connections, and that's what this little picture is supposed to show. Sometimes people will set the set point of the bridge connection basically to the same temperature of what's being provided from the plant, and of course it can't achieve that, and so it ends up going wide open and just wasting energy. The other is that they'll try to control the pump or the valve not from the supply but from the return, and try to make it have a delta T. Like, I'm not going to let you send water back until it comes back at 60. And of course that it doesn't work. The nature of coils are the warmer water you send them, the more water they want. You get into that death spiral situation. So trying to force it into a delta T, physics says you can't do that. It doesn't work. So anyway, we already told you get rid of these things. So the way to solve this one is just cut a valve in there and close it. And so the pumps are now in series. That'll mean putting variable speed drives on everything, but you should have that anyway. Okay, what about measure 2 here? Ones that improve delta T, but with an energy trade-off. So the first is lowering chill water temperature. If I lower the chill water temperature by 1 degree, I increase the delta T by as much as 2 degrees. So that's good. So I lower it 1 degree, delta T increases 2 degrees, but the chiller energy goes up. So the net effect is that I could lower the pump energy, but I'll end up with a higher chiller energy. And don't forget, the chiller uses 10 times as much energy as the pump. So unless I have very high head pumps, like in a campus that really has like 200 feet ahead or something, I don't want to do this. Chiller energy is going to be higher. So in general, don't lower the pump energy just to make the delta T better. A second option that turns out to be an old wives' tale is putting pumps at coils to avoid the dreaded laminar flow effect. Laminar flow is, if you remember your heat transfer, there's like 3 stages of flow. There's fully developed turbulent flow at one end at higher velocities. There's laminar flow at lower velocities. In between is in between. Laminar flow is when the flow is so low that the turbulence, the heat transfer film coefficient, basically starts going away, and it starts becoming less conductive as compared to turbulent. And so theoretically, you can get into a laminar flow situation where the flow through the coil is so low that the heat transfer just doesn't work as well. So the idea was put a pump on it and keep the velocity up through the coil all the way, and that this would actually save energy. But remember that the pump that you put on that coil also uses energy. And remember, the whole idea here is to save energy. So we analyzed this even back in 2002 when we wrote this paper the first time. The coil manufacturers were starting to put out selection programs that would go beyond the laminar flow region. So usually when you select a coil and it goes into laminar flow, it says, sorry, can't select in this region. But now it's possible to select into the laminar flow region. And what we found is that for a few different coils here, is that the delta T actually gets better at part load. And this is just pure physics, right? I have the same physical size of the coil, but less flow going through it. So it looks bigger to the flow. Then I start getting into the mixed flow region, and my heat transfer coefficient starts going down. And then once I hit laminar flow, it can't go down anymore. And so now it goes back up again for the same reason that it went up over here. I have effectively an oversized coil. And what we found is that basically in this case here, that the delta T was 13.5 or something like this in this example. It never got below about 13, even in laminar flow. And so it just wasn't an issue. This coil here, which was the fed by multiple tubes one, did worse. And another reason why we want to not do that, the dual row one here, that means we fed it twice. This is where we fed it not just counterflow, but also in the middle. So it was an 8-row coil. We fed it the 8th row, and we fed the 4th row as well. So you don't want to do that. You know, that's bad. That's wrecking the coil. And then, of course, the ASHRAE standard 410 came out in 2001, where it now made coil manufacturers also rate the coils in laminar flow and publish the data. And so they showed that just like I showed you, there was a little drop off in capacity when we get into the mixed region. Right when we hit laminar flow, that goes away because you can't get any worse than laminar flow, and there just isn't a big disruption. There's no drop off in laminar flow. So the whole idea that coils can't go into laminar flow or they drop off is total garbage. We also looked at, okay, well, what if the coils did help you? What happens if we able to maintain a constant delta T versus a degrading delta T if I put a tertiary pump or a coil pump on every coil? And we found, of course, that the energy use was worse because of the energy use of all those pumps. So it makes no sense to use coil pumps. You don't save energy by using energy. Conclusion, even if the flow problem were real, which it's not, coil pumps are not a good solution. They add to both first cost and energy costs. Okay, let's move on to the third cost, which is degrading delta T that really can't be eliminated. This happens when you have air economizers and 100% outside air systems. So what we found in this campus down in San Jose was it had a lot of process stuff. It was serving not just office buildings, but also some process loads. And can you guys still hear me? I just whapped my headphone and I want to make sure I didn't turn something off. Somebody go off mute and tell me, you can hear me?
Yep.
Okay, good. What happens if this campus had a whole bunch of buildings that had 100% outside air? And of course, what we found was that the delta T would go down in mild weather. Now, why is that? Well, here's a coil with counterflow situation. The water comes in 42, leaves at 64. The air comes in at 78 if it's a normal economizer kind of operation, with minimum outside air, it leaves at 55. You'll notice that with counterflow, that the water can come out at a warmer temperature than the air comes out, right? Because it's seeing warmer air. That's how counterflow works. So I got a nice delta T here. I got 24-degree delta T between here and here. Now what happens when it's 60 outside? I got 60 air coming in here. Well, the water cannot come out at 64 because it physically can't be warmer than the air. It's going to come up with a similar kind of approach temperature. So the best it can do is maybe 55. So my 24-degree delta T at design conditions is now a 13-degree delta T when it's cool outside. So this happens because of economizers operating with 100% outside air, but still needing a little cooling. And it happens when you have 100% outside air systems as well. This cannot be helped. This is pure physics. It'll happen, whatever. Another effect is coil effectiveness degrading over time with age. By age, we mean dirt. So the dirt on the water side is almost non-existent because it's a closed system. So don't worry about that unless you somehow are using open circuit water. But on the air side, of course, it will accumulate. And so you got to clean the coils every once in a while. Go in there and blast them with steam cleaners and other things to get the dirt off them, and that can restore their performance. Over time, you might end up where fins start degrading or whatever, but that takes a long time for that to happen. But still definitely an issue. And then lastly, I put this undetermined issue. We've been into some plants that have had issues. We've looked at every single coil, trying to see why some are underperforming. And occasionally we just come up with an issue and say, you know what? I don't know. I don't know what's going on here, but we're just seeing a low delta T, but we can't figure out why. That's a very small percentage of the cases. However, most of the time we find other issues like all the stuff we've identified before. Largely undersized coils in the first place, 4-row coils that should have been 8-row coils. All right, conclusions. Design, construction, and operation errors that cause low delta T can and should be avoided. But other causes can never be eliminated, like mild weather and economizers and 100% outside air and dirt and et cetera. And so therefore, some delta T is inevitable. And so we need to design the plant to be efficient, even if there is degrading delta T. So how do we do that? The first is that we can use variable speed drives. So remember, part of the problem here is if the delta T goes down, we can't help the pump energy go up. That's just going to happen. But we can make it so that the staging of chillers is not a problem. So how do we do that? First is to use variable speed drives. So on the chillers, as I'll point out when we get to this afternoon, that variable speed drives make it so that chillers are more efficient at part load. So turning them on early is exactly what you want to do. So even if the low delta T and the high flow didn't cause you to turn on a chiller, you would have turned on the chiller anyway. And so it just isn't an issue. There's other things you can do to mitigate the problem. One is to use primary only pumping. That means that we don't have primary secondary anymore. We don't have to worry about that degrading delta T death spiral that you have with primary secondary. But extreme delta T won't work with this either, because you're trying to shove a whole bunch of water through the chiller. So there's limited benefit on having this work. Still, primary only does avoid the death spiral. I can do primary secondary with a lower delta T in the primary loop, so I have more flow in it. But the problem with that, of course, now I guarantee myself to have higher first cost and energy cost in the primary loop. So that's not a very good solution. So don't do this. And then primary secondary with a check valve in the common leg. Oh, check valve in the common leg. What's that? Well, check valve in the common leg is to make sure that the water only goes to the left here. So this little arrow here will, I don't know why that keeps happening. The left arrow, the right arrow is not going to happen. The primary always have to be bigger than the secondary. If we start getting this death spiral and the secondary pumps start speeding up and the coils start opening up here to increasing flow in the secondary, this valve will set and it'll basically be like a closed valve. It's like this common leg is not even there. So it puts the primary pumps and the secondary pumps in series with one another. And now we have the ability of these primary pumps to help suck water out of the secondary system. It's essentially a primary only system at this point. And now the pumps are in series with each other. And that helps us get more flow through these chillers, and therefore we can stage them in a more normal manner. So what's the disadvantage of a check valve in the common leg? Some people say, oh, you can't do that. The whole idea of primary and secondary is that we have hydraulically independent circuits. Well, there's no inherent benefit to that. The whole purpose was to make it so that we didn't have low flow on the chillers. Well, by definition, in this case, we don't have low lows on the chillers. We have high flow on the chillers. That's our problem. So there's nothing inherently wrong with the check valve in there. So don't worry about that part. People are concerned about the flow rate exceeding the maximum allowed by the manufacturer. Seldom a real problem because the pump capability is going to fall off. We're going to try to, the pump pressure drop goes as the square of the flow. We can't shove that much water through the chillers. Maximum flow rates are largely arbitrary anyway. And we're also going to be telling you to design for high delta T's in this class. We'll get down there. And when we get to high delta T's, that you got a long way to go to get to the maximum flow rate in there. So you'd have to have horrible delta T degradation to even get there. So if, as a last resort, you might put flow limiting valves on the chillers to prevent them from over pumping, but it really isn't a concern. The pumps in series may force control valves to open, and that's not true when we have variable speed drives, because if these primary pumps start pushing water through the secondary system will just slow down. The primary pumps may ride out their pump curves and overload, and that's seldom a real problem as well. So a lot of possible problems, but no real problems. Here's a couple of real problems. One is I can deadhead the secondary pumps if the primary pumps are off and the chill water isolation valves are closed. So if I have a situation where I've turned off the secondary pumps and the primary pumps are on, and I have the check valve can keep the water from flowing through the secondary system. I'm sorry, the primary pumps are off. So you can see here, right here, the check valve won't allow the secondary pumps to run by themselves. Okay, so the solution to that is just don't run the secondary pumps unless the primary pumps are working. That's pretty easy. The second is if I have dedicated pumps, like shown in this diagram here, I can get ghost flows. So what will happen is that when this check valve seats, and now it's essentially the pumps are in series, it's like this secondary line or this common leg isn't even here, I can start pushing water through the chillers. That's what I want it to do, through the operating chiller. But I can also push it through a non-operating chiller. It basically pushes water through the inactive pump, pushes the check valve open, and now I have a small flow, a ghost flow we call it, through the chiller that's off, and that's a problem. Solution to that is don't use dedicated pumps. Use the headered pumps with isolation valves, and then you won't have that problem. So conclusions on the check valve issue is that for fixed speed chillers, go ahead and do it, and just make sure that you've got the pump interlocks and whatever to make it work. For variable speed chillers, don't bother. We're going to start the chillers early anyway, and so it simply is not an issue. Now, since most of our chillers these days are variable speed, the check valve question is just sort of not there anymore. If you had older chillers on an older job and a retrofit, then it may make sense to put them in. Okay, moving on to condenser water systems. Hold on one second. Okay, condenser water systems. So let's talk about them. They have the basic same options that we had, headering versus dedicated pumps as the chill water. Many of the considerations are the same as well. We have the control complexity issue where the controllers here can start the pumps themselves. We can have the custom pump heads just like with chill water, usually less expensive. And as long as we don't have the need for head pressure control or a water side economizer. What does that mean? Well, that's what comes up over here. Headered options advantages are better redundancy, just like chill water. But we also have some advantages that didn't come into play in chilled water. One is that the valves can double as head pressure control. So these valves don't need to be two position, they can be modulating. And what that means is if when you head pressure control is something that is an issue on some chillers and not on others. It's not an issue on pumps, chillers that don't have oil. So if you have magnetic bearing chillers or ceramic bearing chillers, they don't have oil, so they don't need head pressure control. On centrifugal chillers that have oil or screw chillers, they do need head pressure control, particularly screw chillers. I'm not sure exactly why that's particularly true with screw chillers, but they do. So even if you're only operating the chiller in warm weather, when that you have air economizers in your building, and let's say the chiller comes on when it's 60 outside, the water in the cooling tower can be cold, right? Because you were just on full economizer, no chilling was required. The water in the cooling tower can be 55 degrees or so, just sitting there. And when you first turn on the system, that 55-degree water goes right into a chiller. Can it handle that water? And most centrifugal chillers can handle it for a little while, but screw chillers in general can't. And so solution is we just make this a modulating valve, and when you have to limit the head, the leaving water temperature coming out of the chiller, you modulate the valve. So this gets controlled either by the chiller controller itself saying I need head pressure control, or through the energy management system. So that's a real advantage of this style, particularly when you have a water side economizer. So water side economizer, which we'll talk about in a minute, is much easier to integrate into a system with header pumps. Another advantage, the other advantage, of course, is the standby pump. And then it is possible to run fewer condenser water pumps than chillers. Sometimes it makes sense to do that, but not very often. So that's not a big important deal. So we have some big deals here, though. Besides the better redundancy and the optional standby pump, we have the head pressure capability, which is very nice. So by the way, almost except for data centers where we have that, we like to group chillers, pumps, and towers all into one controller. We always use this headered approach. So this is like 99% of the time we're using the headered option. So cooling towers, how about piping them? 3 options on them. One is to buy the cooling towers with dams or nozzles that will allow you to have low flow. So if I had 3 cooling towers like this, but I'm only running 1 chiller, I run 1 condenser water pump, I need to have the towers have the ability to go down to 1/3 flow each, right? So I'm running 1 pump. It'll write out its pump curve a little, so a little more than 1/3 of the flow. But basically, I want flow to go through all 3 towers and have that work. And this is a really good thing to do, not only because I don't have to buy any of these isolation valves, but it's much more energy efficient. Now, why is that? If you do the math on this, if I have 1 cooling tower running, let's say the towers can't handle but anything but design flow. So I put these valves in and I shut off, I'm at one chiller, 1 condenser water pump, and 1 cooling tower. So I have this one running, say, at full speed, and the other 2 are off. If I have this arrangement up here where all of them get flow, they would all be running at 1/3 speed to get the same CFM. That uses 1/9 of the energy of running 1 tower at full speed and the other 2 off. With 2 cooling towers, it's 1/4, okay, it's the square. So clearly, it's way more energy efficient to run as many cooling towers as you possibly can with whatever flow rate. So they're flow limited, not load limited. You don't want to stage cooling towers on load. You stage them on minimum flow. And so in this case here, if I was able to get 1/3 flow through each of these towers by using these dams and nozzles that the manufacturer installs, then I can have 1 pump serve all 3 of these. This is always the most efficient and always the least expensive in there. And it's always possible with 2 cooling towers because Title 24 mandates that it be possible. And it's usually possible with 3, depending on the kind of cooling tower you select, and we'll get into that in a minute, or actually this afternoon. Um, and so this is the best option. This is what you want to do. Now, if you got more cooling towers, or you have just situations where this does not work, then you have to decide between 2 options. One is to only put the control valves on the supply, and then use the equalizer to allow flow to equalize. So you suck out of all 3, but you only supply the 1. So what happens is I have all the flow going in here, and then the equalizer, this starts filling up, and the equalizer, the difference in elevation of the basin, pushes the water into the other ones so that they can suck out of all 3. So this means oversizing the equalizer so that the head difference between the overflow here and whatever water makes the water come into these cooling towers is that difference, which is only a few inches, works. So this takes some careful sizing of there. Then the last one is the easiest to design, is just put valves on both supply and return, being careful how you sequence these as well. So in our jobs, about I don't know why it keeps doing that. About 90% of our jobs are going to be done this way. It's only ones where we have more than 3 cooling towers that we have a problem. Then we use this approach because we trust ourselves to size the equalizer correctly. We actually use the spreadsheet I talked about for sizing pumps to do that. And then we never do this because we're gutsy. But some people don't want to take the chance on sizing the equalizer wrong and having to retrofit these valves at the end. Understandable, but that's not a problem. Okay, what about piping them? There was an article in the journal one time talking about using reverse return for cooling towers and chillers. Reverse return, remember, is what we looked at when we wanted to equalize the pressure drop across control valves in a variable flow system. A chill water plant and a condensed water plant is not a variable flow system per se. It's not using modulating control valves to maintain flow and controllability, whatever. It's a staged flow plant at best. So reverse return makes no sense at all. You can balance the system just manually if you feel like you need to balance it at all. So here's the example that they gave where they did reverse return, feeding the cooling tower, supplying the first, came out and returning the last, so that the towers were balanced. And then they did the same thing with the chillers so that they were balanced. And in fact, none of this had to be done. Cooling towers are fairly insensitive to flow. So we never balance them in our jobs, because if you can use a coil selection program to prove this to yourself. But if one of them was plus 20% flow, and the second, if you had 2 cooling towers, one was plus 20%, the other was minus 20%, you would end up with almost the exact same leaving water temperature from the combination of the 2. So balancing flow is really just not necessary on a cooling tower. And it's barely necessary on the chillers as well. However, it's easy done. You just manually do it with the butterfly valve that's coming out of the plant, and you just can modulate it so that they're proportionally balanced. They all have the same pressure drop across them when all the pumps are on. So it's real easy. You don't need to do reverse return, complete waste. Now, one thing you can do even better is to header the system so that you never see a big pipe, that you always have. All the pipes here are 10-inch, you can see, right? Over here, we have 14-inch pipes and probably some other pipe sizes in here, like 12-inch in here. So it goes like, 14, 12, 10, 14, 12, 10. Over here, they're all 10, because we made it so that the header was such that no common pipe sees all the flow. If you can imagine, like, this pump's on and this pump's on, well, then 2 chillers are on too. So flow goes this way, or it goes this way, or it goes this way. If you just go through the scenarios on here, you can see that we never have to make a big pipe, because the water flow never goes through a common pipe. So when you design the system, it's physically laid out just like it's drawn here, where everything's aligned with each other. It's a row of chillers and pumps and cooling towers, all aligned this way. You save a lot of money doing this, hundreds of thousands of dollars on a big plant. Here's a clever idea. I got this one from a plant I designed in Washington, D.C., the Census Bureau building, where it's cold and they have winters there. We don't have that much in here, but the local supplier said, hey, a way you can save some money by not having to run makeup water to each of the cooling tower cells was to put a standpipe in the equalizer, measure the level of the water in the standpipe, which is the average water level of the cooling towers, and then control the makeup water with a valve that was back in the plant and didn't have to go outside. So that's what we did. So we put a level sensor in the equalizer. We have a slow closing makeup water valve that we're controlling by the DDC system in the condenser water piping inside the building. So we don't have any makeup water going outside that requires, in that climate, you would require heat tape and insulation as well. So it saves you all that cost. And it just saves you cost in general. It's cheaper than running pipe out to each of the cells. And it also eliminates this little float valve. This is the same kind of thing you have in your toilet. And it's just as reliable as your one in your toilet, right? It runs all the time. It's a problem. So we get rid of that and we replace it with a level sensor. This is a capacitance type. This is the brand that we generally use. You stick it in the standpipe and you measure the flow. And then it also, so what does it do? It allows the makeup water to be inside, right? It gives you an analog sensor so that you can meet Title 24. Maybe you didn't know this, but Title 24, since the 2013 version, required that you have alarms on high level on cooling towers so that overflows don't occur. So you're not feeding too much water and having it dump down the drain. So that's required. So if you use this float valve over here, you still got to put a sensor out in the cooling tower to measure the level for these alarms. Often overlooked, but now it's covered. The unreliable float valve is eliminated. That's great. And it's lower cost. Yes, isn't that great? So you have all these alarming capabilities and it costs less, especially for a multi-cell tower. So speaking of cost less, we come up with a new idea. We had a little problem with this one over here. We had a cooling tower that had foaming water in it, and the foam would actually get into the equalizer somehow, and it would collect in the standpipes. We had foam in there. It was from the water treatment. We didn't know what it was. Nobody could figure it out, but the foam fooled the capacitance sensor. By the way, these are the same sensors that if you buy electronic water makeup control from the cooling tower manufacturers, they use the same thing. But we found that we can measure water with pressure. It seems crazy to think that pressure with only a few inches of water will create enough pressure you can measure it, but you can. Here's a pressure sensor that measures from 0 to 1 psi. That's 2.31 feet. Okay, so we can measure with 0.25 accuracy. That's quarters of inches the elevation of a cooling tower with pressure. So on the job, we had the foam problem on. We stuck this on there, and sure enough, it worked. And now this is our standard practice. It eliminates the standpipe. It isn't fooled by foam, and the pressure sensor is actually less expensive than the capacitance sensor as well. On our jobs, we put them at 3 o'clock so that dirt doesn't get in them, we actually put one at 9 o'clock as well. We put 2 of them on because they're cheaper. We say, hey, let's just be careful. Plus, we haven't used these, but on one job, and just to be careful, we now are putting 2 of them on there just to be sure we got it covered. Okay, let's talk about economizers, water side economizers. So in general, in our climate, you want to use air side economizers. Air side economizers on air handlers are the best. Not only do they save a ton of energy, but they improve air quality. So all the stuff about COVID and everything, you want to use outside air. Well, economizers do that automatically to save energy, but they improve air quality at the same time. So it's all pluses on economizers, so do that. But occasionally, you'll get applications where air side economizers don't work. The classic case is sometimes a tall building where you can't get air in and out of the building. As you know, as I mentioned earlier, We do that. We just use a big air handler on the roof. So we've got 30-story buildings with one air handler on the roof. So because we like that air side economizer so much. And so use the air side economizer if you can, but if you can't, in our case, the classic case is a data center that's where I can't get air in and out very easily. We use air side economizers on data centers too. Some of our clients get squishy about that because of air quality issues. They don't want you bringing in, bad outside air with ozone and whatever in it. But sometimes it's just physically too difficult because the loads are so high and the airflows are so high. So then we use a water side economizer. Now, water side economizers were first invented. People put them in parallel with the chiller, so it looks just like a chiller. Condenser water pipes just like the chiller, chill water pipes just like the chiller. We call this a non-integrated economizer because it generally can't work unless the chillers are not working either. In other words, it has to provide all of the load, the water as cold as it needs to be, or none of it. And that's why it's called non-integrated. So let's say we have a situation where we need 47-degree water out in the building for the loads, and let's say it's coming back at 65. That means it goes into the heat exchanger at 65, and it needs to come out at 47 to handle the entire load. So the chillers don't need to run. Well, how do I get to 47 on the chill water side from the condenser water side? Well, I'd need like 44-degree water with about a 3-degree approach on the heat exchanger, which means I need 44-degree water coming off the cooling tower. So how well can I get 44-degree water off of a cooling tower? Well, I need about 34-degree wet bulb in order for that to happen. So how many hours in the Bay Area is the wet bulb at 34 degrees? Answer, 10 hours a year in the San Francisco Bay Area for most of our climates here. In other words, never. So the non-integrated economizer would do almost nothing for you. We have to have the ability to have the economizer provide part of the cooling, if not all of it. So then we use something we call an integrated economizer. Here it is with primary secondary piping. We put the heat exchanger, instead of being in parallel with the chillers, we put it in series with the chillers. On the return side, upstream of the common leg, and then to get the water to go through the heat exchanger, we either pump it through, primary, secondary kind of thing, or we put a valve that squishes down and pushes the water through. In which case, these pumps have to be sized with that heat exchanger in mind, because some of the time it's going to be pushing the water through. On the condenser water side, it looks just the same as before. It's piped in parallel. The idea here is that if we have the economizer working, it's because it's cold outside. If it's cold outside, we don't need one of the chillers. So at worst, we're going to have the heat exchanger and one chiller running. So we don't have to oversize the pumps or anything. Either the two pumps go to both chillers, or they go to one chiller and the heat exchanger, or they go just to the heat exchanger. We put in modulating valves for head pressure control if we need to. If these are mag bearing chillers, then we don't need to. And that's what we call an integrated economizer. So let's do that same scenario: 47 degrees, chill water, 65 coming back. I need 50. What happens if it's 52 outside? I can get 59 off the towers. I can get 59 to the heat exchanger. 3-degree approach, I can get 62. Well, 62 isn't 47, so I'm going to have to run one of the chillers to take the 62 down to 47. And so I end up where I'm not doing the entire load, but I'm doing some of it. I'm going 3 degrees on the economizer, and then more than that, 12 degrees off the, or was that 15 degrees off the curve. So doing the chiller is doing a lot of work, but the economizer is doing something. So how many hours is it below 52? 4,000 hours. So for 4,000 hours, this partial economizer can give me some energy savings off the system. And that's why Title 24, since 1991, has required integrated economizers. We do a lot of peer reviews. Dozens of times we'd see people pipe them incorrectly, which is pretty crazy given that it is now 30 years since this became a requirement. So here we have 41% of the load is by the chiller, 9% by the chiller, the heat exchanger. Yeah, it doesn't sound that great, but 4,000 hours a year of that, and that's a lot. Here's what it looks like when it's primary only. In general, when it's primary only, you usually don't put the pump in here. You allow the pumps to the primary pumps to handle that pressure drop. Remember, when your economizer's on, the system's at part load. It's cold outside, so I have extra capacity in my pump, so I can do this where I just close this valve to push the water through when I'm on economizer, and open it when I'm not on economizer. When you have primary only, you have to put a bypass around here, because there's times when the chillers don't need to run at all. When it's very cold outside, I can do all the cooling with the economizer. So I open this up so that I don't push water through inactive chillers. So the same thing here. Okay, so comparing non-integrated to integrated, we have advantages of integrated water side economizer, much higher energy savings, especially in mild climates, less so in more extreme climates. Starting and stopping is a lot easier because the economizer is allowing the chiller to load up slowly all by itself. And eventually, when I turn off the economizer, basically it wasn't doing much anyway. I turn it off right when it really isn't lowering the water temperature very much at all. When we do that switch over from having the economizer to not having it, it can be done very, very smoothly. It also is not a problem when we turn on the economizer. The issue is not turning it off. We know when the economizer is not doing anything for us by looking at the water coming out of the heat exchanger. What we don't know is when we can turn it back on again. So guideline 36 has some very clever logic to try to determine when we can turn it back on again. But if you do so incorrectly with a non-integrated economizer, you turn off the chiller, you turn on the economizer, and you see if it can get the water cold enough. Oh my gosh, it's not cold enough. You have to reverse that and say, no, never mind. Turn on the chillers, turn off the economizer. When it's integrated, I turn on the chillers are already running. I turn on the economizer to see if I can make it cold enough. If it doesn't make it cold enough, big deal, then turn it off. And the chillers have see nothing. There's no effect on them in terms of their on and offness. So it's much easier to control, no sudden switchovers. And of course, it meets Title 24 and 90.1 prescriptive requirements, which requires an integrated economizer. Advantages of non-integrated is nothing at all. It may save a tiny little bit of money, but that's it. So it's not, it doesn't do anything. So don't do it. Here's an example of a waterside economizer savings. In our area, again, air economizers are God. You want to use air economizers. But occasionally we have a building that has a data center in it as well, for which air economizers are tough to do. So here's a exact case, where we have a data center that's about 110-ton load out of a total of 630. There are airside economizers on the office part, but not on the data center. It has chill water craws. So we look at a integrated versus non-integrated. We moved the building to different climates just for the hell of it to see what the difference was. And basically what it comes down to is that if you have I'm sorry, this is the savings with and without, this isn't integration versus non-integrated. This is an integrated economizer in different climates. So it saves a lot of energy in most climates, unless it's really hot and humid like Miami. And this is a data center. So remember, we don't need all that cold water for the data center to work. And so the chill water supply temperature you can see is in the 50s. On some of our data centers now, we have chill water supplies in the 60s, because our data centers are now hot. We don't just have a hot and a cold aisle. We have a hot and a very hot aisle with modern data centers. And the water temperature coming off the heat exchanger is not what we need fully, but it's better than the return water temperature. So we're taking a lot of the load off of it. Here's a blown up section where you can see that most of the load in this particular case, 3 days in April, we were able to get most of the load with the waterside economizer, with the rest by the chiller. Very seldom in our climate do you actually get all of the load by the waterside economizer, but it does get partial load, so it's very effective. All right, It is, oh, look at that, back on time. It's 12:15. Let's take lunch back here at 1:10, so 55 minutes. We'll restart again at 1:10, and I'll mark that on here. Is there any, I don't know why this thing is doing this to me. 1:10, Jesus. These little squirts of things are not something I'm doing. So anyway, we're gonna come back at 1:10. We'll try drawing that again. There we go, 1:10. And if there's any questions in the meantime, I'm happy to stick around and listen to answer your questions. So again, you can just, you're not on mute. So if you want to take yourself off of mute personally, you can ask me any questions. Okay, you're unmuted. I got a question. Said about the water side economizer issue. What about use of plate and frame heat exchanger on the cooling tower loop? Yes, you lose 1 or 2 degrees across the heat exchanger in any of the pumps, but you have a closed system into the water valve. So the water side economizers already have a heat exchanger. So that's what this is. So that keeps the chill water loop closed circuit, and the other side is open circuit. You're gonna have to have the open circuit some way. Early versions of water side economizer, people would inject condenser water directly into the chill water, so it would essentially make the chill water an open circuit system, and that was sort of a disaster from a water quality standpoint with clogging coils and other things. So let me know if that answers your question. And again,
the question was on the cooling tower side of the chiller loop, the condensing water loop.
So heat exchanger, so that the chillers would be closed circuit. I mean, the condensers on the chillers would be closed circuit.
Correct. It keeps the chiller barrels nice and clean. It keeps all the debris in the cooling tower itself.
The issue is that it's open circuit somewhere, right? And so either, like, you could have what we call fluid coolers or closed circuit cooling towers, where the condenser is all closed circuit, but there's still an open circuit somewhere. So that would be, that's what you're describing is what might happen when you have condensers that are hard to clean, like heat pumps. So when people do hydronic heat pump systems, they'll often use either a closed circuit fluid cooler or a open cooling tower with a heat exchanger, sort of like this heat exchanger, but up at the cooling tower, to avoid clogging. So you're going to have a maintenance cost somewhere, and so it's open circuit somewhere. So you have a water treatment somewhere, you've got something somewhere. Saving the condensers here, these are shell and tube heat exchangers, and they're designed to be serviceable. And so you annually will take off the head and ream them and clean them and things like that. And if you weren't cleaning that, you'd be cleaning the heat exchanger, plates as well. Somewhere along the way, you got to clean something. So it's a first cost issue as much as a maintenance cost issue. You don't save much in the maintenance, maybe nothing, and it adds a lot of first costs, because you need an extra set of pumps as well as the heat exchangers themselves. So I hope that answers your question. All right, so the morning we basically had a summary of sort of the fundamentals, the little pieces together, what the chill water systems look like and the components, how they get put together. But now we're going to get into the actual details, the design procedure. So now you're an engineer putting on your hat, ready to design a chill water plant. So the first thing we'll do is go select the chill water system. We've shown you examples of distribution systems, and now we'll show you how to pick which one's right for your job. And then we'll look at the temperatures and flow rates and primary pipe sizes. These are all tied together. Then we do the same thing. The next two bullets are the condenser water side, both the distribution system and the flow rates, and then we'll pick a cooling tower and all the options it has. Then we'll select the chiller. Now we've got, and we won't get into pumps just to save time. They are covered in the manuals that I've referenced, but we won't cover them here. And then we'll get into the control sequences after that. So distribution system. So we created this little chart where on the left-hand side are 3 independent variables that define your system. And the right side tells you what system is going to provide the lowest life cycle cost. And again, this is not lowest energy cost, it's lowest life cycle cost. So it will respect the first cost as well, and to a lesser extent, the maintenance cost. All right, so let's start at the top. If we have one load, one coil, any number of chillers, any number of coils with load serve, any size of coils, then the system you want to use is the single coil. By the way, these slide numbers sometimes get off because PG&E has me insert slides at the beginning of the deck that they want me to present, and these aren't auto updated. So this is the option where we had one coil and one chiller, or one coil and 2 series chillers. And so this is the best system for that. So it has no control valves at all, and chill water temperature is reset by the air side system control loops. And that's the least expensive and the most energy efficient system. So that's a win-win in that regard. So then we have more than one load, but we only have one chiller and the loads are pretty small. We'll use the option that has both 2-ways and 3-way valves. It's primary only. This is the one where the 3-way valves are at the end and they sum up to the minimum flow that the chiller needs. Then we go on to what happens if we have not too many coils, less than or equal to 3. This is a Title 24 and 90.1 limit 3 coils. If it's more than one chiller, so we have the staging issues that we worry about, we do a primary only constant flow system. This is all 3-way valves. This is very limited. It's only where you have 3 coils and generally small system. What if I have lots of coils serving similar loads, or any number of coil or any serving dissimilar loads, many coils serving similar loads, or any serving dissimilar loads, more than one chiller, then this is my most common application. So this is where I'm serving lots of loads. They may or may not be similar, so I either have a few serving that are very dissimilar, like the ballroom example I gave you, or the typical one where we just have coils all over the place. This is my most common example. We use 2-way valves only, and then it's either primary only or it's primary secondary. And I'll discuss which one you pick of these 2 in a minute. And then we have more than one coil, any number of chillers, and we have a large campus application. Then we look at distributed secondary. And then we have an unusual example where we have large coils, and large coil is defined as 100 GPM, just made up by me as an arbitrary number, but you sort of got to have something. And this is where you use a pump instead of a control valve. So you have no control valves, the pump is used instead. This is a fairly unusual circumstance. So in your buildings, most of your jobs are going to be this one. And so that's that. If we have the mega air handlers kind of thing, then it'll be this one up here. But most of your jobs can be in this middle one. So let's talk about which to choose. So I'm going to talk in more detail about these last 3. So here's primary, secondary. This one has the check valve and the common leg, or not. This could be gone if we have chillers that are variable speed, as we talked about earlier. These can be headered pumps or dedicated pumps, as shown there. Either way, still primary, secondary. And then we have primary distributed secondary. So this is the same plant exactly, except we deleted the secondary pumps and we move them to each building. So each one of these is a building. And so the question is, what are the advantages and disadvantages of this system? compared to a conventional primary, secondary, or conventional primary, secondary, tertiary. The primary, secondary, tertiary is what we'd have the building pumps and the secondary pumps at the plant. So advantages are reduced horsepower, because each pump is sized from the head from the plant to the building. So each of these pumps is sized to get the water from the plant to the building, through the building, and back again. So the primary pumps are only making the water go around in circles back at the central plant, and each pump would have its own head. So a building that may be far away from the plant, maybe 125 feet or something like that, and one that's close to the plant, maybe 30, 40 feet. It's completely self-balancing in the sense that the pumps will take only as much water as they want. We don't have to worry about overpressurizing the valves at the buildings near the plant. That assumes, of course, that the buildings themselves are not gigantic where you have to worry about oversizing them. So if whoops. So going back to the schematic, so that each building has its own pump, so we don't have to worry about overpressurizing these. When you have a common secondary pump, like here, these have to be sized for the most remote building. And they could be, again, in the example, I said maybe the furthest one needs 110 feet. So this has to be 110 feet. And that means any of the buildings that are close by are going to be have a lot of pressure behind them, that pressure that's used to get the water out to the most remote building. But now I have to chew it all up. So a good example of this is UC Davis, where they have a sporadic design plant and very high head pumps because of some poor decisions on sizing their mains. And they have so much pressure, they end up putting in a valve at each building that just chews up the extra pressure because the coils themselves can't handle it. There's so much extra pressure. Reduced pump energy. So we have we're again, because of the custom heads for each building, we're only using as much energy as we need, and we don't have any complex bridge connections like you do when you have primary, secondary, tertiary. So the disadvantages are you need a pump room in each building. A lot of sometimes you can have the pump be up in the penthouse or somewhere where it's not taking up any space, but most of the time there'll be a pump room right when the chill water and usually hot water come through the wall into the building. Some plants like that anyway, because they like to have a place to have a little office where they put the drawings and other things for the building, so they don't mind having a little room there, but it does take up space. This a little esoteric. The second bullet is higher expansion tank precharge and size. So when you have the water here, once it leaves the plant, its pressure is going down. And when it's coming back, its pressure is even lower. So with primary, secondary, the water is positively pressurized all the way through the system. Here it's negatively pressurized. We have to suck it out of the plant. So what it does mean is that in order to maintain positive pressure in the system so that pumps don't see negative pressures, or particularly in hot water pumps, we need to make sure we don't have any cavitating because of low pressures going into the pumps, low net positive suction head. We increase the pressure of the entire system back at the plant, and that means the expansion tank has to be a little higher, a little larger. And it does have higher costs because we end up with pumps at every single building. And sometimes this last item is difficult to calculate the building, calculate the pump head you need. So what's the pressure? What's the pump pressure drop in the mains? And right now it may be one thing when you have some buildings connected to the system, but later on you're going to add more buildings to the system and it changes what that pressure drop is. So you don't really know how to calculate the head. You can calculate the head here just like normal, but you don't know what it is coming into the plant. So usually you just make something up and it's okay because we have variable speed drives and it will just slow down. As long as you're not ridiculous in your conservatisms, it will slow down and be okay. So that's the advantages, the disadvantages there. One of my colleagues that lives down in Southern California, who does a lot of the CSU buildings, they actually prefer primary, secondary, but what they do is, as we talked about earlier with self-balancing, is they oversize all the mains. In other words, they start out with a size and they just keep it the same the whole way. And that reduces just like it creates the sort of equal pressure at every coil thing in the previous examples, it does the same for each building. So the amount of pressure that the first building needs is not all that different than the amount of pressure the last building needs, because the pressure drop in the mains is so low. And then you have the benefit also of flexibility about adding and subtracting buildings to the system. So that's not a bad way to go either. You know, from an energy standpoint and a flexibility standpoint, that's not a bad way to go. How about using a coil instead of a control valve? So basically, we get rid of the secondary pumps, and each air handler would have its own pump, and that pump is essentially like a control valve, except it's providing its own impetus on the system. So what are the advantages and disadvantages of that? Well, one disadvantage is it's really only applicable to big coils. So we have large air handlers here. And the issue there is that if these are all tiny little coils, these would be tiny little pumps. And sometimes they'd be tiny flow and high head if we're a long way from the plant, and you just can't really find those. You know, either that or they have to be multi-stage pumps, and they get sort of expensive and awkward. Some people have done that, but to me, it only makes sense to do this when you have large coils, which we defined as 100 GPM coils. Now, what happens if a building that has some large coils but that has other small coils? Well, you can do a hybrid where the large coils get their pumps, and then you create a standard primary secondary circuit where the coils are there's pumps that serve multiple coils. So these would be all the small coils, and the big coils would all have their own pumps. Advantages and disadvantages versus conventional primary secondary: reduced horsepower, not only because each pump is sized for the pressure drop from the coil to the plant, but also because we eliminate the control valves. And control valves are typically are commonly selected for like 5 psi, which is like 10 feet. So right off the bat, you gain 10 feet in reduced pressure drop by getting rid of the control valves. Again, it's self-balancing, no need for reverse return or anything like that. Low pump energy. The advantage of when you have a primary secondary system, you maintain a minimum DP set point all the time, and it can be reset, but it's generally going to be fairly high enough to get water through the last coil. Here, there's no DP minimum set point. The pump curve essentially goes through zero and constantly zero flow, and consequently, the pump efficiency is constant. Whenever I have a minimum DP set point, you'll have to sort of imagine a system curve on a pump curve that has a minimum head on it, and that will take you off of the parabola of the normal system curve and cause the pump efficiency to get worse at low loads. In this case here, the pump efficiency is basically constant. You have better control. Nothing's better than a variable speed drive for varying flow. There's no hysteresis. There's no time delays. It's really quite instantaneous the way pumps work, and you don't have to worry about overpressurizing any pumps or any valves because we don't have any. So it can have lower first costs due to the eliminated control valves and the reduced pump and variable frequency drives, but only if we're willing to have one pump per coil. If you say, no, I want redundancy there, I want 2 pumps, then the cost will not be in favor of this option. Disadvantage of this arrangement: one is you can't tap into the distribution system without a pump. So again, the pump, the pressure drop is reversed. Coming out of the plant, this pressure is higher than that pressure. So if I stuck a coil in here, between here and here, the water would go backwards. It would go in that direction because this pressure is higher. So in order to get water to go through a coil, I have to put a pump on it and pump it through. And that can be a pain for just adding coils to the system. Yeah, so you have to have a pump. Sometimes that's a problem. The low flow, high head pumps are hard to get. The reduced redundancy, unless you put the duplex pumps at every coil, but then that costs too much. And then some unlikely, but some possibilities of low load instabilities because you eventually have to cycle the pump. The minimum speed on the pump is going to be 5% or 10%. Anybody who, God darn this, I don't know why it keeps doing that. Sorry. The minimum speed on pumps on motors is often misunderstood. And first of all, there's no minimum speed on the VFD itself. It can go to nothing. The pump motor may have a minimum, but on applications for like this, like pumps and fans, every VFD ready motor that's sold in the country can go to a 10-to-1 turn down. That's 10%. And most of them are 20-to-1 turn down. That's 5%. So there's a lot of old wives' tale about maintaining 20% or 25%. It's garbage. ABB, the VFD manufacturer, at one point had a default for their minimum speed of something like 20 hertz, and a lot of techs were afraid to change that to something lower because they say, well, if it came from the factory that way, it must be right. And so we would end up often on our projects having to change the minimum in the field ourselves because we knew it wasn't right. I complained to ABB enough that they finally said, you're right. And they now ship their VFDs where the minimum speed is 0. So there ain't no minimum speed on the pump. So there's no, you'll have to set it yourself if you want it to have a minimum speed. But anyway, since you can go down to like 5% on these things, the odds of having to cycle much is very low. What about primary only versus primary secondary? Remember, one of the options, the most common application was lots of coils. What do we do then? So primary only. So primary only in general is going to have headered pumps and isolation valves, as we've shown here, instead of dedicated pumps. And the reason for that is primarily allowing slow staging. And I'll talk about that later on today when we talk about staging primary pumps. It does also allow unequal number of pumps and chillers. So, for instance, we could have 1 pump and 2 chillers running. So with the logic that we'll talk about this afternoon, guideline 36 logic, the pumps are in this arrangement are staged differently than the chillers. The pumps are staged entirely on flow, and the chillers are staged on load. So they don't even, we can have a different number of chiller and pumps, and they're really they don't have to match each other. We don't have to start a pump when we start a chiller. And then we're showing here with the flow meter. We can also have the DP sensor across the chillers as an indicator of flow. But as I talked about earlier, we generally will use the flow meter so that we can also measure not just flow, but also capacity load. So the advantages of this versus primary secondary are lower first cost because we have fewer pumps, less plant space required. So the first time I did a primary only plant was in 1997, and it was actually driven by space. We had an existing building that needed a chiller plant stuffed into one corner, and I didn't have enough room to have both primary pumps and secondary pumps. I had done commissioning for a primary only plant in 1994 back in Atlanta when I worked there for a while, and so I learned about it and never tried it myself. We had a bunch of issues on that job, but not that they're all resolvable. So I finally bucked it up and said, okay, I'm going to do a primary only plant. Anyway, it was driven not by the first cost, but by space requirements. Reduced horsepower. We have part of the horsepower savings is that whenever you have a pump, you also have valves on either side of it. You have a check valve. You often have a strainer as well. And so every time you have a pump, you have the pressure drops of all those elements. So by eliminating one pair of pumps, the secondary pumps, we eliminate those as well. But there's an indirect savings is that pump efficiency is for a pump with the normal flow rates and heads that our distribution pump has. We end up with pumps that are 1800 RPM motors 1750 RPM speed of the pump. If you end up with a primary pump, if it's properly sized, it's only go around in circles. It only has the pressure drop of the chiller essentially, and that's about it. So it really might have a head of only like 25 feet, and yet it has a high flow rate. And to get that pump, a selection of that pump to be efficient, you often end up using a 1200 RPM motor pump, and that costs more. The motor costs more, and the pump is bigger because it operates more slowly. So you spend more money on it. And a lot of people cheap out and they say, no, I'm not going to do that. And they use a 1800 RPM motor and just a less efficient pump. So by getting rid of the primary pumps, or really combining the primary pumps with the distribution pumps, we can end up with more efficient pump selections. So for both these reasons, we end up with lower pump horsepower. And we end up with lower pump energy over time, not only because we started out with less horsepower, but we now also have cube law energy savings through the through the primary circuit, as well as the secondary circuit. So we get energy savings that we didn't have before. The traditional primary secondary has constant speed primary pumps and variable speed secondary pumps. Now, you could use primary secondary with variable speed primary pumps, and some people do that, and that gains a lot of the pump energy savings back from compared to constant speed pumps. But of course, you spend more doing that. That's more of something you do on a retrofit basis than a design basis, new design. So we did a very detailed model when we were first looking at primary, secondary versus primary only. This involved a lot of the modeling from the pipe flow circuit model. And the reason why is because some people said, well, maybe primary second looks like it's better, or primary only looks like it's better, but over all the staging that occurs, it may not be over all the stages. So this is a 3-chiller plant. So you can see these little disruptions where the curve blips. That's when we start and stop, one of the chillers, this one and primary pumps. And it turned out that in the model, primary was always more energy efficient than primary secondary. So you may be asking yourself, okay, wait a minute, we got first costs are lower, less space is required, less energy. What's not to like about this system? Why not just always use primary only? Well, it does have some downside, and here they are. One is the failure of the bypass control. So the bypass valve is, it has a control, it can fail. We already talked about it being well tuned, so to make sure that it doesn't cause short cycling of the pump, but it can literally just fail, and that's a downside. But it also, the system is much more sensitive to disruption. So for instance, I mentioned that job in Atlanta that I was commissioning back in '94, and it was the first primary only job I'd ever seen. And one of its big problems was all the air handlers. This was like a 70-story building. All the air handlers went off at the exact same time every night. So the chiller is cruising along, and all of a sudden, whammo, all the valves go closed except for a couple of 24/7 loads. The abruptness of the disruption in flow caused everything to trip. And so we had to make sure that we slowly closed the valves when units were turned off. We changed the schedule so that they didn't all stop at the same time as well. Now in guideline 36, we solved this by simply closing the valve very slowly when we turn off an air handler, so that we don't have to worry about schedules and other things, but it is an issue. And then we have flow fluctuations when staging chillers on, because the flow drops through the operating chiller. The easiest way to explain this is with an example, which I'll do on the next slide. And then just a point that both these issues are only problems where you have a plant that does have a minimum bypass control, and that has staging with very few chillers running. It's usually staging from 1 to 2 is the issue, less of an issue with 2 to 3, and not at all an issue from 3 to 4 or more. So the plant at San Jose that I talked about that we worked on, it had 12 chillers, and 3 of them always ran because there was always a base load from all the process loads. And they didn't have a minimum flow bypass because they didn't need it, because they always needed at least 3 chillers. So in that plant, primary only, which is what it was, had no problems because there was no staging issues with flow fluctuations. There's no minimum flow bypass at all. So here's the explanation for why there's an issue with staging, particularly from 1 to 2. So let's say we're cruising along here. We got 1,000 GPM going through 1 chiller. The other 2 chillers are off, and we decide that we need to add flow. So we got some coils that are saying, hey, I need more flow. I need more colder water. My valves are wide open. Do something about it. What to do? So we want to increase the capacity. We want to stage on a chiller. What do we do? Well, if we just instantaneously opened up the automatic isolation valve, the flow would immediately split, half through one chiller and half through the other. And that abrupt change in flow can make this chiller trip off. And in fact, that's what the problems we had in Atlanta in that first plant was. It would trip whenever it went from 1 to 2. So the way we solved that, way we solved that is by using the auto isolation valves and making these modulating. In that plant, they're actually pneumatic, so inherently modulating. And we just did it slowly. So what the guideline 36 logic is, it will say, okay, relax this chiller that was running, basically raise its set point or demand limit it in some way so it's not close to a tripping point. It's not close to the water being too cold. And then slowly open this valve. Don't turn on the chiller yet. Slowly open this valve and allow this flow to drop from 1,000 GPM down to 500 slowly. Eventually, this one's wide open. And once this one's wide open, you can start this chiller and you can re-engage this one and drop its water temperature set point back down. And now we're good to go. So that's the kind of logic we need to do. That's fairly tricky and complicated for primary only, that you don't see with primary secondary. And it requires that the controls do it too. You can't just sort of manually go over there and turn on a chiller because all this logic has to happen or you'll trip things. Now this concern is still in guideline 36. We still have this relaxed way of staging, but it's becoming less and less of an issue, and maybe and not too long we won't worry about it at all because chiller controllers are getting so robust that they may not have a problem with abrupt changes in flow anymore. It's the cost of making this an analog valve versus a 2-position valve is not that big of a deal. And so having that ability to slowly open it is nice, but it may not be too long before we just say it's going to work anyway. We did have a plant that had train chillers on it where we deliberately took one chiller running at high load, didn't relax it at all, and opened up both of the other isolation valves to allow flow to go to all 3 chillers. So now we had 1,000 divided by 3 through the chillers, and it didn't trip. So it had robust enough controls that even opening them didn't trip them. Remember, though, that electric actuators are very slow anyway. There's probably a 90-second valve to go from full open to full close. So it's never super abrupt one way or the other. But the control sequences do include this soft staging, but it may or may not be an issue in the future. So those are the primary, secondary versus primary only advantages. But there's one exception, one special case, and that is chilled water thermal energy storage. If we have thermal energy storage, it turns out that primary, secondary is just ideal because you put the tank in the common leg between the two, and it allows the plant to be charged, or the tank to be charged and discharged at the same time. So you can run the primary circuit only and charge it at night. You can run the secondary circuit only and discharge it during the day, or you can do both at the same time and run the secondary to some, say, 24/7 loads at the same time as you charge it. And there's no control valves in here, you'll notice. You didn't have to open up and say a charging valve and a discharging valve. I've seen some crazy piping of thermal energy storage tanks where somebody just hadn't heard of this idea. Nobody that's heard of this idea doesn't think that it's fantastic. Super simple idea. Just put the tank in the common leg, and it's the way to go. So this is a case where primary secondary is always the best way to go versus primary only. And then speaking of thermal energy storage, it's getting more popular to use thermal energy storage. It's very popular at big central plants and like UCs and the CSUs pretty much all use it. It has energy savings. You can get rebates for it. Title 24 gives you credit for using energy off peak, etc. But it's very expensive and it takes up a lot of space. At the end of this presentation, I'll talk about the time-independent energy recovery system that we developed that is a compromise. It does use TES, but a much smaller tank compared to chill water thermal energy storage. So with this decision of primary only versus primary secondary, so in that chart, it said pick one or the other, and here are the considerations. We use primary only for plants with many chillers and no bypass, like that plant down in San Jose, or plants where the design engineer and future on-site operators understand the complexity of the controls and the need to maintain them. So as I said, you can't just walk over to the chiller 2 and crank it on. Everything will trip. So the building engineers have to understand, design engineers have to understand it so that they build in the controls to allow soft staging and other issues and softly turning off air handlers, all that kind of stuff. Now, fortunately, all that stuff is in Guideline 36 now, so it's sort of thought out for you. Anyway, the building engineers are a factor. So otherwise, you primary, secondary, and also use primary, secondary when you have a chill water thermal energy storage. So where this might be? Let's say you had a big high school that was big enough to be chilled water. You probably wouldn't want to do a primary only variable flow there. The kind of maintenance people they have at a school are generally not that sophisticated, and they'll appreciate the simplicity of primary secondary. Other than that, go ahead and use primary only. And I mentioned a little earlier about primary secondary with variable speed pumps on variable speed drives on both the primary pumps and the secondary pumps. You can get pretty much all the energy savings, not quite, but pretty much all the energy savings of primary only that way. But it costs way more now because you're buying variable speed drives as well as extra pumps. However, it's a great solution for a retrofit. So I've seen people take a primary, secondary existing system and try to convert it to primary only by having to replace pumps and other things. It's like, no. Just put variable speed drives on the primary pumps, and now you have a system that is really just as good as primary only, but it's still simpler and doesn't have a lot of the issues of primary only with respect to flow disruptions and everything. So don't think that primary only is the thing you have to do. Yes, on a new building, it makes total sense. It's less expensive, more energy efficient. But on a retrofit, just keep it primary, secondary, and put variable speed drives on it. Okay, let's move on to optimum chilled water and condenser water temperatures. Start with chilled water. Again, we have this equation we talked about before. Load is equal to 500 times GPM times delta T. Part of the fundamentals of this is pipe sizing. How do you size a pipe? And there's an article that was in our link there on how to size a pipe using life cycle costs. So we discuss needing to balance the cost of the pipe at its installation, the cost of the pump energy, the longevity of the pipe, meaning we have to consider whether we're screaming water through it and maybe eroding the pipe, noise issues, and sometimes space limitations. Pipes are pretty small, so usually space isn't a factor, but it can be at times. So we developed a life cycle cost spreadsheet that you can download from our website. And what it is a spreadsheet that we developed that includes in it all the pressure drop information of these various devices. So we have a straight pipe, elbows, T's, and all these fittings in here. And all that is built into the spreadsheet. So you just say the quantity that you have without having to worry about looking up model numbers and catalogs or anything like that. And it does it for you. You can look at, do we need to turn on a speed limit because of noise or erosion? Do we want to include the cost of insulation in here? So all that is built into the spreadsheet. And you'll notice all these auto things in here. So you enter a line pretty much as any sections that you want, but you at least have to enter a line for each different flow rate. And once you're done entering all the stuff, you go all the way out and all the way back on your system, go around in circles, and then we have this auto group button. What that will do is make sure that all the pipes that have the same flow rates are treated as one with respect to life cycle cost. The purpose of that is that sometimes you can end up with a pipe with the same flow rate be a different pipe size, because if there's lots of fitting in it, it costs more. So it might be that you'll end up having a small pipe if there's lots of fittings and a big pipe if it's straight. And just from a practical standpoint, you sort of want all the pipes that are the same flow rate to be the same size. So we group them together. That makes the life cycle cost analysis work. And then you can press, if you have auto in here, you press this auto pipe size button and it'll automatically size all the pipes based on life cycle cost. And you enter, of course, all the life cycle cost parameters in there as well. Now you can size it manually if you want, like we manually, in this particular example, manually overrode the pipe sizes here and said, no, we're gonna upsize these a little bit because this is the longest run and it's got some good long pipe lengths. So just to reduce the pump head a little bit, we're gonna oversize just these pipes here to the system. So this is how it works. Now we ran we ran a macro that ran the pipes life cycle cost selection for a couple of standard circuits that had pumps, coils, other things, and changed the pipe size and then ran the pipe size selection program to see what flow rate was the best so that we could come up with a simplified chart so that you didn't have to enter all the data. So for this, you have to actually have a design in order for you to do it, right? You got to have all the feet of pipe available to you. You have to know where the fittings are, all designed. And that's great for the end of the job, but it's not very good for the beginning of the job. But by the way to use this is it's great to have 3 screens. One for the spreadsheet, one for the piping schematic, which shows you where all the fittings are, the valves and stuff, and the other being your Revit or AutoCAD drawing, where you can measure the lengths of each pipe. So with those 3 screens open, you can take off all this stuff in just minutes. It takes almost no time at all to do. Anyway, so early on in the job, you want to be able to size the pipes really quickly and easily. So we created these sheets, also downloadable from our website, that talks about constant flow systems. This would be like cooling towers, constant flow, constant speed, and then variable flow, variable speed systems. So this would be your hot water and your chill water plants. And then you have whether the piping is in non-noise sensitive or noise sensitive, and then how many hours a year does it run. So if you decided that I had a chill water plant that was variable speed, variable flow, I go to this chart over here on the right. It's about, say, 2,000 hours. It's non-noise sensitive, say this is like in the chiller plant. And then I would simply go down until I found a number that was bigger than my flow rate that I wanted to design for. So let's say it was 400 GPM. I go down here until I see something bigger than 400 GPM, and that's my pipe size. So that's how to use it. Now, if it was out in the space, now it's noise sensitive. Then I have 2,000 hours. I'm still going to go down here, and now it's going to say, no, you need a 5-inch pipe because a 4-inch pipe would make too much noise. So that's basically how this is done. So you can preliminarily select all your pipe sizes, and then later towards the end of the job, you can revise them all if you want to using this spreadsheet here. You're going to run this spreadsheet anyway because you need to size your pump head from it. All right, so I introduced that because we use pipe sizing in determining what my optimum delta T's are. So what are the trade-offs on chill water delta T? So a big delta T means we have smaller pipes, smaller pumps, smaller pump motors, we have lower pump energy, all good. On the other side, maybe an 8-degree delta T, we have smaller coils, we have less coil surface area, and we have lower fan energy because the smaller coil will have a lower air side pressure drop. So in looking at this, you say, okay, well, there's going to be a trade-off between the two. Now the fan runs all the time. So chances are this air side penalty is at some point going to offset the pump energy savings over here, and I'll be better off using a smaller coil at some point. So we expected that doing life cycle cost on different sizes of coils, different delta T's, that eventually it would flip, and you'd say originally the savings would be for bigger delta T's, and at some point it would say no, the airside penalty is too much. So we've selected some real coils to try to analyze this in detail. And what you'll notice is that for these coils looking at 10 to 25-degree delta T's, the coil pressure drop, of course, is basically going as the square of the flow. And they're not quite because they have different number of rows. But no matter how you look at it, the bigger delta T's have much lower pressure drop on the water side, obviously, not surprising. The air side is, of course, going in the opposite direction. We have a 1/2 inch here and 3/4 of an inch for a 25-degree delta T. So that's basically a 1/4 inch difference between the two. And that's not nearly the same magnitude as the water side between them. And then here's the rows and here's the fin per inch. So all these were selected for the same conditions, but for different and the same water temperature, 43 degrees, but differing delta T's. So again, our thought was, okay, this 1/4 inch difference between 0.78 and 0.48 eventually would put the fan energy as a factor and would offset the pump energy side of the equation. But when we did the analysis, we didn't find that to be true because that 1/4 inch is only a 1/4 inch at full load. And the pumps are also variable speed and variable volume. And remember, it's also, the whole system maybe has 4 inches of pressure. So that 1/4 inch is a very small portion of, it's only 10% or so of the fan energy. And it's variable speed, so you'll only see that at full speed. So what we found was that the fan energy, you can see right here, is not that much more for a 20-degree delta T than 11-degree delta T. It's just a blip. You can barely see it in this thing on an annual basis. Now, with the same pipe size, a little unfair here because we didn't make the pipe sizes go down, but keeping the first cost the same, essentially, and varying the coil size, you can see the pump energy go way, way, way down. So the pump energy starts to become a factor in here, and it overwhelms the fan energy add. So the fan energy add versus the chill water pump energy savings favored the bigger delta T. Now, as I said, this is a little bit unfair because I would have at some point selected a smaller pipe and taken the first cost savings, in which case this would have a little bit higher energy use. But nevertheless, as we are doing this analysis, we kept finding out that the bigger the delta T, the better it was. And when we first did this analysis was in the late 90s. At that time, nobody did more than about a 15-degree delta T. That was the biggest we'd ever seen anybody do. On our own projects, and we were fairly aggressive, we may have gone to 18-degree delta T once in a while. But what this analysis was telling us is that you keep going up in delta T and things keep getting better from a life cycle cost standpoint. Then we looked at what happened if we kept the air side pressure drop the same. In other words, let's use the same coil and then vary the water temperatures in here. And so if we use 41 degrees, we could get a 16-degree delta T. If we use 44, we could get a 10. So which is better? Of course, the fan energy by definition is all the same here. And you can see that the chiller energy gets worse with the colder water over here. So it's higher here than it was here. But the pump energy gets better. And again, it's a little unfair because we kept the pipe sizes the same. But you can see that the bigger delta T had the bigger energy use, even with this analysis. And then we looked at first costs. So at first cost, we did some selections of coils. We selected the coils, priced the coils here, and then also piped the system up with the normal piping thing with valves and test plugs and all that kind of stuff, and had a contractor price it for us. And you found that with the different delta T's, so the fluid pressure drop is right here. You can see that basically the first cost was almost the same. This includes about 20 feet of pipe from the mains to the coil. So a lot of the savings that the big delta T saw was because its pipe size to the coil was smaller, and we had about 20 feet of it, or 40 feet. I'm sorry, 20 feet. Yes, 10 feet each direction. So that's part of the savings. But all in all, is that the plant side, if anything, it gets better with bigger delta T. The cost gets better, but it's perhaps close to neutral because of the extra cost of the coil. So what we found was in doing the life cycle cost analysis that both first cost, especially both energy cost and first cost, went down. Energy cost definitely, first cost also went down by picking a very high delta T. Ones that were higher than we'd ever picked before going into this analysis, up to like 25 degrees. That's just with a normal chill water system. If you have a system that has a water side economizer where the return water temperature, the warmer it is, the more energy savings I'm going to get, that's better. And if I have a thermal energy storage system, it's even better still because I now get more storage for the same number of gallons in there. So delta T on chilled water is good. And what we ignore that little square for a little bit. Here's the optimized procedure. We have two procedures to follow. One is this long version of it, and one is a short version of it. And you know what? We never use the long version of it anymore. So I'm just gonna skip it because I'm just gonna get you to the important part here, which is this. Is the long and the short of it is, you use big coils. And what we found was that the delta T kept getting better and better as the life cycle cost kept getting better and better as the delta T went up. But we finally hit a wall, not in life cycle cost, but in standard 62 cleanability limits. So standard 62 has a requirement that says for a dry coil at 500 feet per minute, it can't have a pressure drop bigger than 3/4 of an inch. And the purpose of that cleanability thing is so that you can clean the coil. If you had a 12-row coil with 15 fins per inch, and you try to spray it and steam clean it, it wouldn't clean because all the dirt deep inside, you can't get to it. And so somewhat arbitrarily, but with some feedback from some contractors, standard 62 determined that a 3/4 inch pressure drop was a surrogate for cleanability. So that happens when you have 8 rows and 10 fins per inch, maybe 12 fins per inch, depending on the fin type. So basically 8 rows, 10 fins. And so the answer to optimizing our plant gets really, really, really simple. Is instead of selecting a delta T and using it and making it the same for every coil, you select the coil and get the selection program to tell you what the delta T is from that and what the flow is. So you start out with 8 row 10 fins for all your coils, every single one of them. And in some cases, fan coils may not have that available. Okay, well then pick 6 rows if it's not available. If 6 rows isn't available, pick a different manufacturer because I can guarantee you there's lots of manufacturers out there of fan coils that make 6-row fan coils. Some even make 8-row fan coils. So that's it. It's so simple. Now I'll skip all the other stuff here, but because I'm going to go to our simplified procedure. In fact, I'll skip this example because I'm going to go to the simplified procedure. Here's the shortcut procedure. This is what we now use all the time, because just like everybody else, we have a time limit. You know, we have a fixed fee and we got to make some decisions. So here's what we do. We say we use 42 degrees. The previous procedure was basically trying to find how warm the temperature could be for a given pipe size, essentially a given system of pipe sizes. Here we just say, screw it. Let's just use 42 degrees. Why 42? Well, it's well enough above freezing that you don't have to worry about that. It's well enough above where you're going to probably have trips. You want to have a little insulation from trips if the flow changes and your chiller suddenly drops the water temperature. But it's not so high that we end up with higher, lower delta T's and lower first class. Remember, the colder the water, the bigger the delta T is going to be. And we use the 8-row 10-fin coils. We make sure that they're fully circuited. Go back to that slide on circuiting. Is don't accept anything worse than fully circuited. You might experiment with half circuiting, where you put in, rather than all the rows getting a feed, half the rows get a feed. The pressure drop will go up, but your delta T will get better. And then you determine the actual coil delta T and flow using the coil program. So you're using the coil program backwards from the way people traditionally used them. Traditionally, you would say, I want a 12-degree delta T, or I want a 10-degree delta T. You tell me how many rows and fins I want. Now we're saying, I'm telling you how many rows and fins I want, and you tell me what the coil delta T and flow are. You simply sum up the flows and then do a GPM weighted average chill water return temperature, so that you know what's coming back to the plant. So you can do this all by putting it, of course, into a spreadsheet. So versus the previous method, the one I skipped, is that we end up with colder water temperature because we just fixed it at 42. And both of them end up with the same pipe sizes by design. In this case, the first costs can be lower because we end up with a bigger delta T by using that colder water. So the pipe sizes are the same. We found that the energy difference between the two is fairly small, because we actively use chill water reset to reset the water temperature up most of the year, so that we get most of the energy savings of the warmer water, and only when we're on peak and we've run out of pump, essentially, do we need to make the water temperature colder. So this shortcut procedure is slightly less life cycle cost, worse, but it's so much easier to do, and it doesn't take any iteration. So this is what we do. All right, optimum condenser water temperature. Again, if anybody has any questions, jump right in. Okay, so using the same kind of chart, we have on the high side 20-degree delta T. We have smaller pumps, smaller pipes, smaller pump motor, smaller cooling tower motor. Lots of good stuff over here. Lower pump energy, lower cooling tower energy. On the left side, low delta T, we have a smaller condenser. We have lower chiller energy. So you look at this one and say, well, gosh, this is going to be the same way, right? This is going to be where the higher is better in the system. But don't forget, chiller energy is way bigger than pump energy. So it doesn't turn out that way. So what we found was, in the original runs, is to look at, again, looking at this one is a constant cooling tower. So we pick one cooling tower and we change what the approach and range are. So we make the water colder but with a bigger range versus a smaller range and a warmer water. So this is a constant cooling tower. So the yellow thing here is going to be the cooling tower energy, and the white is the pump energy. The yellow is the same, and the chiller energy changes. So remember, we talked about lift. Lift is the leaving water temperature. So it's what's determining what the chiller power is. So this is the sum of these two, is what's coming out of the chiller and going back to the cooling tower. So over here we have 85.5. Over here we have 89. So 89 is higher coming out of the chiller. That's what determines its lift. And that's why the chiller energy over here is bigger than the chiller energy over here. But you'll see that the total energy actually has a dip right here. And so it isn't the bigger delta T all the time, as it was with chilled water. And that's simply because the chiller energy is bigger than the pump energy, and the cooling tower fan energy as well, although that's constant in this case. So there is the thing we sort of expected on the chilled water, where there'd be a low point between, we wouldn't just all go all the way to high delta T. Then we did a lot of life cycle costing for the chiller plant manual that we did for ASHRAE, and we looked at 5 different weather zones, including Miami, Chicago, Albuquerque, Bay Area, and one other that I can't remember, different climates, to see what was the best. And we cost estimated all of them, and with different pipe sizes and equipment and everything like that, and did the energy analysis and found that 15-degree delta T was the life cycle best. So this is life cycle cost on the left here, life cycle costs. You want it to be lowest. And what we found is, like, here's a 9-degree delta T, 12.5, and 15. Every climate zone we analyzed, 15 degrees was best. And interestingly, Train did a study that found that 15 degrees was best. And there's another study we found in the literature that found 15 degrees was best. And it's just strange confluence that everybody seems to agree that 15-degree delta T is the life cycle cost best for a plant. So we say, great, we're picking 15 degrees. I have my animations here a little screwed up. Sorry about that. So here's the procedure. First of all, I want to get the first cost savings of using a 15-degree delta T, but then I'm going to try backing off on that. So first, determine the flow rate at 15 degrees. Take that flow rate and use either the simplified spreadsheet, the shortcut one, or the more detailed sizing spreadsheet, and pick all your pipe sizes in the most important circuits. So you've got individual pumps, the headers coming off the pumps, the going to the chillers, the individual branches to the chillers, and the main risers, if that's going anywhere, or what's going to the cooling towers. So in the critical circuit, okay, that's the one that's going to size the pumps. Usually with condenser water, all the circuits are about the same, so it doesn't matter. And then we find the maximum flow for each pipe size from those, so we size the pipes, and then we go back to the chart and say, okay, well, how much flow could I have gotten through that pipe if I maxed it out from that pipe sizing chart? So we max all the flows out in each section, and then you back calculate what the delta T is for each of those, and the largest one of those is going to be the delta T for the plant. So the procedure here is to, and then we can adjust the condensed water flow once we decide on the delta T. So the procedure is intended to minimize cost by reducing the pipe size as much as possible. But then once we bought that pipe, once we paid for that pipe, we want to push as much water through it as we can so we can reduce the delta T, because we know that a smaller delta T, or really a smaller leaving chilled water temperature from out of the condenser, is going to reduce chiller energy. So here's an example. So we have our chilled water plant. We have the rejected BTUs. So this is what's coming out of the chiller, what's being rejected to the cooling tower, each chiller, and then total. We say, okay, let's take a 15-degree delta T, calculate what the flow is. So that's the BTUs, 500 GPM delta T. Calculate what the flow is off a 15-degree delta T. Go back to those charts. In this case, it's going to be constant flow, constant speed, without considering noise. And those charts say, oh, it's a 6-inch pipe to each tower and to each chiller, and it's an 8-inch pipe for the mains. And you say, great. Once I've done that, I go backwards and I say, okay, what's the maximum I can get out of a 6-inch pipe? What's the maximum I can get out of a 12-inch pipe? And you back calculate what the delta T is at these flow rates. So for the 6-inch pipe, it's at 11.9 degree delta T, and for the 8-inch pipes, it's a 13.9. So this is what I select. I select a 13.9 degree delta T, and now I use that to size all the flow rates and delta Ts from the system. Had I used a 10-degree delta T, you can see I would have been one pipe size larger for both sides. That would be a significant first cost hit. And so your first costs are going to go up. And in fact, our energy can actually go down with the lower flow rates. So we maximize flow with the pumps. We take the first cost benefit of the big delta T, then we maximize the flow rate to reduce the return water temperature, improving the efficiency. So that's the basic gist of this. It's a very simple procedure on how to do it. So start with 15, get the flows, select the pipe, max the pipe out, and back calculate the delta T. Again, any questions? Go ahead and interrupt me. Okay, so let's go on to cooling towers. Cooling towers have interesting performance. It's the range of the cooling tower. This is the difference between the water coming into the cooling tower versus minus what's going out of the cooling tower. And then the approach, I'll show you this again on the next slide. The approach is the difference between what's coming out of the cooling tower and the wet bulb temperature that we're fighting against. And then there's capacity over here. So this is saying that with a big range and a big approach, I can get a lot of cooling capacity out of the tower. And the lower the approach, the more difficult it is for me to get capacity out of the tower. And it's quite steep here. So it's pretty much like any heat exchanger. As you try to get closer and closer approaches, just like on a plate heat exchanger, you might try 5 degrees. As you go from 5 to 4 to 3 to 2, the size of the heat exchanger goes up exponentially. And the same with cooling towers on approach. So here's a schematic showing what happens. The water comes into the top of the cooling tower, and the air comes in the other direction, or count sideways flow, but basically it's counterflow. And as the air and the water hit each other, some energy is transferred. Some of it is just simply a sensible transfer, because the water can be colder than the air depending on where in this tower you're at. But most of it is evaporation. So about 90% of the heat transfer is latent, meaning it's evaporating water. So that's how it works. So the definitions of our terms, we have the entering minus leaving is our range. The leaving minus the wet bulb temperature is the approach. So why wet bulb temperature? Well, that's basically what's driving the evaporation. That's the energy content of the air. So standard rating conditions for ASHRAE are 95, 85, 75. 95 entering, cooling the water to 85 at 75-degree wet bulb. Some of you may be familiar with the CTI standard, Cooling Tower Institute standard rating condition, which is 78 degrees. Now, why did ASHRAE pick a different number than the cooling tower industry for a standard rating condition? Here's an interesting story. This was an accident. I was on the 90.1 committee in the late 90s. We decided to include cooling towers for the first time in the equipment efficiency standards. And we went out for public review, establishing a certain efficiency, and I'll talk about what that metric is in a second, at 95, 85, 78 at the standard CTI rating conditions. But when it got published, ASHRAE staff, this is back in the old days when they would take our stuff and then put it into a printing kind of program that allowed them to print books, a long time ago. And PDF hadn't been invented yet, and they made a typo, and they just, instead of typing 78, they typed 75. We noticed this right after the public review and about to go to publish it, and we said, oh, well, that was just a typo. We'll change it to 78. But that, of course, is a lower approach. So it's easier to make the efficiency requirement at 85 to 75 than it is at 85 to 78. So the cooling tower manufacturer said, whoa, wait a minute. You just made the thing more stringent. We're going to have to go out to public review all over again. And we didn't have time for another public review. We wanted to get this into the 99 version of ASHRAE standard 90.1. So we said, forget it. We'll just use 75. And so just because of a typo, we managed to change the entire industry standard from 95, 85, 78 to 75. Now you know something you didn't know. All right, cooling towers. The best kind of cooling towers are propeller fan towers. The ones on the left, these are the two most common size. The one on the left is called cross flow. because the air comes in sideways and then goes vertically. The water's going down, the air is going left to right. So it's a sideways kind of flow distribution. And then counterflow is over here where the water is going vertically and the air is going vertically the other direction. So this is counterflow, this is crossflow. As you might expect, counterflow is going to be a little bit more efficient. It's a more physically better way of doing heat transfer, just like heat exchangers are. But there's a lot of other differences. So here's an example of fan control with a single cell cooling tower. Back when we first started doing this analysis, it was the mid-90s when we first started doing it for cool tools for PG&E. Variable speed drives were very expensive. So we also looked at two-speed motors. I bet you guys, young people, have never even seen a two-speed motor. They're pretty much gone because variable speed drives are so inexpensive now, but they weren't back then. So we looked at two-speed motors that were either single winding or two windings, 100 over 50, 2-to-1, or 1/3, 2 down, 100 to 67%. And then we looked at a single speed fan, this is that dark line, and then we look at a variable speed drive, which is the dashed line here. And you'll see that first you get some cooling even when the fans are off, because the water going over the cooling tower fill has a stack effect kind of thing, and some air comes across it just naturally, particularly in the counterflow towers. And you'll see that the single speed fan has much worse efficiency than the two-speed and the variable speed fans. And it turns out that the two-speed fan that is the yellow line here is a little bit more efficient than the two-speed fan that is 1/3, 2/3. But it doesn't really matter because nowadays we use variable speed. Here's the recommendations that came out of our analysis. First of all, one speed control is almost never the optimum strategy, regardless of size, weather, or application, including applications like water side economizers. With water side economizers, you're running the fan at full speed a lot of hours, but it still turns out that there's enough economizer hours that it always makes sense to use a variable speed drive. The two-speed motors are okay with mid-1990 costs, but variable speed drives are now the best choice. The costs are continue to fall. Right now, a variable speed drive and a one-speed motor is actually less expensive than a two-speed motor. So two-speed motors are gone. I'll probably take them out of this slide from now on, but sort of interesting history. Other nice things about variable speed drives, they have a soft start. So if you've ever been around a cooling tower with a single speed motor, right when it starts, the belt starts squealing until it all catches up. So it makes a lot of noise and also wears out the belt. Now with a soft start, the belts last much longer and you don't have that noise. The fan itself has lower noise. Its speed goes down roughly as the square of the noise. The noise goes down as the square of the speed. We have lots of info available if we use BACnet to connect into the VFD. BACnet connections are standard on every variable speed drive. You can connect into them and get entry information like how much power the motor is using. Very nice for calculating what your plant kW per ton is, and you can get alarms and stuff like that. And much more precise control. So we can control the water temperatures very precisely as opposed to cycling fans, which cause the water temperatures to go up and down, which drives the chiller crazy when it's going up and down and up and down. So it's all good. Variable speed drives what you want. Now, if you have multiple cell towers, Title 24 requires that at least 2/3 of them have variable speed drives, but you want to put them on every cell. First of all, it's good for redundancy. You want all the cells to be the same, and you want to be able to, stays them on all together. But also 90.1 requires variable speed drives on all cells. I imagine Title 24 will catch up to that one eventually. And as we talked about before, you want to run as many cells as possible based on minimum flow so that all the cells can have the same speed and you maximize the energy use. As I mentioned earlier, if you have two cells at half speed, they use 1/4 the energy of one cell at full speed and the other one off. So cube law savings, those are good. Now we look at the tower efficiency. What's the tower efficiency? It's essentially how much heat transfer area there is. The larger the box, the larger the physical size of the cooling tower heat transfer surface, the slower the fan can run, the less pressure drop the fan is going to see, and so its energy use goes down. So back in the late 90s, when we first pulled cooling towers into the ASHRAE 90.1 standard, we came up with a metric called GPM per horsepower. And it's the flow rate to that the tower can cool water from 95, 85, 75. Again, it used to be 78, but now it's 75, divided by the fan power. With cooling towers, they always use the entire fan they have. You know, even if it's belt driven, they're going to crank it up so that the brake horsepower is basically the same as the motor horsepower, maybe even a little bit more into the power factor. So the horsepower is basically the brake horsepower. And so that metric describes how efficient the box is inherently. So it has nothing to do with how you're applying it, what your actual temperature conditions are, what climate zone you're in. It's a physical attribute of the box. So in our energy study that we did for the chiller manual, we looked at 3 ranges of cooling towers: a low GPM or horsepower that was roughly 50 GPM per horsepower. These were real cooling towers, so they actually had sort of a range of conditions here. By the way, the Title 24 and 90.1 minimum is like 43 GPM per horsepower. That basically doesn't exist. You can't buy a cooling tower that bad until you get into the biggest box sizes for the cooling towers. And then medium is 70, high is 90. And this is really actually a range of GPM per horsepower. So that's what we target. And what we found was for life cycle cost for a Oakland office building, that the 90 GPM per horsepower was life cycle cost best. So the most efficient towers were so basically double the efficiency that's minimum in both Title 24 and 90.1 is cost effective. So that's the efficiency. And we looked at it pretty much all over, and the big cooling towers were cost effective almost everywhere. Now we looked at the approach. So the approach temperature is how close does that leaving water temperature get to the wet bulb temperature. And what we found is that you can see here, these are all low approach towers here with different chillers, and with this is a 9 to 12 degree approach, 8 to 10 degree approach, 5 to 7 degree approach, and 3 to 5 degree approach. So the more expensive approaches with big delta T's have really high first costs because of the cooling tower. You can see this green line is the cooling tower. It gets bigger faster with the lower approaches. And interestingly, we found in Oakland that the approach that we really should be looking at is a 9 degree, roughly a 9 degree approach. Bigger than most people size cooling towers for in the Bay Area. Most people are buy a bigger tower than that, but that's because they haven't been doing life cycle cost. A data center is a little bit different because it runs all the time, and so there the lower approaches are the life cycle cost optimum. So we did this analysis in all 5 of those climate zones that I mentioned. So here they are over here, Oakland. You'll notice I always do Oakland in my analyses because that's where I live, and that's what I want to know the answer to for my jobs. So whenever we do the analysis, we always do Oakland. We've got Chicago, Albuquerque, Atlanta, Las Vegas, and Miami. So different climate zones here. Later, we redid the analysis with all the ASHRAE climate zones. These are not Title 24 climate zones. These are ASHRAE climate zones. And here you can see, by the way, are the wet bulbs and the CDD50. So what we found was that there's a correlation between the approach plus range. So what's the approach plus the range? That's the approach is to wet bulb, and then the range gets you to the, so this is basically how close does the condenser water return temperature approach the ambient. So it's not the approach, it's the approach plus the range. So it's what's coming out of the cooling tower, out of the chiller into the cooling tower is the variable. Now we know that's the driver variable because that's what is causing the lift on the cooling tower. So it's not surprising that we could only find correlations with approach plus range. And so here's all the numbers you need to do this calculation. So the approach, you can take this delta T over here and put it on this side. So approach plus range equals this straight line. And it's the curve fit is 26 minus 0.007 CDD50. So where do you get CDD50? There's an ASHRAE standard called 169 that has all these data in it. Here's all the ones you'll probably need for designing in the Bay Area, so you don't even have to look it up. But one important thing to know is that you can also get CDD50 off the internet. You can go to websites that will allow you to calculate weather data as well. But don't do it, don't use it, because all this analysis was correlated to the ASHRAE 169 weather data. And I know it's gotten hotter. Our wet bulb temperatures have gone up. And the CDD, the cooling degree days base 50, is a bit, this is, by the way, the average temperature minus 50 degrees Fahrenheit for each day added up for the year. And it's gone up, you know, climate change, it's gotten worse. And so that's true, but this analysis was done based on the old data. And so we can't mix data sets here. So we gotta keep it the same consistency. So use the 169 data when you do this analysis. So that's how you do approach. So here are the guidelines in summary. Is one, always use the propeller fans. Avoid the centrifugal fan cooling towers. Perhaps if you have some high static requirement like a sound trap, like if your cooling tower is right next to some very expensive condos with high-priced lawyers who are going to sue your butt, you might have to quiet them down with a sound trap, in which case propeller fans don't have a lot of oomph, so you might have to use a centrifugal fan. There's also low profile cooling towers that use centrifugal fans, and they are much lower than the propeller fan options. So it does make sense to, I mean, it can make sense sometimes when you have a low height that you have to maintain the cooling tower, is to use those. However, I never do, because A, they cost more, B, they use at least twice as much energy as a propeller fan. And so when the architect says, what's the lowest cooling tower you can get? I don't even consider these, you know, they don't know the answer to that. So they always lie to us about how much space you can have in a shaft and everything. So sometimes we lie back to them and say, well, the lowest you can get is a 12-foot cooling tower, even though there's an 8-foot one that uses a centrifugal fan. Anyway, don't use those centrifugal fan options unless you absolutely have to. They cost more, as well as using twice as much energy. If you do need low sound, all the manufacturers of propeller fan towers have low sound options. In fact, they have two different low sound options, a low sound and an ultra low sound. So you can look at those options. They both cost more and make the tower slightly less efficient. So only do it when your acoustical engineer tells you you have to do it. For efficiency, we shoot for 80 GPM and sometimes a little bit more for commercial occupancies here in the Bay Area, actually for anywhere. And then if you're doing a data center or something that's 24/7, then we go higher, like 100 GPM per horsepower, or even higher than that if you're really pushing the envelope for efficiency versus life cycle cost. And then on approach, use the equation for that previous slide, the CDD50 equation, and you'll note that with the Bay Area, with a 15-degree delta T, your approach is going to be 8 to 9 degrees, not 7 or 8 or so that most people are designing for. So basically, we've been oversizing our cooling towers. And over the country, we've looked at these numbers compared to what the sales are on cooling towers, and we find that mild climates, people are oversizing cooling towers, but in the more severe climates like Miami, they're undersizing them. So it sort of averages out because everybody just uses the standard 95, 85, 78 number, the 7 degrees there, just because it's rote. But for data centers, push it because their energy use is a huge factor given the high loads and the 24/7 operation. Okay, anything more on cooling towers? Oh, sorry, I'm not done with cooling towers. I did want to talk about the flow options. So I mentioned that you want to get low flow so that the cooling towers can operate with 3 cooling towers with 1 pump running, 1 chiller and 1 pump, and 3 cooling towers all running, at least 2 cooling towers running with 2 pumps with 1 of them on. So Marley and BAC are the most popular manufacturers of these cross-flow cooling towers, and they use different things. BAC uses little dams, and Marley uses little cups, but the idea is the same. When we have full flow and the water coming in, the water fills up. It's just a gravity pan. It just fills it up with water, and the higher the flow rate, the more it fills up, because the cups don't let the water go through in the back part of the heat transfer surface area. So the idea is to keep the front all wet, and it's okay if the back gets dry, but the front has to stay all wet, because otherwise, if it's dry in certain parts facing in the 90-degree direction here, going into the heat transfer surface, it will the water will evaporate and the dissolved solids will stay behind, and it'll end up fouling the cooling tower. And also air bypasses the dry spots, so you want to keep everything wet. So that's how this works, is that the little dams, when the flow is low, it just simply doesn't let water go into these little cups. And as I said, BAC uses little dams, sheet metal dams, that do the exact same thing. But the idea is to allow lower flows while keeping the front surface area all wet. And with these little dams or cups, we can end up with the cooling tower going down to about 1/3 of your design flow. Counterflow ones, on the other hand, can't do that. So here's a comparison of the counterflow versus crossflow. Minimum flows, as I said, you can at least get to 40%, usually to 30%. So this means I could do 3 towers and still not have to put any isolation valves on there. The counterflow ones are seldom less than 50%. Even though Title 24 requires that they be 50% or less, I don't know. Everybody cheats is basically what happens. They shouldn't be allowed to do that. Some manufacturers have basically 2 connection points with 2 different nozzle sets so that you can achieve the 50%, but almost nobody buys that. So in a way, the counterflow ones are cheating. They don't meet the prescriptive requirement for the code. So maintenance access. The cross-flow towers have the distribution plants easily cleaned. You just go up the side here, and I'll show you a picture in a second of what that physically looks like. You can clean them out quite easily, whereas with counterflow, I have to first remove these eliminators and then go in through the top of the thing to get at the nozzles, which is quite difficult to do. Efficiency and cost. Counterflow is slightly more efficient for the same cost, but they have higher pump energy, because these spray nozzles use more pump energy than just pure gravity. You pay for the gravity no matter what, but here you have gravity plus the spray nozzles. So overall, they basically have the same efficiency. And then in terms of height and counter footprint, crossflow is shorter, but a larger footprint, usually heavier because they hold a little bit more water in them, whereas counterflow is taller with a smaller footprint and usually a little less light. Here's other considerations, our recommendations. Use crossflow for if you have 3 cooling towers, because if you have 3 cooling towers, we can get the flow down to 30%. And so we don't need the isolation valves. It'll be much more energy efficient. So it eliminates the isolation valves. And then if you have low parapet well heights, it's a lower cooling tower than a crossflow tower, so it's shorter, and that's good. Notice though, if you want to get railings up there so you can climb up here and clean out the basins, these little covers come off and you can clean them out. If you want to have safety railings, you don't have to have safety railings on this, by the way, but if you want to, but they stick up. But you can get safety railings that go on the end like this that don't stick up. Now we only get these when we have cooling towers that are above about 12 or 13 feet. Just a normal ladder, a portable ladder, You just climb, put the ladder against the cooling tower, climb up, and you can reach into these baits. You don't have to stand on the cooling tower to clean these things. So these railings are sort of worthless. I mean, it's very seldom you have to stand on the cooling tower to need the railings. On the other hand, if you have a tall cooling tower and you're next to the edge of the building and it's 30 stories, you definitely want the railings, or people freak out when they're trying to clean the basins. Another things to get for these cooling towers is the internal distribution. So down here on the right, you can get from the factory this internal piping, so that's a single point piping connection. And this saves you the expense of having to support this piping going to the pans in some separate way. And it also is shorter, so it reduces the visibility of those pipes. So definitely do that. Lower maintenance costs for these spans versus counterflow. Get them with the internal walkway. So this little door right here is how you get into them. Inside, you can buy this internal walkway that's just essentially underneath the fan, and you can climb in here and replace the motor and do whatever kind of maintenance on the propeller if you want from there. So that's the pretty standard option. And then for very large plants, it's more cost effective to use the crossflow towers because they're going to have fewer cells and smaller footprint compared to counterflow. So where do you use the counterflows? If I have a very tall parapet or well anyway, because they're taller towers inherently, and you need the tower to be at least the size of the height of the well, so that you don't have air getting pushed back into the well and short circuiting. So these are tall to begin with. So if you happen to have a tall parapet well, it might be an application. And it also can have lower first class for smaller plants. But a very large majority of our plants use cross flow. It's just got too many advantages over counterflow. All right, let's take a 5-minute break. So it is 2:42, and let's take 5 minutes, so it'll be 2:47. So we'll see you here back in 5 minutes. Okay, we are back live. And we're moving on to chiller selections. So this chart here shows the chiller efficiency over here. So this is kW per ton on the left, and part load ratio, the actual load divided by the full load, and then how it varies with condenser water supply temperature as well. This is actually the lift here essentially with in this particular analysis. It's done with a constant water temperature. Basically, the cold water makes kW per ton go down. The low load makes kW per ton go up. So the chiller is actually going to have its lowest energy use when it's at a middle load, and not too low, not too high, and with low lift. So which we'll see when we get into the controls. All right, so chiller selection. The most common approach is people will pick the number of chillers, usually arbitrarily, as limited by the program or the space. 2 chillers makes up. We collected some data when we were doing the chill water manual, and about 80% of cooling plants have 2 chillers. Something like 15% have 1 chiller. And then the rest is multiple chillers, more than 2. So big chiller plants aren't very many. They're huge, of course, often, but they're not very many of them. So most buildings have 2. And why do they have 2? Simply because that provides a little bit of redundancy, a little bit of better part loading, and so that's why they do it. But there might be the sizing of them may not be 50-50, may not be the best way of sizing the plant. So you take the load, divide by the number of chillers, and that's make them all the same. You pick your favorite vendor, whoever took you out to lunch most recently, and then you select their option or have them select options for you. So centrifugal chillers and screw chillers are basically custom devices, water-cooled ones are. So you need the manufacturers to pick them for you. And they'll often pick you one or two choices, usually sort of near code minimum for one of them, and then maybe a really high efficiency one, and particularly a high efficiency one that their competitors have a hard time competing against. To help you dial in the job on them. And then you pick the option based on minimal analysis or no analysis. You might just say, hey, it's a green job. We're just going to pick the most efficient chiller we can, and you don't do any analysis. So that's basically the way it is usually done. A better approach, we think, is to first pick a short list of vendors based on your experience, the owner's experience with them as well. Request the chiller's bids based on performance specification with multiple options encouraged. So most of these chillers are custom. They can have any number, different sizes of heat exchangers with multiple different numbers of tubes and heat transfer area. So you can, when the chiller manufacturers make a selection for a centrifugal chiller, they're going to get 100 selections. And how do you know which one is the best? They all give you the tons you want, but they all are doing it with different efficiencies, different flow rates, different pressure drops, different, it's all over the map. So how do you know which one is the best? Well, the best way is just get multiple selections and then allow the designers to help choose it through a rigorous analysis like I'm going to describe in here. So we get bids. The bids include both the price and the performance. We adjust bids for other first cost impacts. The classic example of this one is open drive versus closed drive. York is the only manufacturer that makes an open drive machine. They also make closed drive machines, but their open drive machines, open means that the motor is not cooled by the refrigerant. And all that heat goes into the chiller room. And if you have that kind of chiller, you've got to cool the chiller room. So you need to put in a fan coil in the chiller room to cool it down that you wouldn't have to do with most other chillers. Chiller equipment loads are usually sort of negative loads. The surface areas are colder than the room is. So the only heat load is the inefficiency of the pump motors, which is very small. So you don't usually need cooling in a chiller room for the room itself, but you do when it's a open drive machine. So you have to adjust for that. And then we estimate the energy use using a computer model of the plant. We do this in our own office in 2 steps. One is we use Energy Plus or CBEC.com or whatever software you're using to generate a load profile. And then we have our own building plant model that models the plant itself, because the control options for the major programs like Energy Plus and eQuest just aren't sophisticated enough to really model the plant the way we want to model it. And then we select the chillers based on life cycle cost. And then this process is done during the design development process after the architects quits fooling around with the windows and you know pretty much what the loads are going to be. At that point, usually in the middle of design development, that kind of stuff freezes, and you can say, fine, the chillers aren't going to change in capacity. Let's pick them now. You don't have to pick them in. You can also pick them after the design is over, after it goes out to bid. So if you want, but it's best, the best flexibility is to do it during the design development period, because then you can design around the chiller you select. Once you select the chiller, you hard spec it. And I'll show you sort of an example how to do that. You say, hey, the bidding's done on this chiller. We already bid it. Here's the price. Here's including freight to the job site. Don't bid any other chillers because this is it. We already bid it for you. Again, you can do this after the fact as well by just stipulating what the chiller price is and then pick it later after the contractor's already on board. And this works both with design build or plan and spec. The chiller specification is try to be as general as possible. For instance, don't specify the number of chillers, the chiller size, the chiller efficiency, and the unloading mechanism, meaning variable speed, as much as possible, because you want to look at all the options and see which is the best. So what you do specify is, of course, the total load. We do that. You give them an example of the load profile so the bidders know if there's lots of low load hours, they need to select chillers that can handle those low load hours. You specify the minimum number of chillers and any other kind of redundancy, N+1, that kind of stuff that you want to do. You specify the entering, leaving water temperatures for the both chilled water and condenser water. Sometimes you can do this with condenser water as a table of rates. Basically, you pick a cooling tower and then you select it at that same cooling tower at various conditions, and allow the manufacturer to decide what works best for them. Available energy sources use electricity. We did have a project at the Fairmont Hotel in San Francisco where the power was very limited. Their service was very limited. So we ended up having to use high temperature hot water for one of the chillers, basically absorption chiller with high temperature hot water. And so that limited the sources there. Any other constraints, physical, if you think the room is tight, include a layout of the chiller room so that they have to fit it all in. Acoustical constraints, usually not a problem because we're good about putting the chiller plant not over the boss's office. But if you have acoustical constraints with blankets or any other things that you may need, include that. Acceptable refrigerants, early on, that was an issue when LEED did not give credit for R123, which is the refrigerant that Trane uses. And later on that changed, so it didn't matter. Well, now we're back to also limiting refrigerants because come January 1st, just a few weeks away, the rules are going to change. And we now are going to have a list of refrigerants that are different from the ones we've been using for new chilled water equipment. And then the rest of the spec is your normal stuff for your chiller spec, just what you already have in there. So you want to limit, you don't want to over specify as much as possible. For damn sure, don't say what the efficiency is, and don't say what the unloading mechanism is. Let the contractors or the bidders give you all the choices there. Remember, I said when you pick a chiller, you're going to get hundreds of selections. Let them pick 2 or 3 or 4 of them, and then give them to us to analyze, to figure out which one's best. Here's a sample load profile. You get this out of the eQuest or Energy Plus run. This is very typical of a building. This is a 600-ton nominal building, but in fact, the load never gets above 500 tons because the real life loads in our load calcs are always less. We always have lots of low load hours because of economizer. So with a lot of hours between 60 and 70 degrees in the Bay Area, that generates very low loads. It's not cold enough to run on economizer entirely by itself, but not warm enough to really load up the chiller. So it's very typical. And then we have a thing about not allowing tolerance to be taken in accordance to the ASHRAE rating standard. So ASHRAE 55590 is the rating standard for chillers, and it includes the provision that allows the manufacturer to take tolerance into account. So tolerance is meaning that if I say the chiller is 0.5 kW per ton, it can really be bigger than that. It can be less efficient than that, and it's okay for me to lie, to claim. And the purpose of the tolerance was there because originally the centrifugal chillers, the impellers were essentially hand tooled. They would put them on a lathe and grind them down and make them work. And so the getting the right exact size repeatedly was poor. Nowadays, of course, everything is precision tooled, and there's no real reason for this tolerance. But it's in there, it's been in there for the standard, and the manufacturers don't want to get rid of it. So why do you want to insist on zero tolerance? Well, it levels the playing field because not all the manufacturers lie consistently. I'm sorry to say the word lie, but quite frankly, it's really true. I mean, they're just totally misleading you. Not that the other manufacturers of other products don't do the same. The VRF manufacturers are even worse. But anyway, all the manufacturers are going to push the rating standards as much as they can. That's their job, right? To sell equipment for the lowest price. It's just not good for us. And so your model energy cost will be more accurate if you have the actual performance. And what the tolerance that they're allowed is bigger at lower loads. And so it can often make a chiller look like a 500-ton chiller look like it'll be efficient doing 50 tons. Well, it's not going to be efficient doing 50 tons in real life, but with the tolerances, it can make it look like 50 tons. So here's the tolerance curves. And you can see at low load, 10% of the load, I get to add to cheat by 20, 25%. And so I can make a chiller that it says it's operating at so many kW per ton at 10% load, and in fact the load is 25% bigger than that, or the energy use is 25% bigger. So that's why the zero tolerance. Now it's difficult to get all the manufacturers to give you the data on that. They often have to go back to the factory to enter a super secret password into the selection software, the lie, don't lie switch. So it can be sort of a pain, but you can see why it can make a real difference on the analysis. Enforcement. It's a good idea to do a certified test, particularly if you have the performance is critical, like a data center or something like that. We'll always do certified tests. It's tougher on a typical building because it costs money. The owner doesn't necessarily want that, but you can't test in the field. You can't, the accuracy, think of it, you got to measure flow, both condenser and chilled water flow accurately, the delta T across the two accurately, or the absolute temperatures accurate. So it's 4 temperatures, 2 flows, and a kW, all of which have errors in them. And the errors in the field are always much bigger than the errors on a bench test in the factory. And so it's really impossible to do in the field. So if you want to do a guaranteed performance, you need to do a factory test. It's sometimes good to get a price for a factory test and threaten to do a factory test, but then not do it, so they at least know that there might be some comeuppance if they cheat. And then if they do the factory test and they fail to meet the efficiency requirements that they said they were going to meet in this analysis, then you can hit them with a penalty. So we have clauses in our specs that say, if you don't meet the kW per ton, here's what you pay the owner. Either that or fix it. Either repair the chiller, because remember it's still in the factory at this point, or you pay the owner money back on what they paid you. So here's what the chiller bid forms are. The yellow fields are what the vendors put in. The white fields are fixed, and then the gray fields are calculated in the spreadsheet. So you can see you put all the important data in there. And then there's a tab for full load data at various flow and temperature conditions. So you can see the evaporator temperatures are changed, the condenser water temperatures are changed. And then there's a part load conditions spreadsheet. And from the data in these 3 tabs, there's a 4th tab that calculates what the model is. So both the DOE2 models, the old models that are in eQuest, and the Energy Plus models, they create a regression analysis curves that are a function of these water temperatures and loads. Again, we take the bid evaluation, we adjust the first cost as I talked about. Maintenance costs. Maintenance costs are tough because all the manufacturers hide the data. They don't tell you what their maintenance costs are. You don't know what manufacturer has the best maintenance thing. Everybody claims they have the best, and there's no published data on this at all. And General will treat the chillers of like kind of having the same maintenance costs. Since we don't know, we just don't do anything. So we treat all centrifugal chillers the same. We do know that screw chillers actually have a lower maintenance cost than centrifugal chillers. So we might, if it's not an explicit cost advantage, we keep that in mind as one of our soft factors in making the selection. We also think that magnetic bearing chillers will have a lower maintenance cost overall than standard bearing, although we just don't know that yet because they haven't been around quite long enough. We use the energy model to calculate the building load and energy costs. We calculate life cycle costs in the normal way with discount factors and escalation and whatever for energy utility costs. Once we get the analysis done, we look at soft factors, and I'll explain that in a minute, just using an example. And then finally, we select the final selection. Once we make a selection, we flat spec it, so we don't accept any more proposals later on, so that the manufacturers, this is their one and only chance to be a part of this process. And if they want to be a part of it, great. If they don't, they can't come in later and say, oh, we'll give you a price now that it's all over. It's too late then. So in the spec, we will set, or on the schedule, we'll just say, no, we'll list the actual chiller we selected. We'll say no equal, and the marks column, we refer to the specs. The specs will have nothing in part 2, which is all the materials section, because we've already bid that part. That was part of the how we got the chiller in the first place. We don't want people to use it to create another bid. Retain all the part 3, because we still got to install the thing. And in part 1, we say what the chillers cost. So we say, here's the chiller cost right here. They include freight, but not taxes. Bids for other chillers will not be accepted. So it's flat spec'd. Here's an example. This is one, the second or third project that we did using this approach. This one happens to have pump coils, by the way. It was an example I showed earlier with some pump coils, and as well as some standard primary, secondary. And it had 2 chillers, but we didn't, or 2 or 3 chillers. We said this one, we didn't even tell how many chillers there were. But it did have a small data center. So one of these loads over here was a small data center that ran 24/7. So we had a lot of low load hours on the building. And we gave the manufacturer the leeway to do any number of chillers they wanted, any size of chillers they wanted. We just made it a blank slate. And they did what they did, and then we did the analysis on it. So you can see that some had, a couple of them had 3 chillers. And then this is the early days of variable speed drives. This is in the late 90s. So we had some with variable speed drives and some not. Nowadays, everything's got a variable speed drive on it because the costs have gone down so much. So we list them all here. We do a life cycle cost rank, our first cost rank just for interest. We do an energy cost rank for interest. We calculate the life cycle cost, and then we rank them. So here you can see that the lowest life cycle cost was this one, but the one we selected was this one in there. So it's 2 unequally sized chillers, 50, 1/3, 2/3. Both of them had VFDs. It came in second in the life cycle cost and 8th in the first cost rank. But we selected that one because it wasn't the lowest life cycle cost, but we picked it anyway. The reason why was because it was close in life cycle costs. So you can see that it was $8,000 over 15 years. That's basically nothing. You know, we all recognize that these calculations have a lot of error to them. You could just change any of these assumptions for escalation rates and everything. By the way, the electricity escalation was 0. This was made when Enron was telling us that we were not going to pay for more electricity because we were going to go with an open system. So much for that lesson. Ended up being 10% instead. So we know there's lots of slop in the assumptions. So we generally treat the life cycle costs as the lowest 2 or 3, you know, are sort of considered the same, because we know that you just change an assumption and you can flip them. The carrier one used R134A, and at this point, York had R123 chillers as the Train at that time. York eventually stopped making that chiller. Remember, this is late 90s. And then both the chillers had variable speed drives, which we liked for the soft start capabilities as well as energy. And then the small chiller can operate with the larger flows. So we had each chiller had pumps. The pumps were headered, but we had 2 constant speed condenser water pumps, and one small one for the small chiller, one big one for the big chiller. But the small one could actually make the big chiller work. Whereas with the York, they made such a big difference in load between the two that the pumps for the small chiller couldn't make the big chiller work. And so that was a big disadvantage. Since then, we've actually made the bid form such that they can't bid a chiller where the pumps don't work with each other. We want that redundancy. And then the carrier was hermetic and the York wasn't. We have I have a prejudice against open drive compressors, not only because of the heat that goes to the room, but also because there's a little oil cup that sits under the coupling between the motor and the compressor that drips oil, and it's like, I don't want a chiller that drips oil. So anyway, and then also that Carrier had the lowest cost. So between the two. So one thing you know for damn sure is the cost, and the first cost, and all the rest of it is speculation. And so when it comes right down to it, when there's close choices, we will almost lean towards the first cost because it's the only thing we know for damn sure. The rest of it is a guess. All right, so advantages and disadvantages over just winging it. It's extra work for the engineer and the vendor. Takes a lot of time to fill out those forms. Difficult to include maintenance, as I mentioned. Assumes the energy rate schedules will remain, and we have some simplistic adjustments for escalation, and we have to guess what that number is. So the future of the thing we don't know well. That's true of all life cycle costing. Advantages, it allows the manufacturers to find their own sweet spots. That's good. Usually we get a higher efficiency than the lowest cost machine, so it ends up pushing the owner towards a better, higher energy efficient project. And lastly, this one doesn't make a lot of sense, but it does to me. It's just more rational than making stuff up. You can probably tell by all the analysis that we've done and all these things, I can't stand just making shit up. And so we like to do analysis, and just winging things is not good enough for me. So I like having a process that has some rigor to it. Now, this takes a lot of work. So we created a new procedure called the simplified procedure. And this is described in a paper that's on our, we called it the value-based selection of equipment. It applies not just to chillers, but also any product, cooling towers, air handlers, anything. And the idea is similar to before. Once the loads are confirmed, then we can bid it out. And we can also, I'll talk a little bit later about what you can do if you don't want to bid it out during the design. You can bid it out after design is bid, like you might on a design build job. So we have the manufacturers complete a simplified form. The form is much more prescriptive than the previous one because we don't want as many choices. We want to make it a lot simpler. We might have, for fun, we might include two forms. One if the plant had the chillers 50-50, and one if they are 1/3, 2/3. If we had a lot of low load hours, like we have a small data center or something like that, we might do 1/3, 2/3 to accommodate that. And we might want to look at both. So we'll get pricing on both options, but it's a lot more prescriptive. We send the forms to the vendors for pricing. The pricing is based on just their normal selection software. We don't make them do zero tolerance because that's much harder to do. It doesn't come out of their normal stuff. And the whole idea is to make this simple for everybody. All the data in the forms they can get from their normal selection software without doing any extra work. And then we base the selection on first class and a subjective judgment of energy costs. So we're not going to do a detailed energy model. We're just going to look at the factors that affect energy efficiency and make some judgment calls. And then, as before, we flat spec the chiller. Also, as before, I mentioned this a couple times, but let me reiterate it. If you don't want to bid the project out during the design phase, we can also do this later. What we do is we select a couple of chillers and get a local manufacturer, one of your manufacturers, doesn't matter which, to provide a budget price for that chiller, for those chillers, and you simply stipulate that they use that amount that in the bid, and then we can analyze later do the analysis, this whole thing with the contractor already on board, and then if we decide to use a different option than what was stipulated, we have the pricing and we know the difference, and you can simply adjust their contract price by that amount. So here's what the simplified form is. There's actually more fields on this, but they didn't fit on the drawing. We're happy to share these forms, by the way, if anybody wants to use this approach. Well, just send me an email and I'll send you the form. So here's an example. Again, this isn't all the fields, but we knocked it down to a few that so we could do an analysis. So here's a project that had 2 chillers. and they were 300 tons each. And we got 300 tons is an interesting size because almost everybody makes something that does 300 tons. So you can get screw machines, centrifugal machines, open turbo core, that's a modular magnetic bearing machine. You can get lots of different choices with this size, and you can see we did. So we have a screw machine here, a magnetic bearing centrifugal, an open drive standard bearing centrifugal, the modular turbo core magnetic bearing centrifugal, another magnetic bearing, and a screw as well with variable speed drives. So all of them had variable speed drives. You'll see that on pretty much all chillers nowadays. They'll have variable speed drives. So you look at this and say, great, what do I do now? So what we do is we say, okay, what's important? Well, let's eliminate a few. Okay, so first of all, I'm not a big fan of open drive centrifugals. If the open drive centrifugal is there, I need to add some money on there. So this is actually the cheapest machine, but I got to put 10 grand in for a fan coil to cool that room. So now it's no longer the cheapest machine. And then we have this turbo core one is $318,000. Everybody else is around 200 something. So it's way more expensive than everybody else. This, by the way, is very typical. We've never selected a turbo car job yet. They're always has something wrong with them. And then the one on the right has very poor unloading, and it only goes down to 20%. The minimum primary, this is a variable flow primary system. The minimum flow rate was 93%. That's basically constant flow. You know, that's just unacceptable. And then it had the highest NPLV. So of the efficiency numbers, kW per ton is the full load efficiency. That's sort of important. What's really important is the NPLV. That's the non-standard part load value. It's essentially the annualized value. Not a great metric for true part load performance, but it's way more reflective of efficiency, annual efficiency, than design kW per ton, because we're always at part load, right? So full load kW per ton is seldom really an interesting number for us. So we look at those numbers and say, okay, what about good things? So the square boxes are around good things. So this is a good low price. That's a good low price. Here's some good unloading capability. Here's some evaporator passes 2 versus 3. When you lay out a chiller plant, you'll see that when I have to have 3 passes, I end up with the pipes on the other side of the chiller coming in or out, and it adds to piping costs a little bit. So that's a soft factor saying, hey, this is going to make the piping cost less if I have 2 passes versus 3. Here's some low pressure drops on the chill water side. That's all good. And here's some variable flow low numbers. So while these were too high, these are good and low. So you want it to be 40% or so as a minimum turn down. By the way, we have very high delta T's here. You can see a 25-degree delta T. So the turn down may be less than you might see in other jobs because we already started with a small flow rate in there with a big delta T. Condenser water pressure drop's good, and then we have the lowest NPLV over here, and the lowest kW per ton over here. So we have squares and circles, and what does that tell us? Okay, let's just eliminate a few things. These two are eliminated because the right-hand one has just very poor unloading capabilities, inefficient, lousy choice, never mind, not going to do it. The turbocore run was just too expensive, so we get rid of that. Okay, what else? Well, this one, once we add the 10 grand for the fan coil in there, it's no longer low anymore, and option number 1 is better at everything else. So that eliminates that one. So we end up with 1, 2, and 5, and 2 and 5 are mag bearing centrifugal chillers. That's good. 5 has some pretty good numbers over here, but it has very poor flow unloading over here, and it had the highest full load kW per ton. So sort of in my mind, I'm thinking, okay, 1 or 2 are going to be the choices that we make. So which is it? Well, we picked 1. Why? Because it cost the least. Okay, $206,000 versus $238,000. So it has the lowest price, and again, the price is the one thing you know for sure. And option 3 we eliminated because of the open drive on the thing. So it was no longer the least expensive. It's likely to be the most energy efficient option because it has the lowest NPLV and it unloads well and it has good turn down. So we have good turn down on the evaporator. It has the lowest NPLV and it has very good unloading before it cycles. So that's somewhat offset by higher pump energy. So it had somewhat higher pressure drops on the evaporator and the condenser. But remember that the evaporator flow is the evaporator is, well, first of all, these two had very similar numbers between the two. Remember, we're going between 1 and 2. But also this is cube law stuff here too, right? That we're not going to pay that penalty all the time. We have variable flow. It has screw compressors, where they're generally less expensive to maintain than centrifugal compressors, especially centrifugal compressors without mag bearings. Now the second one choice does have mag bearings. So between the maintenance costs here, it's sort of a wag. It's, you know, we think that this screw is still going to be less expensive to maintain. So that's why we made it. Now, the last comment here is that we would have picked the mag bearing one if it was a different kind of plant. If I had a plant with a water side economizer, I definitely would have picked option number 2. Why? Because of this value here. Minimum lift at minimum load is 0. So that we can run the water side economizer as hard as we can and also run the chiller without any head pressure control. So that's a good thing. But this particular plant didn't have a water side economizer, so that consideration was not there. Another reason with water side economizers is mag bearing chillers with variable speed drives can cycle a lot without hurting themselves. And we end up with a lot of low loads when we have water side economizers, where we're just trimming what's coming off the heat exchanger. And so you can cycle them a lot, and that's good, and not good to cycle screw chillers. So that would have changed our mind had this had a water side economizer. So that's how you do it. So it's a lot of subjective kind of stuff, not as comprehensive, but it's a lot better than being arbitrary. Still allows us to design around a specific chiller if we do this during the design phase. It's easy to bid for the vendors because they don't have to get any data from the factory. There's no zero tolerance stuff. Everything that is in the forms is something that they can get out of their selection software very easily. It's easier for designers because we don't have to do the energy modeling. On the other hand, it can be difficult sometimes because it's partly subjective, you know. So we end up having to, you know, make subjective calls, just like we did in this example. Lots of choices. Now this is all explained in this link here to value-based equipment selection. We do this for all of our jobs for all equipment. It's a good idea for chillers, cooling towers, custom air handlers, heat pumps. We're now into heat pumps. If we were doing boilers anymore, we'd probably do it with boilers, but not doing much in the way of boilers these days. All right, any questions? Okay, moving on here. So now we're going to get on to control sequences, and it's difficult to optimize control sequences, again, because as we talked about at the beginning, there are so many different variables in here, and all of them will affect how you control the plant. So for instance, if I have a really efficient cooling tower, I may drive the water temperature down colder and get some energy savings on the chiller. But if it's not a very efficient cooling tower, I would want to do that less. So there's just all these variables to deal with. Too many independent variables to just arbitrarily pick something. You've got to do some analysis to make it work. So what is the optimized sequence? And once we find an optimum through analysis, can we generalize it so that it applies to different plants, so I don't have to do a deep dive analysis every single time? Can I make the sequences simpler? So what we did was we took a generic plant, 1,000 tons. As I said, about 80% of plants have 2 chillers, so we went with 2 chillers, 2 towers, 2 pumps. We put everything on variable speed drives, except for the condenser water pumps, which are optionally variable speed, because as I talked about, we may or may not want them to be variable speed, and I'll explain to you why. So the models are chiller models that we developed that are now being used in Energy Plus, and we calibrated them to some real chiller data. And then cooling towers, we used the DOE 2.2 model, which is also used in Energy Plus, calibrated to the manufacturer's data. Pump models, we assumed that flow varied with the GPM to the 1.8, not quite turbulent flow. We used real pump data with real pump curves and regressed off of them. And then motor efficiency data that we got from manufacturers. So we create this model. We first run DOE2, which is eQuest, to generate a load profile for the building. So we have simultaneous flow, water temperatures, dry bulb, wet bulb, put it in a big database program, go into a visual basic model of the chill water plant that we wrote. And it then the output of that goes into a database where we have all the operating points done. So our visual basic model is iterative, and it goes through and has nested do loops or for loops, whatever you want to call them. So we look at every possible combination. So we say for one to the number of chillers, same with cooling towers. We look at the cooling tower fan power from 10 to 100%. We look at the condenser water flow from 0 to 100%. We do all this kind of stuff, nested loops, where we look at every single possible combination of operating condition so that we can know that whatever we come out of the model, we've looked at it. And so the runtime takes a long time. We had to divide it up into several computers to get the runs done, because we also were looking at 5 climate zones and a whole bunch of other stuff in there. So all the runs took a lot of time to run, and that was just for the computer runs. And then, of course, if you had a bug, you had to start over again, which was really, really frustrating. So we spit all that out into a database. We have all of the data here. Now we query it and say, what is the least amount of energy each hour? And that is what we call the top, the theoretical plant, optimum plant performance. And so this is the best you can do. And we know it's the best you can do because we've looked at every possible operating condition. From that, we start just plotting things. And we look at this versus that and this versus that and try to find correlations between the top, what conditions made the plant the most efficient versus the independent variables like weather conditions and load and things like that. From that, we develop a control sequence. The control sequence can then go back into the database and model the actual control sequence and then see how well we did. So we know what the top is, and then we know how our actual sequence can do because all these points are there. We just say, here's the data points that the sequence would have selected. And then, as I said, we plot them against various things. Once we figure out what the independent variables are that really determine performance, we look at correlations, and then we test the sequence to see how close to the top we get. So here is what we get our results are. First of all, so let's go on from there. We learned a lot from this, and I'll tell you what the results are as we go through each of the components of the plant. So first, for primary pumps of a primary secondary system, if it's we stage the pumps with the chillers. This is the primary pumps, remember. If we have speed control, because remember, one of the options on a primary secondary pump plant is to have variable speed drives, then we'll maintain the chill water supply temperature and vary the flow down, looking at making sure that the primary flow exceeds the secondary flow just by a lot, or ties the secondary flow. And then we'll make sure that we maintain the minimum flow through the chillers at their minimum speed. So we're basically going to try to track the secondary flow, stay just a little bit above it, and we can do that with flow meters or with temperature. And then, but we stop reducing flow when we get to the minimum flow needed for the chillers. So that's variable flow. What about the primary only pumps or the secondary chill water pumps on a primary secondary system? The top model, again, we correlated. This is the optimum number of pumps. If we try to find a correlation with speed, you can see that with speed, the optimum number was 1 or 2 in a broad range here, from about 55% to 75% or so. Sometimes it was 1 pump and sometimes it was 2 pumps. We can't tell. But what happens if we correlate against flow? Then it's quite clear that we correlate, but when we're less than about 47% of design flow, it's 1 pump, and we're above that, it's 2. So most people stage pumps off of speed. When they max out a pump, then they turn on the other pump. Well, it turns out that that isn't right, because what happens is your pump that when you're running 1 pump and you run it out to 100% speed, it's way out on its curve, and the pump efficiency is not efficient there. It's better to keep the pump closer to its selection point where its efficiency is higher. So we stage off of speed so that off of flow, so that the pump stays home where it's most efficient. So the logic then is 1 pump less than 47, 2 pumps greater than 47. We don't put a deadband in here. We put in short cycling timers in there. This is typical of guideline 36. Rather than have a delta in the flow variable here, which is a surrogate for short cycling, we say, why don't we just put timers in for short cycling? Don't let it change from 1 to 2 or 2 to 1, except unless it's run for a while first. And that way you don't have to make arbitrary choices of how much deadband you want in these things. So this was one of the things that came out of the top modeling, is how to control the pumps. Then how do you control the speed of the primary pump or the secondary pumps? First of all, straightforward on that one. You put the DP sensor out in the system. The further you can put it out, the more energy efficient it will be. 90.1 actually requires that the DP sensors be put out at all of the end of the remote circuits. Title 24 doesn't really address that, but the further out you put it, the lower the set point can be, and the more energy efficient will be. Now we do DP set point reset based off valve position, which we'll discuss in a minute, and that generally means that you can put the DP sensor anywhere because we're going to change its set point. However, as I'll discuss in a minute, when we have pressure dependent valves, you can't really decide whether a coil wants more colder water or whether it wants more pressure. So you have to use those valve requests to do one or the other, reset the DP set point or reset the chill water set point. And because chillers use a lot more energy than pumps, we choose to reset the water temperature first. And that makes it more important to get the DP set point as low as possible. So do put it way out into the system as much as you can. And then sometimes that's way out in the system, or if you have a campus, it's clear in another building. So what you do then is you put 2 DP sensors in. That's what this last thing calls for. Is you put 1 DP sensor in the plant, and you control the variable speed drives to it, but you reset its set point based on remote DP sensors that are connected at the end of the network and pass their information through the network. So one of the controls rules that we talked about earlier is that the control point, the control device, and the control loop have to be in the same controller. If you put a DP sensor way out in the building, you have to home run it all the way back to the plant to make sure that you don't violate that rule. But by cascading the loops like this, you can get the same energy benefit without having to have such a long wiring run. And guideline 36 has logic for both situations. So here's the reason why you want to put the DP sensor way out into the system. If you're just riding the pump curve, that's what this line looks like. So there actually is some, excuse me, not riding the pump curve. This is if I have the DP sensor right at the discharge of the pump. So you still get some energy savings because the flow is varying, but you don't get any energy savings from the head going down. The further out in the system you set it, the lower the set point can be. And then, so the blue line is if you put it 2/3 of the way out the system, like people talk about. And then the bottom line is if I had perfect reset based on valve position, We never get there because, again, we're going to reset the water temperature before we reset the DP set point. So we're almost always at the design DP set point with the guideline 36 logic. Chill water set point. Reset impacts. So chilling water reset will reduce the chiller energy, but it increases the pump energy. So that's a bad thing. However, it almost always ends up resetting the chill water energy less. So again, chillers use way more energy than pumps, and chiller efficiency is very much dependent on the water temperatures, the lift. And so while you do lose some of the energy savings from the chiller by increasing pump energy, you end up with a net savings. Now, a lot of people get concerned about resetting water temperatures because of dehumidification. We don't care about that here because we have such a dry climate. That's only true if you have a reset that uses open loop logic, meaning if I'm resetting, say, off of outside air temperature, it's possible in that case, when you're not looking at what's happening at the coils, that you might starve a coil. But if you're resetting off valve position, it can never hurt dehumidification. Why? Because we are at that point, if we're maintaining that each valve is never going to be, wide open, we're always going to keep it just near wide open, but not fully wide open. We know we're maintaining set point, supply air temperature set point. And if we're maintaining supply air temperature set point, that's what determines the dew point of the air leaving the coil. The water temperature doesn't. So experiment this with a chill water selection program, a coil selection program, is select a coil, then reduce the airflow so you're at a part load condition, and then fiddle with keep the leaving air temperature the same, say 55 degrees, and then change the water temperature set point, make it warmer, and you'll see that the dew point temperature or the wet bulb temperature, whatever, the combination of the two, look at it in a seg chart, is not going to be very different. The water temperature doesn't make much difference. It's the air temperature that controls the humidity. So you basically are never going to starve a coil of dehumidification if you reset off of valve position rather than some indirect thing like outside air temperature. So the logic is to reset the valve, reset off of valve position using trim and respond. If you don't know what trim and respond is, take the UC Berkeley class on controls, and it'll tell you what that is. It's a little hard to explain. And then for variable flow systems with variable speed drives, we reset the chill water, we sequence resetting the chill water set point and the DP set point to each other. They're not independent like VAV boxes. So VAV boxes, you might be familiar that guideline 36 logic resets both the supply air temperature off the air handler and the DP set point of the fan. It can do that because there's two loops at the zone level. We have the room loop that sets the CFM, and we have the damper loop that delivers that CFM. The first can reset air temperature, the second resets DP set point. But in a system with pressure dependent valves, again, we don't know whether the coil is starved of cold water or starved of low pressure. So you just don't have any choice on that one. So we reset them in sequence, and here's what it looks like. The chill water set point, we basically have a loop that's resetting. The output of the loop is 0 to 100% off of trying to keep essentially one valve wide open. And as the load goes down, we first reset the chill water set point as much as 15 degrees. And if we can still go down, we'll reset the DP set point. However, you basically never get there because at some point, 15 degrees plus T-min, so T-min is like, 42, 44. By the time, this is going to be close to 60, chances are you're starving the coils of water temperature before you even get to the DP point, which is why it's important to make the DP set point as low as you can by putting it out into the system as much as you can, because the reset just doesn't happen. Now, if you had constant speed chillers, which are less beneficial, the chill water reset is less beneficial for, and if you have very high pump heads, you can reverse this. Put the DP set point line over here, and the chill water set point line over here. So it makes a V shape instead of a pyramid shape. and you'll probably be better off. But 99.99% of the time, you don't have that, right? You've got variable speed chillers, and you've got lower pump heads than that. And so the water temperature set point makes sense first. By the way, water temperature set point also reduces losses from the piping. So that's a second good reason for using it. So here's the analysis that led us to this conclusion. Here's Houston. This is energy costs, energy use rather, using chill water reset with a fixed DP. Here's a 6 chill water set point with DP reset, and here's both of them combined. You can see that the chill water set point reset did most of the energy savings. The pump savings on top of it is very minor because we very seldom get there. But resetting the water temperature is better than resetting the chill water set point first. Same in Oakland, where the water temperature reset is best. DP set point doesn't do that much. Doing both, you can barely tell it from just doing the water temperature as well. And this was for a plant with very high pump head, but it had variable speed chillers. All right, moving on to control sequence was for cooling towers. So we used our top model to try to find correlations of condenser water supply temperature with wet bulb. You've probably heard of people using wet bulb temperature to reset chill water, condenser water supply temperature off the cooling tower. And in fact, in really humid climates, it's not bad. So what these dots are is these are the number of times that this is all the top conditions. These are the conditions that produce the lowest energy use of the plant. And you can see it's a pretty good straight line, 0.927 R squared, not bad at all. So this looks like, wow, in Miami, we should use water temperature, wet bulb to reset water temperatures. Well, in Oakland, the R squared is 0.01. Basically, there's no correlation at all. And we found this on all of the climates except for the humid climates, where wet bulb was just simply not a good indicator of how to reset water temperatures. Instead, we found a correlation with lift. Not surprising. Lift, again, is what drives the chiller's efficiency. So if you look at the Carnot efficiency of a machine, of a refrigeration, it's driven by the lift. And so lift is leaving minus leaving. Condenser water return temperature, what's coming out of the condenser, minus what's coming out of the chiller. And we look at that, and you can see that there's some pretty decent straight lines here, pretty good correlations. So we found that for office buildings, that the lift and load variation correlated quite well. Percent load on the bottom versus lift. If we know lift, then we can determine what the condenser water return temperature is. So if we know what the straight line is, we can solve for water temperature, and that's how we can cool our cooling tower. So data centers, it doesn't work so well though. Why? Because data center, the load has like nothing to do with the weather, right? It has everything to do with what's inside. So with data centers, it's better to use wet bulb. In very humid climates, it's better to use wet bulb as well, like Miami. But Guideline 36 trying to be generalized said, well, most climates, it's going to be lift versus load that correlates. So the logic then is to make a straight line of lift equals this is a straight line, like slope times, this is y equals mx plus b, right? So A is the slope, that's x is plant load ratio, b is the intercept, and we can do curve fits based on these models. Draw a straight line and regress it. And you'll notice that we're going to control to the condenser water return temperature, not the supply. So we actually are controlling with what's coming out of the chiller going into the cooling tower. That correlates because that's what the lift is defined as. So let's calculate the set point as the lift that comes out of the equation, this equation here, add it to the water temperature that we're delivering, and that's our set point, and we control the water temperature to maintain that set point. Now, occasionally the cooling towers and the chillers are separated by a long distance. If they're right next to each other up on the roof in the penthouse, no problem. But if the chillers are in the basement and the towers are on the roof, because of the time delays, this will be unstable. So we do, again, like we did with pressure, is we do a cascading loop, is we control the tower to its leaving water temperature, but we reset its set point based off of the return water temperature loop down at the chiller plant. Again, this is all covered in guideline 36 logic. So what are A and B? You can determine A and B by these curve fits if you do the modeling, but of course you're not going to do the modeling. So we did a lot of analysis to try to find is there a way of simplifying this? Is there a way of calculating the A and B coefficients without doing any modeling at all? And what we found was a decent correlation was to calculate 1.1 times the design lift minus the minimum lift. So the minimum lift is that one that is the minimum lift at minimum load that I pointed out to you was 0 for magnetic bearing chillers, but it's something non-zero for others. And it can be quite high for a screw chiller, like 20 degrees or so, the minimum lift. So that's the minimum lift. The design lift, of course, is your design conditions, condenser water return temperature minus chill water supply temperature design. And then B is lift design minus A. So these numbers are very readily calculated. You just have to ask the manufacturer what their minimum lift is at minimum load, and you can get this number, and that's the curve. There's another tower control option that's really quite beautiful because it doesn't rely on any regressions or any simplifications. But it also only really works on plants where the chill water supply temperature and the loads don't move too quickly. So the perfect example is a central plant, a cup. If I have a plant that's serving all these buildings in, at a UC or CSU campus, the loads don't change very quickly. And so what I can do is try to optimize the condenser water set point dynamically by maximizing the plant efficiency, adding the cooling tower energy to the chiller energy together. Now you'll notice there's no condenser water pump energy in this because I'm assuming that the condenser water pumps are constant flow. We'll talk about that later. It doesn't work really well it doesn't work at all if you're varying the condenser water flow too. So with constant condenser water flow, we're going to try to optimize what temperature set point maximizes the efficiency of the tower and the chiller together. So the efficiency is equal to the kW of the towers. We get that through the variable speed drives. And the kW of the chiller, again, we get that from the chiller variable speed drive through BACnet. So these are both through BACnet. Divide by the actual load, which is, the actual load, flow 500 delta T. And that's the efficiency. And so I won't go through all the steps here, but basically we try inching in onto the efficiency. We drop the water temperature and we see what happens. If we drop the water temperature and it makes the efficiency go up, we say, good, let's drop it again. If we drop the water temperature and it makes the efficiency get worse, then we say, oops, wrong direction, let's go the other way. And of course, we do this very slowly, half a degree at a time, and we wait to see what happens. So that's basically the logic. And it really works quite amazingly well. We can find, without any knowledge of the efficiencies of anything, we can optimize how the tower and the chiller go together. But again, it only generally works on a cup where everything changes slowly. Because remember, the efficiency also of the chiller has to do with what's happening on the other side, which is the leaving water temperature. And if it's being reset very quickly, then it screws all this up. There's too many independent variables in that case. Okay, condenser water pumps. I've alluded a couple of times to constant speed versus variable speed. If they're constant speed, it's easy, just stage them with the chillers. If they're variable speed, we can stage them based on flow, just like we do chill water pumps. But do we want to put a variable speed drive on a condenser water pump? Here are the issues. One is, what's the control logic? With a variable speed drive on almost anything, it's hard to make it worse than constant speed, right? You put it on a fan, and worst case, even if it's a constant volume fan and it's not really varying speed, the energy use is maybe slightly worse because of the inefficiency of the drive, but really it can't be much worse. That's not true with condenser water pumps, because as the flow goes down, the leaving water temperature from the chiller goes up, and that makes its efficiency worse. So you can save pump energy, but lose chiller energy. And remember which one uses the most? The chiller, right? So it can very easy, you can screw up the entire plant by trying to vary the flow through the condenser water system. And so it's a heavy analysis is needed, and even then we can't quite tell what to do. And I'll get into that in a second. So even in our life cycle cost analysis that we did with top modeling, which remember the top model is the best you can possibly do from a control sequence standpoint. If we had top perfect sequence of controls, variable speed drives were only marginally cost effective in offices. And so the worst thing is that we can actually make it come out higher. So as I said, we can screw it all up. Now that's just the energy side of things. What about other stuff? Well, when I reduce the flow through the cooling towers, I have the scaling issue. I might have to turn off a cell because my flow went down. Remember, I had 3 cells. I had 1 pump on going through all 3 of them. Well, if I start reducing that flow, I might have to start shutting off cells. And when I shut off cells, the efficiency of the cooling tower gets worse as well. If I don't shut off the cell, then I can have scaling and air bypassing the dry parts, which makes the fan energy go up. So I can make the fan energy way worse by making the water through the towel go down. I can also get fouling on the condensers. This hasn't been proven by any study to my knowledge, but it's a old wives' tale perhaps. But as the flow goes down through the condensers, dirt that's in the condenser water can settle out and foul the condensers. So lots of bad things can happen when I have variable flow through the condenser water. So let's just look at the energy side of things. We once again look at our top model, and we try to correlate the optimum flow rate versus plant load. And you can tell that the R-squareds aren't very good in this. They're sort of a scatter plot all over the place, just not a good curve fit. But let's try to do it then anyway. We're going to do a curve fit anyway. We got a straight line, not a very good curve fit, but it does have a slope and an intercept. We can make a line y equals mx plus b. So in this case, we're using c and d as the coefficients. We already used a and b, and we're going to make the flow set point equal to this flow ratio times the design flow. We're going to control the speed of the pumps to maintain the flow. First thing, by the way, that means we have to have a flow meter on the condenser water side. That can be a little hairy to do. If you use a full bore mag meter, it's probably okay. But almost any other kind of meter in an open water system tends to foul, particularly a turbine meter. But even a single point mag meter does as well. So that's a problem. We get the C and D coefficients only by optimization. You can't wag them. We couldn't figure out a way of doing it. But you can only get very limited energy savings from this. So here's the, annual energy use of the plant. This is with a constant flow condenser water pumps with perfect control logic. Here's variable flow condenser water pumps with perfect flow. So there is some savings. You can see from here to here, there is some energy savings on there. And here's with real sequences where we have variable flow, constant flow versus real flow. Once again, you do have some savings, not much. But here's the life cycle cost. So now we've not just looking at energy, but also the cost of buying the variable speed drives and the flow meter. And even with top modeling, we barely reduce the life cycle cost enough to call it cost effective. But with real control sequence, it's not even close to being cost effective. So the cost of having to buy the variable speed drives and the flow meter and the real sequences, which are not quite perfect, it's not cost effective. And worse than that, you can actually make the plant behave worse. If I took a plant in Denver but I use the slope and intercept optimized for Oakland, I can make energy use go up. So looking at the right, this is the plant total over here. If I use the top model, this is perfect logic, which nobody can do. If I use the sequences I get out of the standard is a little different. I won't explain what that is. But if I use the sequences from Oakland, the C and D modeling from Oakland, it goes up. So I made it worse. So using and the reason, and the same thing will happen if I use Miami with Oakland sequences. So here's the top model. By the way, standard, just so I can explain it. This is simply using the resets that are in AHRAE 55590. It has a condenser water relief formula, which actually works pretty damn well. So that's what that is. But the top modeling is perfect. This is the ASHRAE reset logic. And then if I use the Oakland C and D, the Oakland slope and intercept, I make the energy use go up. And the reason why this is because the slopes of the lines are so different from what's optimum. So the Miami is the top line, and Oakland is the bottom line superimposed on there, and they're quite different because of the nature of the weather. So the recommendations are use constant speed pumps for offices for dam sure or any normal application. Now some people put variable speed drives on everything, and they use it for like balancing, for instance. Frankly, it's a fairly expensive way of doing balancing, but whatever. But if you do, that doesn't mean you have to use it for anything other than balancing. Just figure out what your design speed is and leave it there. So maybe have a different number for whether there's one pump chiller running or two, but don't try to get fancy with the logic. Now, if you have a data center, now there's a lot of energy at stake, and using VFD can make some sense, but you've got to do the modeling in that case. Now, with a data center, you get a bigger fee, and you can spend some time with the modeling and make it work. All right. So that's pumps, cooling towers. Let's go on to chillers. So easy to stage fixed speed chillers. We do it just like you always did. You operate no more chillers than required to meet the load. So you stage them on based on when the load, when you've maxed out the chiller that's running. The load indicators can be lots of things. You can look at an actual calculation of load, or you can look at just flow or flow in delta T, whether the water temperature is starting to rise. There's other things you can do. Since most of our plants are going to have a flow meter on there, you can calculate load and simply use that. If you don't have a check valve in your common leg, you'll want to also make sure that you start the next chiller to make sure that primary flow exceeds secondary flow. We don't want to get that death spiral in there. So primary flow always has to exceed secondary flow. And then that's the staging on. Staging on is always easier than staging off. Staging off usually requires that you know the load. That's where the flow times the delta T comes into thing. You don't go back to the previous stage unless you're damn sure that that stage can handle the load, because you don't want to short cycle that chiller right back on again. What about variable speed chillers? So again, this is our top modeling. It shows that as a function of load, sometimes we want the optimum is one chiller. Sometimes the optimum is two chillers. What's going on here? Why would it be better at these low load conditions to run two chillers? The reason is because chillers are more efficient at part load than they are at full load. So here's an AHRAE or efficiency of a chiller, a fixed speed chiller and a variable speed chiller with no AHRR tolerance on this one. So we don't want any fake numbers here, right? We want the zero lying here. And you can see that as the load goes down, and this has condenser water relief. This means that we're also simultaneously reducing lift. The variable speed chiller starts out a little worse because it has the variable speed drive inefficiency to deal with. but then as it goes down, its efficiency goes down with it, and fixed speed. At some point, it also gets efficient as the load goes down, but at some point it crosses the line and becomes less efficient than design. So here's looking at a plant. This is a primary secondary plant, so it actually has primary pumps as well as secondary, primary pumps as well as secondary pumps. Whenever we turn on another chiller, we start another primary pump and another condenser water pump. So we're paying the penalty of the pump energy as well as the chiller energy. And this is just looking at the load less than half. So red is our variable speed chillers, and green is our fixed speed chiller. So let's start with green. With green, again, we're less than half the load. You can see that one chiller always uses less kW than two chillers. So again, if we're less than 50% load, you just run one chiller, no brainer. But with variable speed, you can see that it's actually more efficient to run two chillers for a while until you get to this point right here, and then suddenly it becomes better to run one chiller. So this is at about 35% or so of the capacity of the plant. So the chillers are running at quite low load, right? 35% divided by 2, and you're at the pump energy as well. But that's because we have a part load and we're resetting water temperatures. It's absolutely critical that we reset the lift down for this to work. So cautionary note, the chillers the logic must limit the possibility of surge. Centrifugal chillers will have a surge issue, which is a high load, high lift, low load situation. They have their own safeties to make sure they don't get there. But if they do get there, they're going to try to get themselves out of surge by speeding up or doing other things. So chillers are going to have both a variable speed drive, but they'll also have inlet vanes or some other device to unload in case the variable speed drives need to speed up. And so those are all sort of issues. With the logic that we've developed for guideline 36, it pretty much guarantees you're not going to be in surge because it actively resets the water temperature down. Here's a sort of graphical way of looking at it. Surge, again, is low load, high lift. This is different. Centrifugal chillers are different than centrifugal fans because centrifugal fans, as the load goes down, the static pressure also goes down. It inherently goes down. But with chillers, the lift is a function of the evaporator and condenser conditions, not the load. And I can have a low load when it's hot outside. Just have not too many air handlers on, and so the weather is going to drive a lot of the lift situation, not necessarily the load going together. So let's say I had a chiller running right here, and the load is 80-something%, the lift is something, and I say I'm going to run two chillers at 40% instead of one at 80%. Well, if I did that, I now have two chillers running at half the load, but the lift is going to stay the same. The lift is what's being determined by the weather and the water temperatures. And it's not going to change whether I have one chiller running or two chillers running. So by cutting it in half, I now put the chillers into surge, and we don't want to do that. So we got to make the lift go down when with the chillers, or said another way, we make the lift go down all the time and then allows us to stage the chillers down with it. So if the lift were lower, then it's okay to go from one chiller to two chillers. So top model, once again, we look at the number of chillers running. Blue is one chiller, red is two chillers. And we look at the lift versus load. And again, it tends to correlate, but it correlates on a sloped line. So to the left of the line, we want one chiller. To the right of the line, we want two chillers. It's hard to make Excel make a regression on this. You sort of have to do it manually, just visually draw the line. And you can see that there is going to be a slope and an intercept. That left is 1, right is 2. And same with of here, different climates, different chiller types, different everything, but all of them have a left is 1, right is 2. And so we create a line again. And now we went through A and B, and then C and D, and now we got E and F. So the slope is E, F is the intercept, and lift, of course, is the X variable. on the bottom. And then we have this the SPLR, which is the staging PLR. It's the PLR that I want to stage from 1 to 2. And the logic will be if the actual load is greater than the SPLR, I'm going to stage up. If it's less than the SPLR, I'm going to stage down. There's a couple other safeties in there where I'll stage for different reasons, but from an energy standpoint, I'm going to stage when the load is greater than the SPLR to the right of the line, and stage off when I'm to the left of the line. How do you determine E and F? Well, once again, you can do it with simulations, but you can also do what we did for the A and B, where we came up with some decent number that works well most of the time, and that is looking at our minimum lift and our design lift and to come up with those numbers. So here's what we came up with. So you can use these equations from your design lift and your minimum lift so that any chiller plant can use this logic. So this is what's in guideline 36. So if you want more information on optimized sequences for plants, you can buy the research report from RP 1711. That was the research logic that created the sequences that are in guideline 36. And you can also just get them by buying guideline 36. I think I said it was like $30. This says $125. I'm not sure which is which, but anyway, it's a cheap investment to buy the guideline. It includes sequences for almost everything now. It's got all the VAV systems down. It's got all the plants, both hot water and chilled water, and fan coils and a whole bunch of other stuff. What it doesn't have is DOAS. It doesn't have any dedicated outside air system sequences yet, because we're waiting on a research project that ASHRAE has been doing to come up with logic that optimizes DOAS sequences. Lots of people use neutral air as the optimum DOAS sequence. I can assure you that it's not the optimum even close. So we need to do some research, like all this stuff. We did research to figure it out and what the best logic is. Unfortunately, COVID caused that project to get put off for like a year and a half. So it's just now being done. So that'll be added once that research project is done, but almost everything else is in there. So speaking of guideline 36, if you want to use guideline 36, you can buy it and cut and paste the sequences and put them in your spec. But another way is to just say, use guideline 36 and then put this in your spec. To qualify for this project, the primary BAS manufacturer shall agree to fully program and test all ASHRAE guideline 36 sequences that are referenced herein for their dealers bidding this project at no direct cost to these dealers. The cost of the guideline 36 programming and testing shall not be a direct cost of this project. So basically it's saying, manufacturers, if you want to do this, you got to do the guideline 36 sequences programming for your dealers. And don't put it on this cost. I want it to be done for me. That should make my cost on this project go down for using sophisticated sequences, not up. And right now there are 8 manufacturers, BAS manufacturers, all the major ones, that claim to have at least some of the control sequences from 36 pre-programmed. I don't know of any actually that have the central plant programmed, but I can tell you, if you won't let them bid on the job until they do, my guess is that they'll probably say okay, and they'll do it. They're just waiting for the cost impetus to make it worth their time to do the programming for their dealers. The idea behind guideline 36 is that the programming gets done once per manufacturer, and then all the dealers don't have to do it again, so we don't keep reinventing wheels. Okay, how much time do we have here? Let's see. It is 4:08. I got till 4:30. Good. So we have a little time here to talk about the tier plant. When we go to all electric, we use heat pumps. The conventional way of using heat pumps instead of boilers is to just simply have air source heat pumps do the heating. The cooling side stays exactly the same. And we just simply take a boiler and make a heat pump out of it. But the bad thing is that heat pumps cost a good 10, 20 times more than a boiler. and they also have high maintenance costs. They take up a lot of space as well. And they're not really very energy efficient. Right now, Title 24 still uses gas as the baseline. So if you're doing a budget run, energy budget run, you're going to pay a penalty to go to a heat pump, because even though you have a COP of 2.5 or 3 or whatever, it is not going to compete to a condensing boiler. And so you're at a disadvantage. So it costs more, the maintenance costs are higher, and the energy use is not as good. Wow, why would we want to do this? Well, we want to do it because we want to be low carbon. We want to reduce our carbon footprint. Right now, all the economic factors are against it. It doesn't make much sense, but it's going to change over time. First of all, people are making us do this, but a lot of cities are requiring that we have air source heat pumps, or all electric plants rather. And then, of course, the economics will change as more and more people stop using gas. The price per therm is going to go up for gas, and eventually it's going to start make sense to use electric. However, it's still not a great solution, right? The air source heat pump is expensive, et cetera. Now, on a big building, if you're Title 24 is going to have modeling rules. And if you're bigger than, I think it's 5 stories and 250,000 square feet, something like that, forget the real numbers, the baseline central plant that you compete against is a water-cooled centrifugal chiller plant like what's drawn here. And if you say, well, I want to go all heat pumps, but I'm going to use the heat pumps to also be chillers. All heat pumps are also chillers. They have to do defrost at some point, so they have to have reversing valves so they can actually create chill water too. So I could say, hey, why do I need this water-cooled centrifugal chiller? I'm buying all these heat pumps. Let's just use them for cooling as well. The answer is you can't, because you can't possibly pass the energy model if you have a big building where the baseline is water-cooled variable speed centrifugal chiller. It's the best chiller plant you can do, and that's the baseline. So you got to come up with something different to meet Title 24. So here's an option that has a heat recovery chiller to try to take advantage of some of the simultaneous heating and cooling that may be happening in a plant. So heat recovery chiller is one where instead of sending all the rejected heat to a cooling tower, if it's appropriate, if it makes sense, I can send that rejected heat to the building as well. And this can save a little bit of energy, but it requires that you have simultaneous heating and cooling. I have to have the chiller on at the same time as I have heating use. So think about this. If I have a system with an air side economizer, below 55, we don't need any cooling at all. Really, it's below about 60 if we're resetting air temperatures off the air handler. So below about 60, we don't need any cooling. So we'll finally turn on the cooling when it's roughly 60 outside. But at that point, how much heating am I doing? Well, if I'm using guideline 36 for my VAV box controls, you're using very little heat in that situation. So simultaneous heating between 60 and 70 degrees. Above 70, I don't even need the heat. So only in that tiny window between 60 and 70 am I going to see simultaneous heating and cooling. And when I do, in both cases, the loads are very small. I'm just trimming the supply air temperature on the air handler. I'm still on economizer, and I'm just tweaking some reheat at some zone levels that maybe need a little heat or a little reheat for ventilation purposes. So there's not a lot of energy to be saved from simultaneous heating and cooling. What about thermal energy storage? I could do a conventional chilled water thermal energy storage and hot water thermal energy storage. Now I don't care about simultaneity. I can shift the loads. I can pump when I'm heating in the morning. I can suck energy out of the tank and pump it into the building. When I'm cooling, I can do it at night. I can cool down the tank at night and then pump that into the building. So I don't have to worry about simultaneity. That's great. However, it has super high cost and lots of space. These tanks take monstrous amounts of space. You're not going to be able to do it for your normal office building. It has to be like a central plant for a campus. So what about ground coupling? So with ground coupling, we're essentially using the earth both as a heat source and a heat sink. The idea of this is that I can actually shift loads from summer to winter with enough of that bore field. You make it big enough, and in summertime, I could just pump energy into it, and in the wintertime, I can suck energy out of it, and I can make that work. Unfortunately, it has very high costs, and leaks are a common problem from all those underground tubes that end up shifting over time with the earth moves, and earthquake would be disastrous. And there's also a problem in our climate is that we are not balanced between heating and cooling. And so if you don't have some other way of getting rid of heat, the heat field heats up over time and it no longer works anymore. The ground we think of as infinite, but it's not. So over time, that bore field is going to get warm. So we also have to put in a cooling tower to get rid of some excess heat so that the annual heating sucking out equals the annual cooling sucking in or placing in. So it becomes a plant that also needs a cooling tower and a bore field. And it's really hard to make this work when you don't have a lot of footprint in your building. It's going to be really hard to make this work in a downtown office building when the footprint is the size of the building itself. You got to go way, way down to get enough heat transfer area. So that doesn't work. So what we found is that, oh yeah, this is the comment I just made about balancing the loads with a cooling tower as well. And so what we came up with is time-independent energy recovery. What happened is that we were working on a plant down in LA that does have a bore field, does have heat recovery chillers. It looks just like this, except multiple machines of each. And we were coming up with control sequences for it and optimizing its control. And it occurred to Brandon, one of my partners, he said, hey, you know what? In California, we don't have to shift from summer to winter. We don't really have a summer or a winter, right? I mean, we have sort of predominant loads, but it isn't really a summer and winter like it is in the East. Instead, we have a morning and an afternoon. We have diurnal swings where it's cooling in the afternoon and heating in the morning. So we don't have to worry about shifting the entire year from summer to winter. What happens if we just look at shifting from morning to afternoon, making it so that we can use a tank that's not a chill water tank, but a condenser water tank. And we can use it to store energy so that I don't have to worry about simultaneity of simultaneous loads like that earlier one I showed you. We still have the ability to shift the loads, but we don't want to make it so big that we could shift. We don't need to shift from summer to winter. We just got to shift from one day to the next. So when you do this, we end up with a size of tank that's much, much smaller than if you did thermal energy storage for hot, and there's only one of them as well. And if you're a high-rise building, you can use the tank for fire water storage, which you had to have anyway. So two of our buildings that we're using this on are high-rises, and in both cases, we are using the water as the source of fire water that we have to do anyway. Fire water tanks are less expensive than a thermal energy storage tank because this needs to have insulation, so it's a steel tank with insulation. Fire water tanks are usually concrete with no insulation, so it's not quite a trade-off, but still that weight and space needed is a perfect trade-off. And it's much smaller than if I use chill water and hot water independently. So it takes a small footprint, and it is very energy efficient. It allows us to do lots of heat recovery, and it makes the heating side of the thing much more efficient than if I was using air source heat pumps alone. So for instance, this heat pump here is simply used to charge the tank. I don't need very many of them or very big ones because I have all night to charge the tank. And so I can be bleeding the charge in over time, and then I suck it out with my heat recovery chillers and put it back into the building. And the COP of the system is much higher than if I'm using the heat pumps alone. However, it is very complicated. I won't go through all the details of this because I want to show the pieces of it. and show you how, let me just, I forgot if we had the space thing. No, shoot. One of the things I did want to include, and I missed the slide, is just how much space is needed on these things. So with air source heat pumps, you can need a lot of space for them to do all the heating in your building. If you have a high-rise building, a typical downtown San Francisco, Oakland building, there's not enough roof space to put enough heat pumps on there. One of our buildings in downtown San Francisco, we figured that we would have to have 14 of the largest heat pumps made. We have to cantilever them out over First Street in order for them to heat the building in lieu of boilers. So it just becomes impractical. And they're super expensive, as I mentioned. So by buying one tank, I can go from about 10 of these heat pumps to 2. Now I have plenty of room for the things, and I just have to find a place for the tank. Well, it turns out in a lot of times, finding a place for the tank isn't that hard. As I mentioned, we often have fire water storage anyway. If you have a garage, garages always have a dead corners, right? You can't park in the corner. And so you can simply make a hole in that corner and put a tank in it. And if it's a 4 or 5 story garage, it's plenty of height to make a good stratified tank for no extra space at all. That corner was going to be dead one way or the other. So we're doing this on several buildings now, and in all cases, we had really very little problem finding a place for the tanks. One was a little bit of a problem, but we found the place for the tanks in the building. When you have a garage, you're in great shape. You can find the tanks, a space for the tanks easily. So it turns out that the cost of a tank is way less than the cost of the added heat pumps I would have if I didn't have the tank. So what we're finding is that in every case, we've had contractors, we've done detailed designs where they can estimate it, and contractors are come out saying that this is less expensive than the option of using all air source heat pumps to heat the building. So it's less expensive and it's much more energy efficient, and you can meet Title 24 even now before the rules change. The rules are going to change and make all electric easier, but now before the rules change, they are. So here's the plant for this is a real building. We've got heat recovery chillers. We have one cooling only chiller because the cooling load is bigger than the heating load. And here's a situation where it's a heating design condition. We also have some concurrent loads. One of the nice things about a plant like this is you don't care what you put on it on the chilled water side because we got heat recovery. So I don't have to worry about, I can put all the fan coils for the IDF closets on chilled water instead of putting in split systems all over the place, because it's okay to run the plant for tiny chilling loads because I'm recovering all that, the heat that's being rejected from those loads. So I've got the heat recovery chillers that can do heating, but they can also do cooling. I have my air source heat pumps for charging the plant on a design heating day. And then I have my tank. And the tank temperatures are going to vary from, like in this case, 80 to 40. So it can actually, depending on the time of year and the time of what the loads are, it can vary. And then we have the cooling towers to get rid of excess heat and the normal heating load. So here's my heating operation. I've got all three of the chillers indexed to heating. They're heating, they can't make very hot water without being very inefficient. So like air source heat pumps, they're sort of limited. By the way, doing a 25-degree delta T with 125-degree water requires some thought on what kind of heating coils you're going to use. So that's a thought for another day. Now I have a situation where I'm heating, but I'm also simultaneously doing one of the chillers to cooling load duty. So it's simultaneously heating and cooling at the same time. And then here's a mild weather afternoon where I'm charging the tank. So all the chillers are doing their duty, but there's no heat recovery going on. I'm charging the tank with hot water. And then here's one with one or more of the heat recovery chillers are indexed to cooling. 2 of them are shown here into cooling. 1 of them still heating, sucking energy out of the tank. And here's where all the heat recovery chillers are doing cooling. So this is when we have a near peak day, but we also have some heating to do. So one of the units is actually pumping water into the heating system, but the rest of them are sending the water to the cooling towers or the tank, or the cooling towers in this case. So it's complicated, all right? Don't deny that. The control sequences for this plant take about 30 pages. So it's not easy, but it's both less expensive and more energy efficient than what other people are doing, and it takes up less space. So it's a super great idea. If you one of the references at the very beginning of this presentation gave a link to the title of the paper that's on our website, so you can read all about it. And we would be happy to help anybody to implement this design. All right, so wrapping up here, you have learned techniques to design and control chiller plants to near life cycle costs minimums. So selecting optimum chill water distribution systems, optimum chill water supply and return temperatures, optimum condenser water and tower range and approach, tower efficiency and tower speed controls, optimum chillers and towers, using performance-based bids and life cycle cost, and optimizing sequences and set points. And you also learned about tier, which I think is pretty exciting, and something that those of you, by the way, the tier concept is only really good on big buildings, right? You can imagine that just looking at the thing. The smallest building we've used it on now is 250,000 square feet. So it's definitely a big building system. It's a building that you already were, chilled water and hot water. You weren't using packaged rooftop units or something like that. So that's a limitation of it. All right, we have 4 minutes left. Does anybody have any questions? Feel free to unmute yourself. All right, so not hearing any questions, I will sign us off then. So thanks everybody for attending. And don't forget to use this SurveyMonkey link. It's on the in the slides that you downloaded, but also I think it's also in the message box that was done as well. But I like this cartoon. Science versus everything else. Simple but wrong, complex but right. And that's the way chiller plants are. So thank you all for attending, and we will sign off right now. Thank you.